Лучше это сделать. Там еще есть было решение.
Well, so good morning, everybody, and we are starting our workshop with the greetings from the Directorate of Joint Institute by Vice Director and also just well-known spin physicist Richard Lenin.
Okay, dear participants of the conference, dear colleagues, friends, it is a pleasure for me to welcome you here in Dubna at this workshop. I should say that the Joint Institute has a long-standing tradition in experimental and theoretical physics related to the spin phenomenon. So you probably know that back in 1981, the first workshop in high-energy spin physics was organized in Dubna by Lev Yosifovich Lapidus. These meetings became traditional and regular due to initiative of Anatoly Vasilyevich Yefremov, the chairman of this workshop or conference for many years. Joint Institute has a long-standing tradition in building powerful accelerators, starting from the famous synchrocyclotron and synchrophasotron, powerful cyclotrons in laboratory of nuclear reactions, and the first superconducting relativistic heavy ion synchrotron, so-called nucleotron. The current workshop is taking place in the important period of development of particle and nuclear physics in our institute, which is related to the start-up for super heavy element factory based on the new cyclotron DC-280, and with a progress in building the NICA accelerator complex based on the existing nucleotron facility. NICA means nucleotron ion collider facility based on the nucleotron. The main physics goal of NICA is to study a hot and dense QCD matter, including the search for critical point and mixed phase. The NICA program in collider mode is complementary to the future fixed target program of FAIR at GSI, and it will continue the program of beam energy scan at relativistic heavy ion collider in Brookhaven, but with much higher luminosity. Another important direction of experiments at NICA is devoted to spin physics. It will explore both collider and fixed target modes using polarized neutron and proton beams. There will be a dedicated session at this workshop devoted to spin physics at NICA. Thus, the spin physics program is an important part of the sophisticated fixed target experiment baryonic matter at nucleotron. The spin physics program in the collider mode will be realized with the help of the main multipurpose detector, as well as with the help of dedicated spin physics detector, the design of which is under preparation. The main goal is a study of single spin asymmetries in the ion processes and investigation of new parton distribution functions. Also planned is a study of the spin-related signals of collective effects in heavy ion collisions. Particularly, the vorticity may serve as a new source of hyperon polarization. I would like to thank organizers for their uneasy work. Wish you interesting talks, illuminating discussions, and a nice and pleasant stay here in Dubna, and Joint Institute. Thank you for the attention.
Okay, thank you. Thank you very much.
And I should leave.
Yes. Okay, so Jeff, we continue, and let me continue by the some так, как бы его сделать полноэкранным? Там нормально. Ага. So just okay. So we start our workshop, and actually just the first point I have to mention with regret, of course, that since the previous workshop, which was 2 years ago, we just lost two just very good scientist and very nice person, and the experimentalist, well-known experimentalist from Protvino, who started also spin physics in Dubna, Sandibek Nurushev, and just this year, Jacques Soffer, who is well-known for his very important work in spin physics and last decades in QCD spin physics. And they both participated in our workshop, so I just took the titles of the но тут-то не двигается. Или здесь двигать, да? Тут я вижу, а тут нет. Ничего. А вот как-нибудь попроще. Нет. Well, we have, as you might mention, that this hall is renovated. Also, there is a new logistics here, so just it's generally very good, but we have to. Алло. Алло. Да, ага. Да, ну я его. Well, so just what I said, that this is both Sandibek and Jacques, they participated in our conferences, and here there are titles of the talks. То есть можно сейчас двигать будет, да? Нормально. Well, so this is just I wanted to start by commemoration of paying tribute to them. And so just I would like to ask you to stand up to honor their memory and have a minute of silence. Thank you. And another just event of this is the 100th anniversary of the birth of Yuri Kazarinov, well-known Dubna physicist, and there will be a poster situated just here near the entrance to the hall, but by his colleague, Levan Glonti. And so just as it was said just by just Richard Lednitsky, the series started actually quite long ago, and in year just 81, so we should in 2 years we should may have 40 years from it by Lev Iosifovich Lapidus. And at some quite long ago, so this meeting became regular meeting. So we have it since 2001. We have it each 2 years in the odd years between big spin symposia. And Anatoly Vasilievich Yefremov is the permanent chairman of these meetings. Unfortunately now, because of just his health condition, he cannot participate in all the meetings, but just we will see him definitely at the conference dinner, maybe in some other session. Just now he is following our, and he is constantly following our just talks by just remote system. Just and again is what sets the speciality of this of the just current situation in Joint Institute, that there is so-called mega science project developed here and another site of the institute, and this is accelerator facility constructed using the existing nucleotron, and the physical tasks combine both heavy ions and hadronic physics. And spin and Nika will be essentially just discussed in our workshop. And just the important points that there is a dedicated experiment, SPD, and we will start to discuss it just today and continue it on Wednesday. And also there is a polarization in heavy ion collisions related to such interesting just phenomena as very high vorticity and very high rotation and very fast rotation, actually fastest ever in the universe rotation, its acceleration. And so this makes interesting contact to gravity theory. So these theoretical issues will be also discussed, and there are talks mostly on Thursday and also today. Well, and there are also other subjects, and this is what is constantly discussed at our meeting. There is a COMPASS and AMBER experiments, mostly on Tuesday, and related QCD important subjects of TEDs and GPDs on Wednesday and Tuesdays. Today we'll have just extensive discussion of EDM and best 3 experiments, and on Friday we will discuss also spin physics at LHC, predominantly at CMS. So some practicalities. So lunches, there are various places for lunch, but probably the canteen here on site just is the just best way. We have a lunch break from 1:30 to 3. So typically at 2 o'clock the queue in the canteen is decreasing. So just, and it's the best. It's very close, but because many people know, so it's better to those who are here first time to join. So we will have today welcome party, which is just here
opposite our lecture hall. It will be a concert in the Dubna School of Music, which is just very, also it can be found on the plans. It's on the way from 5 minutes walk, so everything is very close. And workshop dinner will be in the hotel restaurant. And so just our just workshop is in the general program of SPIN meetings. It's supported by International Committee of SPIN Physics Symposia and of course by Joint Institute. So welcome. And well, and so just now we are in position to start our regular scientific program, and the first speaker is Patrick Adlarsson from Uppsala on hyperon spin polarization and CP test at BEST-3. Тут нормально будет остаться? So, 40 minutes. Yeah, you can use better this. No, not this.
Okay, thank you for this kind invitation to give a presentation, and I'm delighted to be the first one to set off this workshop. So I'm going to talk about hyperon spin polarization and CP tests at the BEST-3 experiment. So there are two fundamental objectives of this, well, of hadron physics, but of this talk. So looking at hadron physics, we want to understand its structure at the femtometer scale. And even after 100 years since the discovery of proton, there are still many aspects that we do not understand. So its mass, its spin, its radius, and its structure. And so we're going to hear talks about that during this workshop. So one way to better understand the fundamental properties of the nucleon is to study another system with slightly different properties. So for instance, if you exchange one of the constituent quarks and replace it with the heavier cousins, for instance, a strange or a C quark, then you can study the nucleon but with slightly different properties. So these are hyperons, and they can be used then to increase our understanding of matter. Another fundamental objective is to understand the matter-antimatter asymmetry of the universe. So as we know, the universe consists mostly of matter, hardly any antimatter. So if this is not embedded as an initial condition, there must be some dynamical mechanism which is responsible for this asymmetry. And so the Sakharov criteria, there are 3 Sakharov criteria. And the second one, that there must exist C and CP violating processes, is what I'm focusing on in this talk. But this is then the search that's ongoing. And so we know that in the standard model, we have the CKM mechanism that incorporates the CP violation. However, it's not sufficient to explain the observed asymmetry of the universe. So here one can use hyperons and anti-hyperons to probe the matter-antimatter asymmetry of the universe. Come back to the first objective then. To understand the hadron structure, we look at the electromagnetic form factor. And so it's a fundamental hadron structure related to its charge and magnetization density. And these can be accessed in different kinematic regions, so space and time-like. However, using hyperons in space-like experiments is difficult because due to their finite lifetime, they exist quite shortly. So they make them unfit to use either as a beam or a target. However, we can access the electromagnetic form factor in the time-like region through annihilation processes where you produce the hyperons in E+ E- collision. So if you assume the one photon exchange in the production of the hyperon-anti-hyperon pair, You have the Born cross-section, which describes the behavior. So we have one magnetic part and one electric part, and some kinematical factors. A useful observable to study is the effective form factor, and goes as a square root of the Born cross-section, and that's useful if you have a low statistical sample. Okay. Something which is a little bit peculiar is that the time-like form factors, I mean, the hyperons and baryons can be polarized even if the initial state electrons and positrons are unpolarized. And that comes from intermediate hadron-antihadron states, which can polarize the final state. One can also look at it as different waves which interfere with each other. So in this case, it would be S and D waves. So that means that you can describe the electric and magnetic form factor part into this absolute value here and multiply by a phase. So then one can describe the form factor in the time-like region by these three observables. So you have the effective form factor, you have the ratio between the electric and magnetic part, and you have a relative phase between the electric part. And so if you have a relative phase in the production of the hyperons, that means that these are produced in a polarized state. Okay, so looking at the polarization then, there are a few properties that we can discuss. So when the initial state is unpolarized, so E plus E minus beam they are unpolarized, and the process is parity conserving, the final states are particles are always polarized perpendicular to the production plane. And the relative phase is both production related and depends on both the CMS energy, but also on the scattering angle of the produced hyperon. Since the polarization comes from interfering, or can be understood in terms of interfering amplitudes, so S and D waves, that means that if you're close to threshold, D waves do not contribute at all. So that means that you have no polarization at threshold. Also, the analyticity requires that the space-like and time-like form factor agrees, and since space-like form factors are not polarized, these analyticity requires that they should agree with each other at infinity. That means that the time-like form factor also should be non-polarized at infinity q squared, meaning then that delta phi is 0 there. Okay, so looking at then the decays of hyperons. So one thing is then to have them produced in the polarized state. The other is to actually measure their polarization. And here hyperons is a good tools for that, because in lack of polarimeter, one can still measure the polarization of the hyperons by looking at their decay products. So if you have the most commonly discussed hyperon decay is lambda going to proton pi minus, then by looking at the angular distribution of the proton, one can access the polarization of the mother hyperon. So the angular distribution is given something like this. You have a factor which is a symmetry parameter, and then a factor which is the polarization of the mother hyperon. Okay. Looking then at the asymmetry parameter, these describe of a weak decay. So these are weak decays. They describe the relationship between the parity violating and parity conserving part. And experimentally, okay, so you have three factors, alpha, beta, and gamma, but experimentally you can extract alpha and the weak phase angle, which are determined experimentally, and from that you can access the beta and gamma parameters. The weak phase angle is more challenging to measure, so it requires either a polarimeter or one can study it in double sequential or triple sequential weak decays. For instance, a cascade, double strange particle decaying into a lambda pi, and then lambda decaying into a proton pi. So both the alpha and phi are CP odd observables. So meaning if you study compare the symmetry parameter of the alpha going to proton pi minus and compare it to the symmetry parameter of its antiparticle, so lambda bar going to a proton bar pi plus, they should have the same value but differ in sign. That means that you can then perform a test, a CP test, and if CP holds, then this should be 0. Okay, so the best limit of CP violation is given by this value. However, this test, CP test, is not limited only to lambda decays, but also other weakly decaying hyperons, so sigmas and cascades and omegas. So where we're doing all these measurements is in Beijing. So in the BEST-3 experiment, and it's located at IHEP at Beijing, in China. The data taking has been ongoing since 2009, with a peak luminosity of 10 to the 33 inverse squared centimeter inverse second. BEST-3, the detector itself is being a plus minus experiment, a multi-purpose detector, is suitable for studying hyperons or doing high precision measurements with hyperons. So one thing is that it's a multi-purpose detector, so we can measure both charged and neutral particles with a very good angular coverage. It has symmetric particle and antiparticle conditions. Well, since an E plus E minus experiment, you also have lower hadronic background compared to hadronic experiments, which is important to constrain the background, important for these precision tests. We have good control of the systematic uncertainties and also large data samples to perform these precision tests. So this is what a hyperon bar event can look like. So a lambda bar. The cross-section view here. So this is the proton bar and proton pi minus and pi plus. So the charge track coverage is quite good. Momentum resolution is 0.5% at 1 GeV over C. Slightly less good efficiency for neutrals and energy resolution. The calorimeter consists of 2 parts, and a barrel and an end cap part. For PID, one can use time of flight together with energy loss information of the main drift chamber, if one is interested in that. So coming now to the results that the BEST-3 has obtained. So one thing that we want to ask is the cross-section behavior. Okay, so before, well, up to last year, only Babar and the DM2 collaboration had studied the cross-section behavior. And the BEST-3 came with 4 more data points. These higher energy data points were measured exclusively, so studying all final state particles. And they are in good agreement with what's expected, or with comparison to the Babar and DM2, and with the perturbative QCD fit. What's more interesting is this very low energetic data point. So this was measured at 1 MeV above threshold, and one has seen enhancement effects in proton-proton bar. So the question is, what's going on here? So this is a little bit more difficult data point because close to threshold, it's difficult to measure all the final state particles. So 2 channels were used. So the proton bar pi plus and neutron bar pi naught was used to obtain the cross-section. Due to lower statistics, we can only measure the effective form factor. But this big jump at the data point close to threshold is something that's worth noting, and more data is definitely needed in this close to threshold region. Compared to theoretical predictions, there aren't that many. Looking at the lambda bar. The best, or the one that I know which is the best, is from Heidenbauer-Meissner in 2016. And they cannot, by the way, they cannot explain this data point either. At the time, these were preliminary results. So it calls for more data. But what they also did was they looked at the other properties of the form factor. So the ratio R, so between the electric and magnetic part, and there you see there are only measurements from Babar with quite large error bars. For the polarization, there were no measurements at all, because Babar tried, but the results were inconclusive. Okay. For their study, they used lambda bar final. They focused on lambda bar final state interactions, and they used PS185 data as input to fit their lambda bar potentials. So this inspired the best three to do a first complete measurement of the lambda bar electromagnetic form factor. With a large available data sample at 2.396 GeV. It's an exclusive analysis, all final state particles measured, with the selection criteria to contain all the good events. Okay. Also 4C kinematic fit was performed, giving 555 events, and also a sideband method was used to estimate the level of background, and the level of background is roughly 2.5%. So quite a clean sample. So when you have the final state sample, you want to obtain the parameters, and so for that you need the production and decay process described in an amplitude, and this is given in a simplified form here. Due to the statistics, we assumed the alpha or the symmetry parameter values based on the latest PDG result. But what was the interest here is to obtain the values of the eta and the delta phi parameter. And that's what used to obtain a maximum log likelihood method was used to estimate these parameters. So the eta then is a function of the R value, which means that if you determine eta, you can determine R, because tau is just a kinematical factor, and the polarization here. These are just, and these T0 to T5 are five-dimensional functions based on the experimental data. So these are the angles which are measured. So theta is the scattering angle of lambda. Theta and phi p they are the helicity angles of the proton, which means that they are the angles measured in the rest frame of the lambda system, and well, correspondingly for the antiparticle. For the cross section, then we have obtained a very nice, precise result. Also for the effective form factor part. For the ratio, we obtained the value close to 1. But what I want to focus here is on the polarization. So for the first time, we determined the polarization for any baryon. Okay, so that can be seen from this moment. So it's a comparison between the angles of the proton and antiproton, and the behavior given here is indicative of polarization. So you have the red, which is the fit, and the black and blue are the data points. And then you have the blue line here, and that corresponds to Monte Carlo phase space. So if you have no polarization, this is what one would expect. So we have a clear non-zero value of delta phi. So this shows that at this energy, that S and D wave amplitude both contribute to the production mechanism. Putting now the best three results together with the Haydn-Bauer-Meissner prediction, our results are much more precise for the R value, but for the delta relative phase, the error bars are a little bit larger, but still it's first measurement. Okay. So we are interested, of course, in more, a better understanding of the form factors. So there are more lambda bar energy data points available at various energies collected by the best three. And in order to obtain more statistics, we use, these are analyzed now in an inclusive tag mode. And machine learning techniques are used to suppress the background. In addition, there are also other modes being analyzed, so lambda sigma naught bar and sigma naught bar. So before I showed you a simplified version of the production and decay. If one expands it a little bit, this is the full production and decay amplitude for E plus E minus to lambda bar. So before I looked at the electromagnetic form factor. However, one can use exactly the same amplitude also for in the case that the lambda bar are produced via the J-psi resonance. And that's interesting because for us, we have lots of J-psi events, so 10 to the 10 J-psi events, which were recently collected. Which means that since we have such a high statistics data sample, we can also try to estimate the value of the symmetry parameters and then perform tests on CP symmetry. So then in this case, what you have here are several terms. This term gives the baryon angular distribution parameter. So this gives essentially the cross-section, differential cross-section. These are spin correlation terms. So alpha minus here denotes lambda going to proton pi minus, and alpha plus denotes the lambda bar going to proton bar pi plus. And in these terms, they all are correlated. That means that we cannot use these values to extract individually alpha minus and alpha plus. However, if you look at the last line here, you have them disentangled from each other, only in the scenario that these are produced in a polarized state. So if delta phi is 0, then this term disappears. Okay, and then we cannot access the asymmetry parameters individually. Okay. So the question is, is it polarized? Are the lambdas and lambda bars polarized? Okay, so these were the results here I'm showing came from 1.3 billion J-psi events, and with the branching ratio and efficiency, we collected 420,000 events in the final event sample. For lambda and lambda bar going to proton pi minus. In addition, in one leg, it was studied the lambda bar to neutron bar pi naught was also studied, was also included. As you can see, these are log plots, so these are good agreement between data and Monte Carlo. The background levels is extremely low, so less than a fraction of a percent. And also here, a maximum log likelihood approach was used to estimate the parameters. So again, this is the moment which gives the indication of the delta phi and the polarization. So again, the blue band would be compared to is phase space, so no polarization. And this fit compared to the data points show a clear sign that the lambda and lambda bar are polarized. Also with a little bit lower statistics for the pi minus neutron bar pi naught. So this is the relation between the polarization and the delta phi. And so here, okay. So here is what I explained to you a little bit earlier, is that the polarization is dependent on the scattering angle of the lambda. And so the delta phi was measured to 42.3 degrees, which gives a max polarization of 25%. For the maximum delta phi, the polarization can reach 36%. Just to compare, okay? So since this is non-zero, this allows for a direct and precise measurement of the symmetry parameters alpha minus and alpha plus. For the alpha, going to lambda proton pi minus, what we found was that the obtained value was more than, or almost 20% off from the PDG value, and these were, which were based on results from the late 60s, early 70s. And in our field, these PDG values were simply used, taken for granted, and have been used by several experiments, well, for other purposes, which means that given our results, all the results which use these PDG value, the old PDG value, they have to be either rescaled or remeasured. Okay, so that was one thing. Inspired by the result from BESS3, also Kaon data from JLab were remeasured by David Ireland and colleagues, and they find also a slightly larger value compared to the PDG value, or the old PDG value, but not still in agreement with our results. Also, for this, in this case, J psi going to lambda bar, the correlation factor is quite large, so one can assume that they are almost equal to each other. If you assume they are equal to each other, the average value gives 0.754 with low error bars, which is still quite off, a bit off from this remeasurement. So there's still independent measurements of alpha, of this alpha value for other decays. So for instance, from cascade decays in the future. Looking at the CP test, this is the first measurement in E plus E minus experiments to extract the lambda in its most precise value at roughly 10 to the minus 2, 10 to the minus 3. This is, well, consistent with the standard model, and this is also expected. So you see the CP symmetry breaking is at the order 10 to the minus 5. Okay. So this is the most accurate test up to date. So this was based on 420,000 events. For BESS3 in the future, we have just collected this 10 billion events, and analysis is ongoing, calibration is ongoing. So that means that one can expect the statistical uncertainty for the CP test at 5 to the 10 to the minus 3. There are also plans for a super tau charm factory in Novosibirsk and also China, with the estimation of 2 times 10 to the 12 J size, we can expect the uncertainty to go down to 10 to the minus 4. Okay. So the same formalism used for lambda lambda bar can also be used for other processes, and these have been, this list here contains processes which have been measured and analyzed by the BESS3 collaboration before, but they were used for studying for different purposes, so studying branching ratios and these alpha psi's. So all of these can be remeasured for the purpose of studying the symmetry decay parameters and the polarization. In fact, the entire baryon octet is kinematically available within the J-psi resonance. So actually, my colleague has worked very hard to get the next results I'm going to show to be preliminary, and so these are workshop exclusive for this workshop. Yeah, first time these are presenting. So also for sigma bar, you can use the same formalism. In this case, one can study the sigma going to a proton and a pi naught. For the symmetry parameter, it has been measured for the particle, but not for the antiparticle. Of course, we do not expect these to deviate significantly. The standard model sets the CP symmetry to 3.6 times 10 to the minus 6. Okay. But still, it hasn't been measured before. Okay. There are also other motivations, which I'm not going to go into now, for studying this decay. Okay. But in addition, I mean, I showed you the polarization for J-psi, but we also have other CC bar resonances, and so, for instance, the psi 3686 we haven't looked for polarization of baryons there either. So this would be a first measurement for studying polarization for any baryon at the second resonance. So this analysis is also based on 1.3 billion J-psi events and 200 million psi 3686 events. Not much to say about the event selection. So these are charge track selection and combinatorics to find the best 2 pi naught candidates with kinematic fit for reduction of background and so forth. Roughly 80,000 events is for the exclusive channel, sigma plus, sigma bar minus. And for the lower data sample of psi 3686, we have 5,000 events. Again, the same maximum log likelihood method is used to estimate the parameter. Here, these are taken together in a joint likelihood, so both resonances are fitted simultaneously. So we have alpha J psi and alpha psi 3686, the delta phi for J psi 3686, but the symmetry parameters are the same for both samples. Okay. And also here one sees polarization more clearly seen for J psi compared to psi 3686. But it's still a significant detection of polarization, or also for this second CC bar. Also, the value of alpha bar is extracted for the first time, and with that we can do a first CP test on the sigma system. And as expected, these are consistent with the standard model. I don't have very much theory to compare to because there aren't any. So I hope that this will be, let's say, spur theoreticians on to try to access or study the polarization at these CC bar resonances. Yes, the branching ratios we measured, and the systematic uncertainty is ongoing here. From the future, one can expect also the other sigma states to be analyzed. So analysis is ongoing for sigma naught decaying to a lambda and gamma. And this formalism, how it works for this scenario is a little bit different compared to the other ones, since it's an electromagnetic decay. So from this channel, what we can do is to obtain a semi-independent evaluation of alpha lambda proton pi minus. Also here one can perform a CP test for the decay sigma naught to lambda gamma, and so then this would be governed by since it's an electromagnetic decay and not weak decay, the upper limit is much lower, so 6 times 10 to the minus 12. Also, studies is ongoing for the sigma minus, which decays into a neutron pi minus, and it's antiparticle. So that can be expected from the BESS in the future. Coming to cascades then, was what has been published before. This is an inclusive analysis. So again, the goal was to measure the branching ratio and alpha psi. For exclusive analysis, you have a lower, you can expect a lower background than what's seen here. But you can see for the cascade, which is here, that the signal to background ratio is quite good. And this is the sigma 1385. Okay, so slightly larger background there. Similarly for the cascade naught, this is now the cascade naught also inclusive value, measurement, I mean, and sigma naught 1385. So if you want to measure the symmetry parameters here, it's slightly more involved because it's a two-step weak decay process. So it's instead of a 5-dimensional phase space, we have a 9-dimensional phase space given by 9 helicity angles, and there are also 8 parameters which are needed, which are used to be fixed. I'm soon finished. So we have 6 values. So 2 of these parameters are for the production, and 6 are for the decay. Many of them have never been measured before. Okay. So before I said that in the scenario when you have a J psi decaying to a lambda lambda bar, you must have a non-zero relative phase. But for this more complicated decay, it's not needed, in fact, and the precision doesn't play a very big role if the delta phi is 0 or not. You have slightly fewer terms, 56 terms compared to 5 terms in the lambda lambda bar scenario. If delta phi is non-zero, you have 72 terms. Okay. So again, here one can measure the decay parameters. Again, an independent conformation could be measured for alpha lambda. For the decay asymmetry parameters of cascade to lambda pi and lambda cascade naught to lambda pi naught, these haven't been measured directly. They have only been measured by taking the joint product and then divide out the alpha lambda proton pi minus. And so these were used previously had the old P to G value. They have to be rescaled. Okay, so it's always used to have a direct determination of the asymmetry parameters. For the weak phase angles, one hasn't measured any of any phi bar before. For phi, it has been measured by the hyper CP, and phi naught is also has been measured, but it's extremely poor. It's a very poor measurement, okay, or high error bars. For the CP test, this is the standard model prediction in the order of 10 to the minus 5. One can also do a test on comparing the CP of phi to anti-phi, and Donahue made a prediction back 30 years ago that this is actually more sensitive compared to the ACP test. Okay, but in light of these new results from BESS3, I think these have to be recalculated, these estimates. Okay, but this hasn't been measured before. So, so the best test on CP symmetry comes from the hyper CP experiment. And so this is their published result. At Beach 2008, they had preliminary results indicating CP violation, but these were never published. So it's, of course, interesting to make an independent measurement, and that's what we aim to do. So we can measure these asymmetry parameters and perform these tests, also for these cascades. And also we will be able to measure the CP of B for the first time. And what we found is that actually, due to the fact that you have so many terms, you also obtain a very good precision. So actually, so as an example, for instance, the statistical uncertainty of 5 measured by hyper-CP were made by, with a data sample of 114 million events. We can achieve the same precision with only 140,000 exclusively measured cascades. And for the neutral mode, we only need 300 to reach the PDG sensitivity. Also, what one can see if one compares even to the JPSI to lambda lambda bar, if you look at the, where is it? Okay, alpha lambda. So this is the sensitivity. So you have to divide out by a square root of n for the number of events that you expect. For this, if you look at the JPSI to cascade, you have a much better sensitivity compared to the scenario of measuring through lambda and lambda bar. So analysis is both charge and neutral cascade modes are ongoing, and it's close to my heart since I'm doing the analysis. So a summary and outlook for the future. We have presented the first complete measurement of the form factor in the time-like region. We also have the largest available data sample between 2 and 3.08 GeV. So one can expect, and analysis is ongoing, so one can expect more results from the best 3 with this regard. Concerning the asymmetry parameters, we've shown that it's possible to measure these hyperons and anti-hyperon asymmetry parameters simultaneously. And this had a strong effect for this alpha parameter, which we measured to be off compared to the PDG value. So we have a 10 billion JPSIs, which is undergoing calibration, and it's supposed to be ready in October. We have analysis ongoing for JPSI to sigmas and also for cascades. So in summary then, we have more results to expect from the best 3 collaboration in the future. And as I said, if you're interested in theory concerning hyperons, we very much would appreciate it, because right now it seems that experiment is pushing the frontier of the unknown. And so we also want theoreticians to chip in and help us with that. Thank you.
Okay, thank you very much. Interesting talk, and we already have a new result, which you, as you said, you presented here for the first time, right?
Yes, yes.
Yes. So, okay, so we have plenty of time for discussion.
It's a lambda bar production. Can you say something? Can you set some limit from your data on the time like electric dipole moment form factor?
Sorry for the?
For the electric dipole moment of the lambda.
No, no.
No, but you have CP violation, bounds on CP violation in the production, in the lambda bar production, not decay.
Yes.
But you can analyze that in terms of the EDM, in the time-like region.
Yeah.
The same as you do for the magnetic and electric form factors.
But wouldn't that require more statistics? Or do you have a reference for?
No,
I would be interested.
You are the data holder.
Actually, maybe it's a bit related question. So you assume that the polarization is normal to the scattering plane.
Yes, exactly.
Which is certainly true if parity is conserved. But if parity is violated, the polarization is not necessarily orthogonal to scattering plane. So maybe it's possible to take this effect also into account when processing the data. Or maybe again the statistics is not
No,
sufficient.
it's not. I mean, 555 events. What was checked in this lambda bar 2.396 was if I mean, this is assuming just single photon exchange. One can also assume other, I mean, higher order processes involved, and then one would expect to see an asymmetry in the number of events as a function of cosine theta. And this was tested, and it's consistent with 0. So it's for the two-photon process, we don't see any significant contribution. So it would mostly be
this is
one virtual
you discussed the electromagnetic correction, but if there is a violation of.
But if you have a electric dipole moment-like structure,
exactly. This is what.
Single photon exchange.
Yeah, it's another source. There are two sources of some asymmetries, T-violating asymmetries. It's either higher orders of parity CP conservant theory or CP violation. The question is, what is it numerically? Maybe numerically the effect is still, but
that's
maybe it's because
that I don't know.
And you have higher statistics, right? So maybe it's possible to include this. Yes.
Yeah. So 555 events But for the XVIII, we have, if one wants to do something with that.
But also the XVIII region, it would be of equal interest.
Yeah, sure, definitely.
Now, you show that for supercharms, statistical accuracy will be superb. But what about systematic inaccuracy?
Well, this you mean?
Yeah.
For the now, well, of course. I mean, this is. We have no idea, of course.
Because
I mean,
if you have the systematic just the same as now.
Yeah, of course. But these don't even exist. So these are just on projected. Of course, but I agree. Yeah, but the first step is just to see just to see how close we can come to the standard model prediction if we're able to probe that. But I agree. You really have to have the systematics under control.
This became more important.
Yeah,
sure. This is the most closest possibility.
Yeah.
And just one comment. So from the point of view of who produced a polarized beam from Lyme to Hamperon, so you can see that the polarization became slightly higher than we expect.
Yes, that's good.
Okay.
Here.
Okay.
Did you try to repeat this analysis not only for XVIII decay but also for decay of psi prime? Just to study systematics at least.
So for the psi prime to lambda bar, I mean it will come eventually, but I cannot recollect if there's any. I mean it's interesting for the polarization, of course, but it hasn't been. I'm not sure if there's an analysis ongoing for that. Because there is an analysis ongoing to include this 10 to the 10, it would also make sense to include the data which is available for the psi 2s. I mean, also here we have projected that we're going to. So now there are 225 million psi 3686, but in the white paper we are aiming to collect 3 times 10 to the 9. So already from there it also makes sense to make even more precise measurements for the asymmetry parameter, and then you will definitely get the polarization term there. But as far as I know right now, there's no analysis ongoing for the psi 3686 lambda bar. But I can try to kick them to.
May I also ask you, because of good statistic, you can probably measure not only the single spin asymmetry polarization, but also the double spin asymmetry, the correlation of polarization, of polarizations of 2 lambdas, right?
At XVIII, you mean?
At XVIII, but not necessarily. Also, just when you measure form factor, you may consider the correlation of 2 polarization, which will be.
Yeah.
It will be. It will provide additional addition, because it's also related expressed in terms of form factors.
Yes.
And also there is some constraint due to positivity of density matrix. And
yes, what one could do would be from XVIII for this one, because
also for XVIII, yes.
but not for the electromagnetic. The statistics is too low for
too low, yes.
Too low. But here we have 16 moments which can be used, and so some of them can be also sensitive to other polarizations. So if, for instance, okay, if one sees a deviation between the fit results and the data points, then you have to have either some correction factor which can be due to extra polarization or not. But for these the electromagnetic form factors, the statistics is too low.
Also concerning your new results, I guess slide number 40 or 40?
Yeah, 40 degrees, 42.3 degrees.
No, I mean your new results concerning the decay of sigma, right?
Sigma, yes.
I think it's because your result for just alpha 0 is even closer to 1.
Yeah.
Right. Previous result, and your result for alpha bar 0 somehow deviates, but it's still compatible to 1, right?
Yeah. Yes.
By the way, do you have the explanation why it started to deviate from 1? Why? Because in your analysis you allowed both alpha, which is lower than 1, and higher than 1, right? You allowed this. So do you have explanation, any hint why statistical fluctuation led to decrease of alpha 0 or alpha bar 0? Or it's difficult to say? It's just the result of analysis.
Yeah, it's a result. I mean, one thing is also the fact that these are really close to 1, so it makes it
absolutely
makes it more difficult.
Statistics you allow
yeah.
it to be also higher, right?
We also tested to do it to constrain by a sinus function, so have a sinus delta would equal to alpha. Okay, so another idea was to see if one can constrain. I mean, if one can get a more precise value using a delta, the delta parameter, which is sinus, but then one wouldn't get that. So I think it's just a matter of statistics.
And concerning your result, your new measurement, just for lambda decay, you get the significantly higher values, right, for alpha than previous.
Yes.
All previous, and this would mean that basically all the measurements of lambda polarization
yes.
Are wrong by like 10%, right? So
yeah, 20%.
We should decrease all the results of lambda polarization.
Yeah. So this is given by this figure here. This is the value, and then you shift the wheel, and then
also in particular, for example, in lambda polarization in heavy ion collisions, which we will discuss also there.
Yeah.
By the way, you can net also, so everywhere. Okay, so if there are no more questions, I don't see. Let us thank the speaker again.
Thank you.
And the next speaker is Rumen Senov from Joint Institute, and he will start the discussion of spin program at NICA, SPD project.
I'll try to. Good morning, everybody. Thanks to organizers for inviting me to give this talk to you. And I'll try to present to you our spin physics program in the Joint Institute for Nuclear Research, especially at the new accelerator that is under construction now in the Laboratory of High Energy Physics. And this accelerator follows a long tradition in the Laboratory of High Energy Physics that started with the synchrophasotron in 1957, then continued by the nucleotron, who was the first superconducting accelerator of heavy ions. And now we are building, in addition to this nucleotron, a collider rings that will collide heavy ions and polarized protons and deuterons. NICA stands for nucleotron-based ion collider facility, and is a flagship project here for a few $100 million. And the main tasks for this accelerator will be study of hot and dense baryonic matter. And for heavy ions, we will have ions up to gold with energy per nucleon from 4 to 11 GeV, with luminosity 10 to 27, hopefully, and for polarized particles with the center of mass energy up to 27 GeV and luminosity up to 10 to 32, or even in some scenarios higher. So now we have this chain, so ion source, linear accelerator, nucleotron, and so experiments inside the nucleotron vacuum tube or in fixed target area. And we aim at building a new chain here, source for heavy ions and heavy ion linear accelerator, booster to reach the desired luminosity, and then injecting to a nucleotron, and then we will have two collider rings with two interactions points where two detectors will be positioned. So in red here is what has to be constructed. In blue is what is already available. And those three detectors stay here. So the baryonic matter at the nucleotron is fixed target experiment at extracted heavy ion beam. And it is already in operation, and we expect first results from this experiment. The other detector, so-called multipurpose detector, will study heavy ion collisions up to gold by gold. And the third one, which we are most interested of, is the spin physics detector that will be put in the south interaction point, and will study interaction of polarized protons and deuterons that should be available in the rings. So, civil construction is in good shape, with some delay of a few months. So this is April 9th this year. You can see the rings here. And this is a few days ago. If you are interested, you could follow, live in, so the construction day by day at this website. So, major milestones as presented by our director and project leader Vladimir Kikilidze last year. You see here what is most interesting for the users is that the MPD will start around 2021 with the collider, and the SPD detector could start in 2025 at earliest. So that was a year ago. Now more detailed schedule for the accelerator given by Sergei Kostramin at the PAC meeting this June. So says to us that the collider with beams should be ready around January 2022. So first beams there in this region. So why do we do all this? What do we want to study? This is the main question. And First, we have seen this picture many times, I'm sure. We like to study heavy ion collisions, because they give us approach to so-called quark-gluon phase of the nuclear matter, and we believe that such kind of state existed few microseconds or even earlier after the Big Bang. And also it's an interesting thing to understand the behavior of the nuclear matter under extreme conditions. So at Nika, in those energies I've shown you, so we could reach region in the phase space diagram of the baryonic matter that is not reachable by other experiments. Somewhere here, this is net baryonic density, and this is the temperature. The high energy experiments, that they are somewhere here. They do not have access to this region because of the high temperature, high energy of the collisions. And we could study here the transition between the confined and deconfined state of the matter. So this is the motivation for the heavy ion program. And a bit more detailed account is given here. So the bulk properties, equation of state, modification of hadron properties inside the nuclear matter, deconfinement, phase transitions, QCD critical point. If we are lucky, it could be within reach of Nika accelerator. Strangeness in nuclear matter that gives us a signal for the quark-gluon state of the baryonic matter, and so on. So here is just where we will be staying with our accelerator. This is the energy region of maximal baryonic density. This is our competitor star in Brookhaven, and the BEC stays for beam energy scan. They want to go down with the energy just to enter this region, but that will be with 3 orders magnitude, at least less luminosity, and we will be, I think, in very good position to study what we want to study here. The other competitor or friend, because we are building magnets for them, is the FAIR facility in Darmstadt, and their CIS-100 will have this energy, some up to here, with a bit higher, not a bit, but much higher luminosity, because this is fixed target machine, so experiment. So, and this is all for the heavy ions, and this is not what we are going to talk about today, because what we are interested in is spin physics. And you know this famous picture and this famous statement by Bjorken that the polarization phenomena are often give critical test, offer critical test for theories, for many theories, and theorists do not like very much them, but I don't think this is the case for the audience here. So, what kind of polarized beams we plan to have? We will have talks, at least one talk this next session, about how that could be achieved at our accelerator. So this is those are the parameters that we expect from the collider people. And the luminosity depends on the energy, of course, and the maximum one is of the order of 2 × 10⁻32 in proton case. In the deuteron case, it will be a bit less. So main challenge here is that we will have 22 bunches, and bunch crossing will take place each 80 nanoseconds. So this is a crossing rate of 12 megahertz. And that means that the collision rate will be of the order of 3-4 megahertz, and our detector should be very fast in data taking. Polarized beams, you see here, we expect to have all possible combinations of polarizations in the rings, transverse and longitudinal, and also combinations of transverse and longitudinal polarizations in the beam. Of course, that polarized beams will be available for SPD detector and also could be available for MPD detector, and measurements could be done either there or there. But MPD is much, much slower than our detector. I will show you after, because of the other set of subsystems chosen in MPD. So, what kind of physics task we think can be attacked in this with such polarized beams? First thing is the nuclear spin structure. You know about the story of the nuclear spin. This is not the place where I have to speak or to tell you the stories and the challenges there. And we think we could say few words in that direction. Then there are many spin-dependent effects seen in the past and not explained in elastic scattering, also in exclusive hadron production. We plan to address those problems and to make significant measurements. Then spin effects in production of hadrons with high transverse momentum in interaction of vector and tensor polarized beams. Tensor polarization of deuterons will be or would be possible in our facility. Then multi-quark states and correlations, maybe charmed mesons detection, and so on. So I'll tell a few words about the spin-dependent, so the Drell-Yan processes, in fact, essentially, because for the other things there will be dedicated talks. But first, just again, picture that you have seen. When we consider proton in collinear approximation, we have only 3 structure functions that describe the distribution of quarks inside the hadrons. But when we speak about deviations from this approximation, then we should have structure functions that depend on the transverse momentum, so-called TMD, and structure functions that depend on the distribution in the transverse plane, so-called generalized pattern distributions. And also the spin puzzle of the proton is how we get this famous one half here in this equation, where this is the spin of quarks minus spin of antiquarks. This is the spin of gluons and orbital momentum. So this equation, or this, we have not yet solved. So again, by studying these functions, we could tell something about the composition of the proton spin, hopefully. So, as I said, if we have only collinear approximation or consider only collinear approximation, we need 3 pattern distribution functions. And if we introduce distribution in the transverse plane and transverse momentum distribution, we need 8 in Lydic order approximation, 8 structure functions. They are, this is a picture representing them. And our main statement is that in our experiment, we will be able to measure all these distribution functions in a single facility with minimal systematics between them. So that was never possible in the previous experiments, and we are not aware of experiments and facilities that plan to do so in the future. For measuring the spin structure, for extracting these functions, we could use different physical probes, and we think about 3 probes for the moment. This is inclusive and exclusive Drell-Yan pair production, mainly in anti-muon mode, but could be possible, I think, in electron-positron mode, but this is matter of studies now. Direct photon production, and production of J-psi in the collision of polarized protons. So, for the direct photons, there will be dedicated talk by Alexei Gushkov just after the coffee break, and for the production of J-psi, there will be dedicated talk by Igor Denisenko after the coffee break too. So I will just say more or less nothing about them, but just a few words about the Drell-Yan pair productions. So the Drell-Yan pair production is a well-known phenomenon, and often we should not often remember, but remember all the time that also Matveev, Muradian, and Tavkhelidze, independently of Drell and Yan, predicted the same process and studied it theoretically. And so the name should be Matveev, Muradian, Tavkhelidze, Drell-Yan process, but it is too long, so it's Drell-Yan for the moment. So this virtual photon can be used as a microscope to look inside the nucleon structure, and this is the cross-section here in our region after the J-psi peaks. So the cross-section is of the order of nanobarns. It's too small. It's very small, but still accessible. What has to be measured? So we need to measure different asymmetries, left-right asymmetries, and phi dependence, azimuthal angle dependence of the production rates. So you could see here kind of predictions made some time ago about the different asymmetries, and the value is of about few percent. What could we achieve? So few percent here in Sievert's functions, few percent here in Beer-Mulder's function. So this is the precision we should aim at, so few percent in asymmetries and in azimuthal dependence of the production rate. So this is a kind of comparison between the current COMPASS experiment that attacks the same problem in different way and achieved significant results there. You can see by reading these numbers that this is COMPASS, this is expected SPD, that we will have much larger coverage in the phase space here in the Feynman X and the transverse momentum, the same more or less mass region, and for 1 year, typical year, we could have 3 times more than the COMPASS data, all data of today. So in few years, we will be hopefully leaders in statistics. Those are kinematical distribution, so to show that the coverage in the phase space is much larger for SPD, from -5 to +5 in Feynman. Here, the compass is only in the forward hemisphere, and and a bit larger coverage also in the transverse momentum phase space. So, what could we achieve even for unpolarized Drell-Yan production? This is a Na10 results. So what has been observed is that in the collinear approximation, so the collinear approximation does not hold, and experimentally large values of these parameters have been observed, and violation of the Lamb-Tank relation, this famous relation, and those are their data, and here with the points, we show the available, so the statistical uncertainty that we expect. This statistical uncertainty is within the point size. So this is what Na10 measured, and this is what we expect to be able to measure. So you see that we are in good shape to at least to confirm their results and to go further. Prompt photon production, just an introduction. They give access to gluon distributions, distributions inside the nucleon, because this is just gluon compton scattering and for antiquark annihilation, two processes, and so Compton scattering dominates. The cross-section in our region is of about 1 microbarn. And they give access, as I said, to gluon distribution functions, Sieverts functions for gluons, and gluon polarization if we use longitudinally polarized beams. So for that, Alexei will tell you just after the coffee break. Expected asymmetries are shown here, again of the order of percent, few percents, 10%, something like that. Germanium production, Igor Denisenko will talk about that. Two mechanisms are considered theoretically: gluon quark annihilation and gluon fusion. There are problems in theoretical description of data, and also this mechanism here is important, that it gives access to gluon PDFs too. So next, asymmetries in high PT hadron production. I don't see my friend Stepan Szymanski here, but he is he advocates very strongly that we should study that, and that there are data not understood up to now why such kind of asymmetries are seen in experiments at CERN, AGS, all the experiments, also this FNIL, RIC. You see data. What we see, this is X-Feynman, and this is asymmetry in pi plus and pi minus productions. And that could be, so we could attack problems of diquarks inside the nucleons, confinement laws, nature of these spin effects, deuteron spin structure, properties of the naked interactions of nucleons with hyperons and with strange mesons, nature and properties of cold, superdense baryonic matter. There are even experimental indications that such kind of matter exists. Dilepton production puzzle in NP interaction, but this could be at the second stage of the experiment. NP interactions, because for that we need neutron tagging station. So, another interesting topic is exclusive Drell-Yan production. Some theoretical work is being done here in this laboratory, and this is first numerical result about cross-section, how it might look like. 80 picobarn is a bit low for this process, but because this is exclusive process, maybe it could be attainable, and we could reach kind of such precision, kind of such sensitivity. Then also measurement of generalized pattern distributions through vector meson production. So this is the vector meson. The cross sections is even less, twice less than the previous one. But again, because of the exclusive nature, when you detect all the particles, you could attain much better sensitivity. And here a kind of diagram that shows the physics tasks and puzzles that we could attack. And here the ways we could approach, we could attack, we could measure those things, starting from direct photons and Drell-Yans, here Drell-Yans, exclusive Drell-Yans, JPC, also tensor polarized neutron beams, and so on. So this just shows the rich physics program and rich means that we have to do this program. What in fact we will have, this is a simulation by PTA6 about minimum biased events. So you see protons we should measure with this in this angle and with such energy gammas, protons, pi plus, pi minus, and this is the cross section. This is about 40 millibarn here, of which 30 is the inclusive cross section. That gives requirements to our detector, so close to 4 pi geometrical acceptance, high precision vertex detector, high precision central tracker, good particle ID, efficient muon range system to detect muons, good electromagnetic calorimeter, low material budget, and fast DAQ system. And also we plan to make it modular and with easy access to the elements and also reconfigurable. It will be, as I told you, at the south interaction point. So the building is almost ready. And the idea, this is a preliminary idea how it might look like, is like this. So we have ion, so the tube here, where beams collide. Then you have inner tracker or vertex detector. Then you have a magnetic system inside it, central tracker. I will tell a few words about the magnetic system. PID system, presumably RPCs and supplemented with other detectors, because only RPCs and time of flight does not do the job in the whole phase space. Electromagnetic calorimeter and muon system here for detecting and selecting muons. About 1,800 tons, but we should decrease this at least by 30% because otherwise it will sink down in our sense here in Dubna. And dimensions is here 9 meter by 7 meter diameter. About the magnetic system, one of our baseline options is a hybrid magnetic system. So toroidal coils and field in the center and two pseudo-solenoid-like coils in the end caps. This system gives us minimal magnetic field in the interaction region, that increases the precision in vertex reconstruction first, and second, does not rotate the spins of interacting particles, so we will have the same state as in the collider ring for these particles. But this is a bit challenging and still achievable, we think. Few systems I will flash just. How much time I have? I think 5 more minutes. Thank you. So the vertex detector, we think about silicon, of course, vertex detector, but the combination of double-sided silicon strips and monolithic sensors, so-called maps, that have better resolution, so 3 layers inside of maps and maybe up to 5 outside layers by strip detectors. And the goal is few tens of micrometers resolution for the vertex reconstruction. First simulations, not very well seen here, doesn't matter. So very simple simulations could be taken as a toy model, would be considered. So with only 5 layers and this resolution of in a single detector element, single hit, gives you this vertex resolution with respect to z-axis. So the dependence here comes from the multiple scattering. So the bigger the momentum, the higher the momentum, the lesser the scattering, so better resolution. So in the interesting region after 1 GeV, it is less than 60 and reaches 20 micrometers, which is good resolution in fact. Why do we care about this resolution? 2 things. First, this will help us to suppress the background, muon background coming from decaying of pi plus and pi minuses in the detector. So by pointing to the interaction point, to the vertex, and cutting the tracks that do not point there. And also that could give us access to studying production of charmed mesons, but this is very preliminary, and we do not have still reliable Monte Carlo for the charms. But having in mind what other experiments achieve with such kind of resolution, this gives us confidence, partial confidence, that could be possible. The central tracker, we are thinking about straw tubes to use, just because the spatial resolution is very good. If we use, for example, 1 centimeter diameter straw tube, and the time, the reading of the signal is of about 100 nanoseconds, so this will give us fast enough detector to read the signal between the bench crossings. And the technology is available here in Ginner, in our institute, and also production workshops are available. So this is our baseline for the moment. With the central tracker and the vertex detector, we have made our collaboration studies of the momentum resolution for different types of magnetic systems. So one of them is the hybrid magnetic system. The other one is so-called pseudo-solenoidal magnetic system made of six coils that give you type of solenoidal magnetic field. So here the pseudo-solenoidal is with the black, this one, and the hybrid system is in blue. The red is hypothetical 1 Tesla uniform solenoidal field that is taken as ideal reference, for example. So you see that we have two choices, and the choice should be made soon. This is for 1 GeV particles, and this is momentum dependence in fixed angle at 60 degrees, just to have impression what kind of resolution we could achieve. So what could be achieved is of the order of between 1 and 1.51%, between 1 and 2%, let's say it like that. Okay, now the colorimeter, so the required energy resolution is about 10% divided by square root of E, not very high. The threshold, what is more important, should be below 100 MeV. Alexei will explain you why. And what our baseline, for example, for the moment, design is shashlik type, so-called similar to what was developed for so-called Kopio colorimeter, and that will be about 6,500 modules in kind of projected, maybe geometry not yet decided. So then further going out, this is the last thing is and the most heavy one is the range system. That is a sandwich of steel and drift tubes to just measure the muon tracks and the hadron tracks. It should provide, as you see here, good muon identification and gives kind of colorimetry together with the electromagnetic colorimeter and also additional coordinate measurements. The design anticipated is that of Panda system, and the group that develops the Panda muon system is also engaged in developing our muon system. So you could see test results at CERN with the prototype. This is a muon track, and those two are proton track and neutron. So you see that they are easily distinguishable. So DAQ could be designed as the upgraded DAQ of the COMPASS experiment, and it should cope with event rate of about 3 megahertz and 10 to 20 gigabytes per second. This is very preliminary, just for orientation, and this question should be also attack triggered or triggerless DAQ. We hope that we could manage in 5 years from now that the electronics will be further developed, so maybe triggerless DAQ could be achievable. Software and computing, of course, root. This is SPD root, a clone of MPD root, fair root, and so on and so forth. And this is one of the most important development in our collaboration. So SPD advantages, you can read here, and there is a comparison here between what could be available and is available at RIC, Phoenix, and SPD. So the most appealing thing is that measurement of all structure functions, all 8 structure functions in one experiment. No one else can do that. Collaboration institutions, we are in process of setting up collaborations, 25 so far, through all over the world, but we are growing. And the project started in 2014, sorry, and was presented here and then advertised in few DESPIN conferences, also on other conferences. In 2017, we started a new phase of the project toward the conceptual design report. This is our roadmap. So end of 2025 is the earliest date we could expect collisions inside the SPD project, SPD detector, sorry, and our detector will provide a unique opportunity to study all structure functions and give kind of good, kind of essential words in that direction. And we hope that Nikki, our godness, will help us in that, and we invite you to join our project. Thanks.
Okay, thank you for complete. Talk is open for discussion. Please. Questions?
Too early for questions.
Maybe. Yeah, just.
You show that you will measure mainly PT very high, yes? Starting from something like 4 GV and higher. Is it true? So could you go to lower PT in the Rayyan?
Yes, of course. So as low as 3 degrees multiplied by the momentum, because 3 degrees. So if you have 3 degrees tracked with angle 3 degrees, it goes out of the pipe of the beam tube. So
just because I want
down to 50 MeV, I would say.
Ah, okay, that's good. Because I want to mention that most part of this asymmetries happens at very low PT. So, and you told that your PT is typically higher than compass. So I was, I didn't know. So how low can you go? So.
Hopefully low.
Could you please back to page 29? There were some Feynman X distributions. Yeah, and in what frame? In central?
In lab frame.
Lab frame. Okay, thanks.
Yeah. In lab frame. Sorry. I wanted just to answer the previous question, which showing. No, what was not here? The distributions, minimum bias events. Yeah. So you see, 3 degrees is somewhere here. Okay.
Low enough. Okay, so if there are no more questions, so let us thank the speaker again. And now we have a coffee break, which is served just here, and we resume at 10 minutes before noon. Так. Ну, а вы сейчас председатель в этом. Да, все. Ага, добрый день. Ага. Ну, вы так, я сейчас думаю. Я лучше, может, уже пойдет? Нет, пойду уже к себе. Да?
Ну ладно, именно. А как иначе?
Закачать?
То есть закачать?
Можно самим?
А?
Как я могу? Все, она после, за обед. Я просто хочу это, не знаю, потом не найдешь это, концов.
Ну вот и спинки. Вот сюда вставить.
От Васильева привет передавать? Не, вам передавать привет от Васильева? Он сказал всем передавать.
Еще раз, что вы хотите? Посмотреть.
На какую-то страницу, вот это, что стоит. Здесь про коллаборацию я пропустил. Это вниз.
Сейчас, подождите. Это вот следующее. Вот вы были здесь? Да, вот следующее.
Кнопки вот это.
Да.
Институты, где написано.
Вот. Все хорошо, нашли? Ой. Так. Сейчас момент. Так, и что? Так, сейчас я посмотрю. Так вот.
Ну вот тут, да. Можно посмотреть, как это, если что-то испортилось?
Нет, это PDF-файл, не портится.
Ну, бывает, на самом деле.
Надо,
Все бывает.
надо очень стараться.
Да, были пару прецедентов.
Так.
Он может работать, а потом скакивает на не надо
Да.
проверять его. Вот, не синк, без спин. Попробуйте открыть, потому что флешка там что-то отругалась, когда ее вставили.
Сейчас.
Все хорошо. Спасибо.
Так, значит.
речь идет?
Вот это, да.
Да? И почему А, а не М?
Это Михаил, это Михаил, а это Анатолий.
А.
Потому что Филатов. Спасибо. Поставил сюда, да? А тут оно записано как Кондратенко. PDF. Расправились.
Dear colleagues, please take your seats and stop talking to each other. We are continuing our session, and I give the floor to Alexei Guskov, who is going to tell us about the prompt photon production and detection in SPD. 40 minutes.
Okay, can you hear me? I hope yes. Okay, good morning, dear colleagues. I would like to tell you about planar physics with prompt photons at SPD detector. We remember that gluons together with quarks are the main contributors to the properties of protons. As for the proton mass, the importance of gluon contribution is well known, it's obvious, it's well proven. As for the gluon contribution to the proton spin, situation is much more complex, so I would like to remind you the matter of the spin crisis. Spins of quarks, valence, and C are responsible for about 1/3 of the proton spin. Gluon contribution is known with quite large experimental uncertainty, but it's roughly zero, okay, let's say plus minus 10%. So it means that the residual contribution should come from the orbital moments of quarks and gluons. And on one hand, there is no strong, solid experimental data which can be used to separation of contribution of orbital moments of quarks and gluons. And on the other hand, they are interconnected by quite complex way, even from theoretical point of view. So that means that study of gluon content of proton is still a hot topic of spin physics. So how we can access gluons inside proton? The most direct way is the study the production of prompt photons via the reaction of gluon-Compton scattering. So you have quark and gluon in the initial state and quark and photon in the final state. So from theoretical point of view, that's very simple to treat the results of such experimental studies. So the diagram is simple. It could be calculated directly from QCD in the leading, next to leading order with infinite precision as we want. But from experimental point of view, situation is not so simple because we have quite a hard background, and we will discuss it later. So the another way to access gluon content in proton at our energies I mean SPD energies, low energies where we don't have jets and so on. So the another way is the production of heavy quarkonia, first of all heavy charmonia, and the simplest case is the production of J-psi via gluon-gluon fusion. Here we have nice experimental conditions. J-psi produce a very sharp experimental signal, but it's a bit not trivial to treat the results of such measurements from theoretical point of view because, yeah, no problem to calculate the diagram for CC bar production, but then we need to involve some effective models to describe probability for CC bar going to the J-psi. So it's model-dependent treatment. And the third way is the open charm production. So like in previous case, like in case of charmonia, we also have CC bar in the final state, but they not go to charmonium state, but goes into pairs of D mesons or charm baryons and so on. So it's quite simply to treat such a production from theoretical point of view, but we really should have excellent experimental setup with
quite sophisticated vertex detector to be able to reconstruct secondary vertices of d mesons and charmed baryons decay. So otherwise we don't have chance to distinguish signal over the background. So in my talk, I will speak only about production of prompt photons, and JPSI production will be covered by the next talk by Igor Denisenko. So here you see a very general scheme of photons production in hadronic collisions. So we see that we have hard photons, which can be subdivided into the prompt photons, the photons produced exactly in hard interaction, hard scattering of partons, and fragmentation photons that are produced by quarks and gluons during their hadronization. So then we have a lot of different classes of photons which are important only for nuclei collision. So in proton-proton collision, we simply can neglect all these contributions, and only the decay photons are important for us, and that's our main background, which we will discuss later. Here you see two main diagrams contributing to production of prompt photons in the leading order. So as I said, the main is the gluon Compton scattering, that's our signal. And another contribution is coming from QQ bar annihilation into gluon and photon. So here you see the expressions for the cross sections of these processes on the partonic level. And here you see how their contribution to the total cross-section of inclusive prompt photon production in proton-proton collision for two processes as a function of square root of S. And you see that in a wide range, gluon Compton scattering dominates over QQ bar annihilation. So we know the next two leading order contributions, they also can be calculated. So from theoretical point of view, everything is simple. So, and please pay attention that the cross-section, so this cross-section is for PT above 1 GeV, and you see that this cross-section, even at our energy scale, Nika energy scale, is quite high. So it's order of hundreds nanobarns. So it's about 2 orders of magnitude higher than the Brillouin cross-section, or about one order of magnitude higher than the JPSI production cross-section. So as for fragmentation photons, so you see schematic diagrams for their production. In this blob, the splitting function should be included. I don't have any numerical estimations for exactly our energy scale, but there is nice plot for LHC and energy. So you see the contribution of gluon Compton scattering, the QQ bar annihilation, and fragmentation photons. So you see the typical contribution is from 10 to 15%, even at higher energies. So at our energies, it should be even lower. And probably we will know a bit more about fragmentation photons on Wednesday from talk which will be given by Alexandra Shepilova. So SPD is not the first experiment that wants to study prompt photons at low energies. So in the table you see the list of previous experiments in our energy ranges. So the type of beam particles, targets, the square root of S, and kinematic range. What is important, what I would like to emphasize? First of all, practically all of them were done more than 20 years ago. So I cannot say that that's modern experiments. Another thing is that all of them are the fixed target experiments. And the third thing, only one of them used polarized proton beam to study some spin effect. I will tell a bit more about this experiment later. So, and on the plot you see the kinematic range in terms of pseudo-rapidity, or rapidity for photon is the same, and PT normalized to square root of S, double PT normalized to square root of S, just to be able to compare the experiments with different value of square root of S. So, and you see the kinematic ranges covered by different experiments, and also you see schematically the range which could be covered by SPD. So what is the nature of these limitations for kinematic range? For limitations in rapidity, situation is very simple. It's just geometrical acceptance of the fixed target setups. So just angular limitation. To understand the nature of the limitation on the lower limit on the PT or XT, we need to come to discussion of our background. So our main background is the background from decay of secondary hadrons, pions and eta mesons, first of all. On the left plot, you see the PT distribution for prompt photons produced in the gluon compton scattering and for decay photons, for minimum bias photons. So it's a typical plot for our square root of S. And what is important? It's important to understand that in the full range, our background dominates over signal. We cannot change it. But for quite high PT, basing on pi zero reconstruction, basing on the Monte Carlo, we can quite precisely subtract this background. For low PT, so where background over signal is more than 3 orders of magnitude, we have no chance. So the lower limit on the PT is not some sharp limit, it's just the value of PT where your accuracy is 100%, where your total error is 100%. Typically for, so you see these limits in terms of PT normalized to square root of S, but in terms of PT, its typical values are from 2 to 4 GV over C. So below 2 GV over C, no chance. So for SPD, we assumed here 3 GV as a lower limit. So, and on the left plot, you see the relative contributions of photons from different sources. So the main source is pi zero, then eta mesons, and all others, like eta prime, omega, and so on. Here you see the typical results of previous experiments. So that's Na3. So you see the PT, the measured PT, cross-sections as a function of PT in comparison with theory. And on the small embedded plot, you see the data minus theory normalized to theoretical prediction. So, and you see that, unfortunately, there is no good agreement. And such situation is typical. So you see another experiment. So agreement is a bit better, but again, you see some slopes in both cases. And the most illustrative is this general plot where the data over theoretical prediction is plotted as a function of xt, so PT normalized over square root of S, for the experiments, not only the fixed target experiments at small energies, but also for collider experiments at relatively high square root of S. So unfortunately, there is no experimental points from LHC experiments because this plot is probably 15 years old, but so you see D0, CDF, Phoenix, and so on. So what we can see? We can see that for small xt, so for collider experiments at high square root of s, the agreement not perfect, but more or less okay. But for low energy experiments, mainly fixed target experiments, so situation is completely different. So you see these strange slopes. So at least for 5 experiments, we see these slopes. And yeah, and you see the kinematic range, the range of xt, which can be covered by SPD. And we can conclude that even unpolarized measurements of the prompt photon production cross-section is very interesting, even now, even unpolarized measurement. Yeah, and it's important to emphasize also, as I said, all the previous experiments at our energy scale were the fixed target experiments. And the lowest energy which was achieved in the collider experiments in observation of prompt photon production is 63 GeV for ISR. So you see the typical detector with 2 colorimeters. So the measured PT spectrum of prompt photons, the table with analysis of the source of secondary of background photons, and also RIG at RIG, the experiments were down to 62 and 4 GeV. So nobody tried to look at prompt photons in the collider mode below this energy. So from this point of view, SPD is completely unique. I should also mention the contribution of diagrams with 2 photons in the final state to the production of prompt photons. So of course here we have 2 electromagnetic vertices, so the cross-section is 2 orders of magnitude lower than for gluon-Compton scattering. But on the other point of view, the signature of such events is quite sharp. So such events were observed also in many experiments at higher energy, at our energy scale. But the signature is quite clear because the invariant mass could be quite high. So you see it's not on the level of pi0 mass, it's a few GeV. So that also can be checked at SPD. A bit more kinematics. So again, you see the occupancy of phase space in terms of rapidity and PT for square root of s 26 GeV. So of course, the most of our events are in the central region of the rapidity and small PT. Here you see the X-Feynman distribution versus PT. And the question is, yeah, we can touch our gluons in proton, but how small could be the X of such gluons? So we can easily calculate it from this expression. And on this plot, in color scale, you see the minimal energy of gluon from 1 proton, which can be achieved. So if in our scale, if in PT we assume that we cannot go below 3 GeV due to background, so it means that the minimal X which can be touched is about 0.05, and it corresponds to rapidity of about 1.5. So it's not photons produced at 90 degrees, but at a relatively small angle. Okay, let's come to the spin physics with prompt photons. This table was already presented by Roman, yeah, we know that to describe proton structure in the leading order in the collinear approximation, we need to involve just three parton distribution functions: the density, helicity, and transversity on the diagonal. So if we involve into consideration the transverse motion of partons inside proton, so we need to introduce 5 more functions, and two of these 8 functions are interesting for us and can be easily studied at SPD with prompt photons. So I am speaking about gluon polarization, so about helicity for gluons, and about Sievert's function for gluons. So Sievert's function describes the relation of transverse momentum of parton, polarization of parton, and polarization and inside the transversely polarized nucleon. So to access the gluon helicity function, gluon polarization, we can measure the double spin asymmetry with longitudinally polarized proton beams. So this asymmetry could be factorized like it's shown here. So that's gluon polarization. That's A1P asymmetry, which is known from the previous deep inelastic scattering experiments. So, and multiply to the asymmetry on the partonic level, which is not 1, but okay, quite close. So we can roughly estimate the order of magnitude, possible order of magnitude of this asymmetry. So for delta G over G, we have a lot of experimental points. So as I said, gluon polarization is close to 0, but with relatively high uncertainty. So it's, let's say, plus minus 0.2. So this asymmetry A1P in our for our energy range, as I said, we are definitely above 0.05 in X. So it's roughly, I don't know, 0.3. So we can estimate that in any case, this double spin asymmetry will be below 10%. So not very high, but probably something measurable. So as for gluon-Sievert's function, so as I said, gluon-Sievert's function describes the symmetry of left-right asymmetries in transverse momentum of partons in respect to the plane defined by proton momentum and proton spin. So there are a lot of theoretical models proposed to construct this Sievert's function, but at the moment we have quite uncertain limitations from experimental data from the RIG collider. So to measure it at SPD, we have to use transversely polarized proton beams, so at least one beam should be polarized. So the difference of the cross-section involves this gluon-Sievert's function. And fortunately, we have the predictions for such asymmetries practically exactly to our kinematic range. So you see square root of S is 30 GeV and PT 4 GeV. So for negative and for positive X Feynman, so the cross sections are at least on the level of a few percent, up to 10, 20%. But unfortunately, both predictions were done, again, you see, it's more than 20 years ago. So unfortunately, I'm not aware about newer calculations. I promised to come to the previous measurement with polarized proton beam in Fermilab, the experiment E704. So it's also fixed target experiment and polarized proton beam. And protons, polarized protons were used exactly from lambda decay. So, of course, beam intensity should be quite small. So you see the PT range which was covered. They have a electromagnetic colorimeter with zero bus resolution of about 10 MeV. And you see they had their statistics just less than 500 prompt photon candidates, including more than 200 of background events. And actually they measured this single spin asymmetry, so in positive and negative X Feynman, but you see the uncertainties are huge. And these curves, it seems the curves from the plot with the prediction. So the measurement was done, but okay, accuracy is not enough to conclude something. Here, I would like to mention one more problem in such measurement. In our measurement, we should take into account that our background could also be spin dependent. At least, first of all, for fragmentation photons, there are some estimations from different models, but for the Rick energies, but in our case, at low energies, all the asymmetries are usually higher. So this asymmetry for fragmentation photons could be quite different from zero. And for pi zero production, the asymmetry is well known and it's relatively high. So we need to take it into account. I also should mention the relation of physics with prompt photons and physics with low mass Drell-Yan. Because you see the diagram, gluon constant scattering for the production of prompt photons, and if we attach mu plus mu minus pi, so it's Drell-Yan pi, so the basically kinematics is the same, the cross-section is smaller, but not dramatically, especially in respect to normal Drell-Yan. In low mass Drell-Yan, yeah, 2 orders of magnitude smaller cross-section, but we don't have here so strong background from, like we have in case of prompt photons from pi zero decay. And the possibility to connect both measurements, Drell-Yan, low mass Drell-Yan, and prompt photons was investigated, unfortunately, at much higher energies in proton-antiproton collision. And you see the points, for Drell-Yan and large black points for prompt photon cross-section accordingly scaled. So, and you see that really points are at the same curve. So that's really complementary measurements. I would like to emphasize that this comparison or co-observation of prompt photon production and low mass Drell-Yan production is possible only for collider mode, because unfortunately in fixed target experiments any photon from decay of secondary hadron produces mu plus mu minus pi in the material of the target. So for fixed target it's impossible, only in the collider mode. Okay, let's come to our detector, what we have at SPD to work with prompt photons. So the detector was nicely described by Roman in previous talk. I would like to emphasize that for us is important, the main part which is important for us is the electromagnetic colorimeter. We practically don't need for internal tracking system. So we need for it, but just to distinguish in colorimeter between neutral and charged clusters. So we actually don't need precise measurement of the particle momentum. So, and of course we need vertex reconstruction, but again, we don't require infinitely small precisions on the level of microns. So you see the general idea of the measurement. So we have tracking system and colorimeter, and we need to have some coordinate detectors between the colorimeter just to be able to distinguish between neutral and charged clusters. So since our requirements to the setup are quite minimalistic, I can assume that the measurements with prompt photons could be the first stage of measurements at SPD. So as for electromagnetic colorimeter, here you see the general requirements for such colorimeter. Of course, we try to optimize these requirements according to amount of money which we can assume to spend on it. So that's why our colorimeter, it's a Shashlik type colorimeter with scintillators and LED. So you see the model of copier colorimeter with similar parameters. So the minimal energy range, the energy threshold should be definitely not higher than 100 MeV to be effective in reconstruction of pi zero, just to reduce the pi zero background for prompt photons. So then we are not very sensitive to energy resolution. So in principle, 5 divided to square root of energy would be enough. So resolution for us is important just to reject photons which are in pi zero peak. So our pi zero peak should be relatively narrow. I will show the results of simulation. So granularity, we assume 4 or 5 centimeters, it's enough. So it's, we are in the collider mode, and occupancy of colorimeter cells, so especially in the barrel part of the setup, is not very high. So it's quite improbable that both photons from pi zero decay produce just one cluster of energy deposition in the colorimeter. So relatively reasonable time resolution. So colorimeter should be able to operate in the magnetic field, and long time stability if you want to perform fine measurements of the asymmetries. So here you see the results of Monte Carlo simulation for minimum bias photons in our setup. The most interesting is two-dimensional plots. So that's Z position in the barrel versus the radius of the colorimeter multiplied to azimuthal angle. So you see the horizontal lines which correspond to the elements of our toroidal magnet. So here you see the photon energy versus the polar angle. Again, you see end caps and barrel parts. And I would say that practically all our physics is in the barrel part. And for very optimistic case, if we have fine colorimeter with fine energy resolution, so you see the typical two-photon mass spectrum with energy threshold 100 MeV and 500 MeV. So in both cases, at least in Monte Carlo, we are able to see pi zero, of course, and even eta meson, so without any preselection. As for prompt photon production, situation is very similar. So again, you see the energy of produced prompt photon versus the polar angle. So here you see the acceptance as a function of polar and azimuthal angle. So for azimuthal angle, again, you see these 8 dips from our toroidal coils. In polar angle, you see this structure from our solenoidal coils. So, and please pay attention that our magnetic system, also solenoidal coils, are inside the volume of the electromagnetic calorimeter. So, and you see the efficiency of prompt photon reconstruction as a function of PT, so distribution is more or less flat. So, main source of inefficiency is conversion of prompt photons in the material inside, in the central part of the detector. So, here we studied the main sources of the background. So, as it was already said, the main sources of the background are the decay photons, pi0, eta meson, and all others. So, first of all, you see our signal, Gluon-Compton scattering, and that's also our useless, but that's also our signal. It's prompt photons from QQ bar annihilation. So, you see the main contribution to the background from pi0 decay photons. Then we have some contribution from clusters produced by neutral hadrons, like neutrons, kaons. Then we still have quite, not really too high, but still visible background from double clusters, from overlapping of energy deposition from different particles. Then, due to inefficiency of our track reconstruction system, some charged clusters will be identified as neutral clusters, and some contribution from photons produced not in the interaction point, but somewhere in the setup. So, general strategy of background subtraction. First of all, we reconstruct all possible pi zeros. Then we know this number. We know we assume we have a well-tuned Monte Carlo simulation with very nice described material of our setup. And then we can subtract. So we know how many pi zeros we reconstruct, and we know how many photons we still misidentify. Single photons from pi zero is still in our sample of candidates. So we can subtract such photons, and this coefficient k should be determined from the Monte Carlo simulation. And I'm coming to the most interesting result which we have at the moment. So we try to estimate which accuracy, not only statistical, but also partially systematic uncertainty. So in case of prompt photons, it's practically impossible to distinguish between them. So which accuracy we can achieve. So we assumed 1 year of data taking with the nominal luminosity, 10 to the 32. Here we assumed beam polarization 100%, and we ignore all the effects, all the uncertainties related with polarization measurement and the luminosity measurement. Because we can easily take it into account just because it's just the factors in calculation of our asymmetries. So, and we assume that this factor k we can calculate from the Monte Carlo on the level of 2%, with accuracy of 2%. Now we cannot guarantee, but we assume it. So, and in this case, you see, so the accuracy which we can achieve for both for double spin and single spin asymmetries after 1 year of data taking as a function of X Feynman. So please take into account that the error bars are enlarged by the factor of 2, so actually it's about 2%. And you see the theoretical expectations for the single spin asymmetries. So what we can conclude? We can conclude that probably 2% accuracy is enough to say that asymmetry is not 0, but for precise measurement, it's not enough, so we need to perform further optimization of our setup. And just for your understanding how this accuracy depends on the cut on the minimal PT of photons which we use in our analysis. So at high PT, our accuracy dominates by the statistical uncertainty. We simply don't have data. And at low PT, accuracy is fully defined by systematic uncertainty of calculation of this factor K from the Monte Carlo. So, and you see at 3 GV, it's about 100%. So I'm coming to my summary. I hope I prove you that polarized and unpolarized physics with prompt photons at low energy scale is still actual. And the last experiments were performed in this energy range more than 20 years ago. So now we have much better theoretical understanding of the situation. We have much better experimental techniques. And at SPD, we have a good chance to repeat such measurements first time in the collider mode. So some Monte Carlo simulation was performed. So we know the main sources of the background. We understand the problems, serious problems, which should be solved. But preliminary estimation shows that such measurement could be done. And we are looking for cooperators, for theorists who can make a prediction based on the present understanding of theory for exactly our kinematic range. Thank you.
Thank you, Alexei. Questions, please. Yep. Wait.
Alexei, how do you suppose to suppress the backgrounds in case of double photon production? What are the criteria for such suppression? Are they the same as for single photon production or differ?
Frankly speaking, for double prompt photon production, we never tried to estimate the background, but I hope. So I simply even cannot say what will be the signal to background ratio. So frankly speaking, the cross-section is so small that it's not first priority task.
Okay.
I don't know.
You didn't follow, okay.
I hope at such high masses, background from uncorrelated secondary photons should not be strong. But I would propose the same idea, yes. We reconstruct everything that we can reconstruct. Then from Monte Carlo, we know how many background events we still have in our sample and try to subtract. So the main problem will be to tune our Monte Carlo according to reality.
I have myself a question. Could you go one slide back? Yeah, here. So we are speaking here about the symmetries. Do we gain information if we measure phi dependence, azimuthal dependence of production rate? This is more to theoreticals, maybe, question.
No, probably, formally, yes. But unfortunately, I would not risk to do this because, you see, to perform azimuthal measurement, you need to subdivide your sample, at least, I don't know, in at least 8, 10 bins in phi. So it means that your statistical uncertainty increases by the factor of 3. So formally, we can perform such measurement, but I'm afraid the precision will be so low that such measurements will be simply useless.
Thank you.
My question is more on detector, not on physics, but this is maybe relevant to both talks. A magnetic system, you showed this hybrid system, and I remember that it was earlier discussions which is preferable. I mean, toroid drawback was this drops in acceptance as a function of azimuthal angle. You showed it that it could be calculated, so it could be probably corrected. And the argument, previous arguments against solenoid was that it could rotate, I think, transverse spin when passing through detector. So now it's not a problem. Adding the solenoid, they don't have effect, they don't disturb this spin orientation? Or
So, okay. So, frankly speaking, this system is not the final. So we still discuss choice between the hybrid system, and Roman presented, and this a few, not real solenoid, but a few solenoidal cores, so replace just this, the toroidal part inside by two another solenoidal cores. So from some point of view, that's, we have better performance. But we still don't have final decision, because if we still want to measure the azimuthal asymmetries with Drell-Yan and spin physics, so the toroidal field should be more safe from point of possible systematics. Probably if we don't want to measure azimuthal asymmetries, from my point of view, personal point of view, so now it's not opinion of SPD group, I would prefer to have normal solenoid, or if normal solenoid is too heavy or too complex, so this quasi-solenoid consisting of 6 coils.
Still you are here in this slide. Could you give kind of guess what would be the background, so better conditions if we make our first measurements without the central magnetic system and central tracker? Yes, so empty central sector.
Yes, yes, yes. So as I said, we actually don't need for measurement of the momentum of charged particles. For us, it's important just to see that track is, and this track is connected to the cluster of energy deposition on the calorimeter, just to remove it from our consideration. So, yeah, we can proceed with the magnetic field at all.
So we could kind of Monte Carlo estimation how much better would be if we don't have the central part. Okay, more questions? If not, thanks again, Alexei. And now the next talk is by Igor Denisenko, over there. He's going to tell us about XVIII production in SPD. 30 minutes, Igor.
Good morning. As was just said, my talk is about physics with charmonia at SPD. I will cover some of the previous experimental results at energy close to SPD energy, say about models which are very essential for studies with the charmonia, and finally show just very basic simulations. Okay, so SPD has been nicely already covered, so just reminds the energy range. And our aim is spin physics, spin-dependent structure of the hadrons, and we have different tools to do this: Drell-Yan process, prompt photons, which has been just discussed, and charmonia production. And just from the basic requirements from the SPD detector, it can be found it's well suited for study of the charmonia physics, because we expect high statistics, we expect good momentum resolution. Here I compare it to the fixed target experiment. And we have open geometry, and we should be able to detect and study high subsea states, which is also quite important. So talking about XVIII production in general, we know that it's sensitive to the gluon and to quark distribution of hadrons. It has large cross-section and very distant signal. We can very precisely control background. But the problem is that to interpret results, interpretation of results is theoretically ambiguous and model dependent. And another complication is so-called feed-down contributions, that XVIII can be produced not directly in the partner interaction, but in the decay of higher produced charmonial states like high sub-C or XVIII. And in this case, XVIII can have quite different properties, somewhat different kinematic distribution, and completely different, for example, polarization. So this study is complementary to Drell-Yan for quark PDF, if it's possible, and to prompt photons if we want to study gluon PDF. And study and verification of the gypsy production mechanism would be crucial to interpret results on spin asymmetries, which we expect to measure at SPD, and also it has implication beyond SPD. It will be helpful to extract gluon distribution of mesons in the future experiments with similar CMS energies. Okay, talking about gypsy production at SPD, firstly cross-section. At 26 GeV, we expect cross-section of about 200, 250 nanobarns. Here are the results of previous experiments. That's mostly fixed target experiments. We have 4 pi coverage, and we expect about 20 million gypsy events to be produced inside gypsy or inside SPD detector during 1 year of smooth data taking. So, as I already said, study of the psi prime and high sub C is very interesting, and we expect to measure all which is possible for unpolarized case. That is cross-section, transverse momentum distribution, XF spectra, and polarization. And for the polarized observables, gypsy was suggested to probe Sievert's effect for gluons, and probably we may try to measure asymmetries related to the quark distributions. Why taking into account fin-down contribution is important? Here's the list of review table of the previous experiments. It's with comparable to SPD energies. And we can find that relative contribution of the high sub C decays to the total gypsy number is approximately 30%, which is a quite large number. And it's also interesting to know that the number of the analyzed high sub C particles was just up to several hundreds in previous experiments. Another very important thing is the ratio of the produced high sub C1 and high sub C2. They have quite close mass, so it's difficult to separate them experimentally. And here a B tells us that this ratio is approximately 1, but with significant errors. And this ratio is actually very important if we want to study some possibilities of describing the polarization puzzle. And we also have about 8–10% gypsies produced from psi prime decay. So in total, we have 40%, and we need to take everything into account. Okay, psi prime production, it was studied in the fixed target experiment previously. Its cross-section is about 15% of the one for gypsy. It has low decay fraction to mu plus to mu and mu minus. But for the psi prime, we don't have fin-down contribution, so it's much easier to analyze in much more direct test of the theoretical approaches. So if we take a typical picture of the fixed target experiment, where we have a hadronic observer just downstream the target, we see that psi prime signal is very complicated to analyze. And SPD, having good momentum resolution, we expect to be able to do this. And also at SPD, it will be possible to study gypsy with psi prime with gypsy pi plus pi minus mode, thus significantly increasing the statistics. Okay, so what is known about polarization? There are the most interesting results were obtained by E866. That's polarization given for 2 XF regions. One is below 45 and var is above. Also, there are interesting results measured by the HERA B. That's approximately 200,000 gypsy decays, and this is XF spectrum. And different markers correspond to the different reference frame where the polarization was measured. And polarization was measured also not only function of PT, but also a function of XF. It's shown here. And it's important to stress that the data collected here are very fragmentary. For example, this data and this data are not necessarily in contradiction because they obtained they were measured in the different kinematic regions. So systematic and consistent measurement of gypsy polarization in our energies would be very important. If we come to the observables with polarized beam, so the Phoenix collaboration made an attempt to measure transverse single spin asymmetries, and they reported that for positive XF, they have 3.3 significance for it to be non-zero, and this analysis was done with just 20,000 of GPSI events. So that's also area where SPD can contribute. If we want to interpret results on asymmetry, we need to know what is the contribution from gluon-gluon fusion and what is the contribution from quark-antiquark annihilation. Unfortunately, we can do this only in model-dependent way. So on the left, in one of the just most typical approach to do this at our energy is studying of the XF distribution. On the left is the plot from NS3 collaboration. These are not exactly data, but I will just say data. And contribution from gluon-gluon fusion and quark-antiquark annihilation. And they are different in shape. Gluon-gluon fusion is narrow, and quark-antiquark annihilation is wider. As the experiment E537, it was studied antiproton nuclear reaction with CMS and 15GV, but it was analyzed within the framework of the color operation model, which predicts ratio of the gluon-gluon fusion and quark annihilation. Just very small review of the models. Actually, there are two main models or group of models on the market. They come all from high energy, like Tevatron, and they almost always used in the collinear factorization. So first is color operation model. In this model, it is assumed that the cross-section of the Charmonia state production is proportional to the cross-section of production of a CC bar pair from threshold up to open charm threshold. And for this theory to have some predictive power, this proportionality coefficients I assume to be process independent. Here are the basic diagrams. It's important to stress that in this model, it assumes that color evaporates, that we sum over colors and spins, actually spins of the CC bar pair, and it doesn't make prediction for polarization. But it gives predictions for relative contribution of gluon-gluon process and quark-antiquark annihilation, which is XF distribution. It predicts CMS energy dependence, and for very high PT above, actually, that's what we can see at SPD, it can predict transverse momentum. But it was found that these factors, FH, are not actually process independent, and this is a very approximate statement. And at the same time, there is a very important consequence from this model that the ratio of the differential cross-section for different GIPs of different Charmonia states should be constant because they are basically given by the same formula. And this is not supported by data. Non-relativistic QCD. And again, we start from the collinear approximation. It's based on two conjectures. First conjecture is factorization, that to produce GPSI, we have to produce firstly CC bar pair, which is described by short distance coefficients, and then hadronization of the CC bar pair to some charmonium state is described by the long distance matrix elements. They can be in color octet or color singlet mode. And this is conjecture, and it's proven only for sufficiently high PT. And the next important thing is that there is hierarchy of these long distance matrix elements with respect to relative speed of the SiC working charmonium system. So in the end, we have double expansion in alpha strong and with respect to V. And there are indications that series might be well converged. So there's just diagrams. It really know the same as for the SAM model, and this is 2-to-2 diagrams. Just will not stop here. So ingredients are short distance coefficients, which are calculable. There are color singlet long distance matrix elements, which can be determined from Charmonia decays or from Charmonia wave function in potential models. Collected matrix elements are usually determined from the fit to the experimental data. It's almost always PT distribution. And I know just about one example when these long distance matrix elements were calculated on the latest. That's for high sub C. The model predicts XF, contribution from gluon-gluon and quark-antiquark annihilation, PT, polarization, and CMS energy dependence. This is illustrative plot. I took formulas just from older publication. So there are like complete NLO and more advanced approaches. So it's just for illustration. We have total cross-section, this is total contribution from gluon-gluon fusion. This is from gluon-gluon fusion for the GPSI. This for the high sub C2, psi prime, and the red line is quark-antiquark annihilation contribution. But I'm not saying that it's that small as it's shown here. This simply for illustration. It's important to stress that at leading order, an RQCD cannot describe experimental data, because actually a very important consequence of this factorization of an RQCD is that the long-distance matrix elements should be process independent, and it doesn't hold for leading order. Next to leading order, corrections were found to be significant. Here they're shown for the color singlet term, so this is leading order. Next to the leading order, and this is an NLO, so-called NLO star. And the same, the contribution of the next to leading order to the GPSI photo production at H1 experiment at Hero. GPSI polarization is actually very important and very non-trivial variable, because we determine long-distance matrix elements from the fits to the PT spectra, and GPSI polarization is something completely different. And from theory, it's known that it's sensitive to elementary processes of GPSI production. For it, it also found that the theory predictions vary from higher orders of the perturbation theory. And there is so-called polarization puzzle. It's that usually we observe GPSI to be unpolarized, and it's very hard to describe in theory. And it has there are some ideas why this may happen. For example, here is plot of the polarization here for the epsilon 2s and epsilon 3s, and this for epsilon 1s. So this plot shows that feed-down contribution may play a very important role here, because we don't have for epsilon 2s and epsilon 3s. And another idea suggested in this reference is that actually we may have a constellation of contribution from high sub C1 and high sub C2, and in this case we should know how many high sub C1 and high sub C2 we have. Several groups did a full NLO fit to different data sets, so this E plus, E minus collision, this is photo production, this is proton-proton PT spectra, this is proton-proton polarization. They used somewhat different assumptions. Some ignored feed-down contribution, some didn't. But from this review, the conclusion was that for the moment, no single set of the long-distance matrix elements can describe the data. And actually, there might be actually quite a lot of reasons why this happens. And it was also important observation that if we increase the lowest PT of the GPSI taken into analysis, the discrepancies decrease. So what do we expect as PD? On the right, there is a plot of the PT spectra from NA3 collaboration. So we see that we typically expect to have a PT of about 1 GeV and extend up to probably 3 or 4 GeV. And it's a very difficult region for theoretical description, because collinear factorization just fails here. It gives divergent PT spectrum. Here we should take into account KT. And to my knowledge, there are two approaches. First is parton regionalization approaches, which is expected to work in the whole PT region by Neil Vasin and Saleev. Probably it will be discussed by Vladimir Saleev the day after tomorrow. And there are also approaches of KT factorization, which can be, which can also be, to some extent, be adequate for SPD. And this is KT factorization. And it's important, these approaches, they include some resummation of the soft gluon, part of the soft gluon emission, and this notably affects the observables. Okay, this is P array, and this is Alice publication. The dots, two curves from NLO and RQCD by different groups, and the gray shaded line is P array prediction. On the right is plot by Vladimir Saleev, so the green line is P array spectrum, and the orange line is the collinear parton model. It's full NLO, so it's clear that about 1 GeV they start dramatically diverge. So this seems to be reasonable for our tasks. It's also important to mention there was some improvement of the collaboration models. They just based on the P array. And to overcome the problem of the ratio of cross-section, they just introduce some arguments why it's more reasonable to integrate from the mass of the specific Church harmonium state to the open charm threshold. And actually, they get very reasonable description of the PT, but for hadronization, they assume that TC bar pair angular and spin doesn't change in the hadronization, and actually they were not able to describe polarization of the Hirabi data, which is approximately very close to our energies. Okay, so SPD software is being actively developed, but here can show only very basic simulation. By acceptance, I would understand the fraction of the particles of interest which reach relevant detectors. So for example, if you want to reconstruct GPSI from muons, here is the momentum spectrum of muons, and we can find that in total 93% of muons reach the range system. It's because, firstly, we have approximately 400 MeV loss in the electromagnetic calorimeter, and we also have some energy loss in the coils of the toroid magnet. And also it's important to stress that here it's just coils, there is no supporting construction of these coils. And obviously in real life it will be much lower value because our range system needs to separate muons from pions, but it's something that is not like very clear for small momentum of, relatively small momentum for muons. If we talk about GPSI acceptance, it's very interesting to look at the XVIII acceptance. So we expect to have to measure XF up to values of 0.8. It's interesting because as model predict, the point where quark-anti-quark annihilation becomes equal to the gluon-gluon fusion is actually below this value. So we may have a chance to look for the difference. And we have rather smooth acceptance in PT. If we talk about acceptance of Hoi sub C, the photons almost always have energy above the threshold in the calorimeter. So if we estimate this total acceptance, it's about 80%. And of course, in real life, this will be much lower. But the thing is that we still can expect that we will be able to analyze orders of magnitudes more high sub C decays than previous experiments. Also, there are some basic generator level studies. Here, it's assumed that momentum resolution is 1% for muons. The background considered was decays of pion and cans inside some cylinder in SPD detector. And also, it makes sense to introduce some very basic cuts. And here is background estimation and two peaks from GPSI, which is where we have expect several percent background, and psi prime, which also will be a clear peak on significant background, but everything seems to be controllable. Also, as I was advocating, it's very interesting to determine how many high sub C1 and high sub C2 we have. For this purpose, here is a delta M variable is plotted, which is difference in invariant mass of the photon and two muons and invariant mass of two muons. This variable just mostly cancels effect of the resolution for muons. Here are the assumptions for the calorimeter. And we see that And we see that actually the width of this delta M for high sub C1 and high sub C2 is comparable to the mass difference between high sub C1 and high sub C2. So it can be expected that we can know how many high sub C1 and high sub C2 we have. Okay, and to summarize, Chervonia production is a very powerful probe to study hadron structure. It's program complementary to the prompt photons and Drell-Yan, and for polarized beams we can expect to be able to probe Sievert's effect, and we may have some chance to actually study something for quark, but this is very unclear yet. So we expect SPD to provide precise measurement of the transverse spin asymmetries for the GPSI, and it should be able to provide precise and systematic measurements of the production and production properties of GPSI, psi prime, and high sub C states. And this would be very important input for validation of theoretical approaches, and it will be necessary to interpret the results of the spin asymmetries. And from the point of theory, the SPD energy range is very difficult to describe, and for the moment, parton regization approach and KT factorization approaches seems to be like the only and the most adequate to describe our physics. Okay, thank you.
Thank you, Igor. We have time for questions. Yeah, just a moment.
I'm very happy that you decided to look on Chervonia, especially Chi-C 1 and 2 spaces, but just probably not the question, the comment. Probably it's better to reanalyze the electromagnetic calorimeter, because all your problem with separating these two states is just because of the calorimeter.
Yes, exactly.
So probably it's much better to stay with the better calorimeter, but to achieve this one.
Yeah, that's true.
Okay, thank you. 5 million, please. More. Okay. Yes.
Well, actually, I have a somehow related comment about Chi-C 1, and because this is can be a sensitive test of different way of taking into account transverse momentum. So in how to say, standard TMD factorizations, the gluons are on shelf, and it's not possible to produce due to so-called Landau-Young theorem, it's not possible to produce spin 1 particle. Parton regization, if momentum is taken, transverse momentum is taken into account in a different way. If gluons are off shell, it's possible. So I think it can be just interesting.
Okay, thank you for those comments. Yes.
On the page 10, we see two differential cross-sections, and the left one is not actually for proton-proton, because Na3 utilized two targets, hydrogen and platinum one.
Yeah, that's certainly true, but actually, I know the details of this analysis, but they would require like 5 or probably more minutes of this talk just to describe this. So what I wanted to show that they contribute differently to XF, so you can use XF distribution to validate your model. It's so-called hard cross-section, partonic cross-section, what's written here.
And a short question related to plot on the right. XF in central of mass system or in the lab one?
Sorry?
In XF in what frame?
Basically, for XF, there are like two definitions. One is x1 minus x2, and the other is the longitudinal momentum in the CMS frame divided by maximum momentum.
In the center of mass.
Here, yes. I suppose it's the second one in this talk.
Yeah, but it is in the lab system.
Yeah, that's
no, it's not in the lab. If x1 minus x2, it will be in the central of mass system, not the lab one.
I say there are two definitions, and some experiment actually just use different. So here it's longitudinal momentum twice divided by the square root of s.
Okay.
So, more questions? If not, thanks again, Igor. Now we jump to a different but very much related topic about dynamics and preserving polarization during the stage of acceleration inside the NIC storage rings. It will be given by Yuri Filatov. Please, Yuri.
Сейчас я перезаряжу эту штуку.
Нет, что-то не то. Перевернуть надо. Они одинаково стали. Вряд ли.
Одинаково? То есть там, где это все-таки вот так, да? Так, ну проверим. Так, вот так.
Угу. Кто-то, конечно.
Okay, 30 minutes, please.
Good afternoon. I would like to present our talk, kinematic of proton and neutron beam polarization in the transparent spin mode in the NICA collider, which was made by our team from Novosibirsk, Dubna, and MIPT Долгопрудный. Here, outline of my talk. We discuss manipulation of the beam polarization with the transparent spin mode of NICA. Discuss the issue on kinematics of proton and neutron polarization in transparent spin mode. Talk about direction of polarization at the injection place and at the location of the polarimeter. And finally, I summarize my talk. All colliders can operate in two possible modes. Usually use a distinguished spin mode, RIG, for example. In such collider, the magnetic lattice choose the unique periodic spin motion when particle moves along the closed orbit. Another possibility, use a new mode, transparent spin mode. In such collider, the magnetic element of collider influence on spin is compensated when the particle moves along closed orbit. So any spin direction repeats every particle turns. The main difference of these two modes is the possibility to manipulate the direction of spin polarization during experiment. In the distinct spin mode, the spin direction is unchanged during experiment. And the transparent spin mode, there are unique possibility to manipulate spin direction during experiments by means of small field integrals. In this region mode, we can organize spin flipping system, which is very useful for conducting experiments with polarized beams. The setup in NICA with two solenoid snakes provides three possible configurations. When snakes off, without snakes, the transparent spin mode can be realized at a discrete value of energy, which corresponds to the integer spin resonance. And to organize transparent spin mode in the all energy of NICA, we should switch on two snakes solenoidal. and the transparent spin moment will be in all range of Nika. Here in more detail, the transparent spin moment at the integer spin resonances, we only need for manipulation spin introduce small devices, so-called spin navigators, based on weak solenoids, and such field integral less than 1 Tesla meter is enough to manipulate this direction of proton and neutrons. Here the 25 energy points which correspond to spin resonances with step of approximately half GeV, and only one energy point, this one for deuterons. To manipulate this polarization in all Nika range, it's sufficient to introduce two Siberian snake. Here the proposed scheme for symmetrical solenoid installation around MPD and SPD detector. And for manipulation, we use again spin navigator systems. Such setup allows to manipulate with polarization at SPD and MPD in vertical plane of detectors, and in the arcs is polarization direction lies in the orbit plane. Here the schematic of the distributed solenoidal snakes. We can distribute solenoid in empty space of Nika, very flexible. Here 6 solenoids of 70 centimeters and 6 Tesla meter. Such solenoids allows operate with protons in the all diapason energy range of Nika, and 1/3 of 4 deuteron beams. The spin navigator can be realized in different ways, but for Nika collider, it's useful use small solenoids. Here, an example how to set up longitudinal polarization at SPD. Due to the all lattice is transparent to the spin, the polarization aligned along solenoid at place where at place of SPD. The navigator indicate. We can say the navigator indicate. Well. Indicate the direction of polarization at the place of where solenoid's location. And outside the navigator, direction is determined by magnetic field of the lattice. Here the schematic how we can achieve any direction at the SPD place. We need instead one solenoid, 2 solenoids. The first one, Phi Z1, stabilize the longitudinal polarization before the dipole. Here is an arc magnet. And the second solenoid stabilize polarization after the dipole, near SPD. Here you can see the diagram, vector diagram. For calculation, the net spin field. Such scheme allow to control the polarization in the horizontal place of SPD. If we replace dipole with vertical field by dipoles with radial field, the such navigator allows one to control polarization in vertical plane of SPD. Here, an example of proposed scheme for polarization control. As we can see, it's the scheme for manipulating with direction in the vertical schemes. we use radial magnetic field. So such spin navigators allows, in principle, have any spin direction desirable at SPD. You raise the question, what about the spin direction at the injection place and the place where polarimeter is installed? We choose three TS-mode schematics for comparison with spin kinetics, and I'll show you how the difference between them. Here the calculation for proton beams, then radial polarization is set up in SPD detectors for three TS schematic. As we can see in the place with polarimeter and in the injectors, the polarization will be lying in the plane of collider, both. For this schematic with the symmetrical location solenoidal snake around the SPD and NPT detector, after half snakes, the radial polarization become vertical and keep it value in the first arc and in second arc. So at the place of polarimeter and injection, the polarization will remain constant and vertical. Another possibility is install solenoidal by one side of the detector MPD and SPD in such way. And we have a similar situation with the first case. At the polarimeter and the injection, the polarization will lie in the collider plane. Here presented similar calculation for vertical polarization at SPD. In the first and third case, polarization will at polarimeter and injection will be vertical. And for this symmetrical case, polarization will be rotated in the horizontal plane of collider. The value will be determined by energy and depend on the angle which rotated in these two arc dipoles. For longitudinal polarization at SPD, as we can see, we have the same calculation. It's because the solenoid doesn't influence on the longitudinal direction. So the three cases, the polarization at polarimeter and injection point will be lie in the collider plane. Here, similar calculation for deuteron at the point which correspond to the integer spin resonance. And we can see that the polarization practically doesn't change from the beginning, because small anomalous value of magnetic ratio of deuterons is here practically radial, exactly vertical, and here practically longitudinal. Similar calculation for the symmetric placement of solenoids. Again, but by half snakes change radial polarization to vertical, here vertical to radial, and longitudinal remained constant, practically. Finally, we collect all calculation is in this table. Here the direction at SPD, and here direction at the injection point and the polarimeter. The same table for proton polarization. And as we can see, polarization lie almost for all cases lie in the collider plane, XZ plane. So for these cases, we should we should measure the transverse radial polarization. For the green color, polarization will be aligned along vertical direction. And we have few possibilities to make measurement of polarization. For example, a part of experiments, at time of experiments, we can align polarization along vertical polarization, and it will be vertical at any energy at polarimeter. Or we can take into account the radial projection of polarization at place of polarimeter and make polarization in such way, make measurement in such way. The issue connected with matching polarization during injection into collider solved in an easy way. Our spin navigator allows make any desirable direction, and so I can match polarization well. And finally, the kinematic of beam polarization is calculated when vertical, longitudinal, radial polarization is set in SPD detectors with different schemes of placement of snake solenoids. The results are relevant to solve the task of injection and polarimetry. Thank you.
Thank you, Yuri. We have time for questions. Yeah.
Concerning neutron, what about tensor polarization? Because when you are speaking, you are speaking about vector polarization, right, which is coupled to magnetic field. But what about tensor polarization? Is it discussed somehow? At Hermes, it's done just by using some atomic, just transition. And is there any way to get tensor polarization at Nika?
Here we discuss the vector polarization. What about tensor?
It's different because vector is P odd, and it's coupled to magnetic field, which is also P odd. Tensor is not coupled directly to magnetic field.
Может, Анатолий Михайлович может ответить, я не знаю.
Is it discussed for colliders?
Tensor polarization is only the atomic beam source.
Yeah, at Hermes, yes.
You cannot set tensor polarized particles arbitrarily in the ring.
Yeah. So this means that if it is obtained somehow, Hermes is different. Yes, it's a jet target, right? Yeah.
My question is, what you can profit for physics from tensor polarization of the beam?
Wait for his talk.
Maybe I mentioned, but just it contains tensor structure function, and now it's related also to so shear forces in nuclear. So it's interesting, and also so tensor polarization is really interesting and important.
Stepan. Wait.
I think the questions will be experimental because we had experience to using at nucleotron and synchrophasotron tensor polarized beam when we have the depolarized resonances up to 5 GeV, we have not seen any depolarization. That's why we need to take the polarized tensor with polarization and check it only. Calculations is a big problem.
So if you have it from the very beginning, then it's maybe possible to still accelerate it.
Okay, yeah.
And preserve, right?
The problem should be studied. I have much simpler question. You were speaking all the time about polarization in one of the detectors, for example, in SPD. What would be the polarization in the other one when the setup, the accelerator, is tuned to give right polarization in SPD, for example? Could that time MPD do meaningful measurements?
For MPD, yes, we can. This polarization have the proper relation by angle in the arc.
So
I can predict.
By myself, I care for SPD, of course, but maybe they could use that time for something interesting too.
Can manipulate this polarization exactly in this way at MPD.
No, I mean simultaneously.
Simultaneously, we have good direction for specific points when it's кратно to P.
Okay.
Ну давайте. But for this calculation, we choose gamma G6. So we have at SPD and MPD the same longitudinal direction.
Yeah. Okay.
And here another example. Here vertical. No.
There will be something meaningful. Okay, great. So, any more questions? If not, thank you very much indeed. So we reconvene at 3 p.m. sharp, 3 o'clock, and follow the crowd for the canteen.
Да, то есть должна сохраняться, да? То есть магнитное поле.
У нас даже мы там делали.
Есть всего 3 круга.
Коля, а ты что не загружаешь себя? Не будешь загружать?
Ну, хорошо. Так и скажу. Ну, нет, они поворачивают, да. Вектор, То есть вы действуете. Когда будет, мы займемся. Поэтому даже сегодня, то есть можно даже в течение месяца, да? Хорошо, хорошо. Да.
Она не сидит в окружении.
А это вот интересный вопрос. Это хорошо.
У нас еще есть...
Еще много чего.
Да. Настя, о чем делать?
Не, ну а сейчас, что у нас там естественных комиссий?
А как? Папочки раздавать.
Ну если кто-то...
Консультации
может, да,
говорит, что скоро все подойдут, и все будет хорошо.
Может, с перерывом, да?
Да, перерыв.
Будете докладывать, когда выкладываете сайт?
Да.
Мне пускают малину, требуют отчет. Она говорит, вы рассказываете.
Слушайте, а ты знаешь...
У меня другая материал была.
А ты знаешь...
Я на первую половину доклада положил денег.
Тут у нас который как раз идет по полиметрии, верно? И у нас сейчас 3 доклада по полиметрии, мы перебрасываем с места на место. Давай мы поставим туда Киселева,
Филатов, понятно.
свои доклады.
Филатов Будажач.
А если она подготовит столбик, мы сделаем.
Нет, доклад у нее практически готов.
Вопрос, когда его, слушай, может это завтра?
Завтра она не может.
Если ты вместо нее. Если тебе все равно когда. Давай завтра. Давай завтра, потому что использовать этого время по полиметрии. Мы уже так делали, мы уже вставили, мы ее туда уже вставили.
Она была.
Нет, она была, потом мы ее перебросили. А теперь там еще нужно одно место для доклада. И сейчас она уже там совсем напряжена. А тогда ты завтра за нее что-нибудь скажешь, и все. Окей?
Но единственное, говорю, что я придумал, что первую часть пусть Ладыгин говорит.
Ну это если ты его убедишь в этом.
Дело в том, что первую часть доклада математику курировал Ладыгин.
Я пытаюсь это выключить, но он не выключается.
Как выключать? Длительное нажатие его внизу.
Длительное.
Длительное.
Да, о том, что оно должно быть длительным, до этого я не знаю.
Ну это специально, чтобы
Давайте Настю, пусть этот докладывает, помогает докладчикам.
Настя?
Ну, потом она же появится. Давайте мы ей вот это поручим. Потому что помощь докладчикам...
Но она уже как-то робко сказала, что завтра.
Вы поняли, что если вы пользуетесь вот этой кнопкой, вот этой она красная подсвечена, то это значит, что вы выключили. Поэтому вот эти вот, зелененькие означает, что включено.
Понятно. Значит, надо, чтобы эта кнопка была черной.
Да, вот, да. Тогда будет включено.
То есть получилось так.
Сначала выключили это, а потом стали включать здесь. Нет, тогда выключали здесь, а потом
еще включили.
Да, и все равно не работает. То есть должно быть...
Ну, в общем, да.
В общем, понятно.
Да.
Все понятно, что непонятно?
Все понятно.
Ну ладно. Я сейчас буду микрофон ставить.
Ты знаешь, да, вот микрофон, в который докладчик говорит, если его сделать побольше, вот в который...
Побольше что?
Погромче, чтобы он...
Он и так громко. Так, где это?
То, что звенело-то?
Звонок. Это звонит. Вот чувствуешь эхо?
Да.
Появляется. Вот сейчас надо проверить.
Просьба Анатолия Васильевича еще увеличить звук, если это возможно.
Да, вот в который говорит председатель.
Он сказал, что уже лучше, но если можно еще, то надо еще. Вот все, говорит, что нет. Что
вот это плохие батарейки.
Да, это не те, что... Хотя они работали еще, когда я смею.
Подождите, сейчас, вот я тут настраиваю, я включу специально, чтобы это настроить. Все, оставьте меня как есть.
Пусть Анатолий Васильевич слушает,
слушайте,
пока
Анатолий
Андрей...
Васильевич, сейчас Андрей будет настраивать. Слушайте.
Да, аудитория.
Ага.
Там я все уже настроил, что мы...
Ага.
Уровень громкости, который я в интернет, это я увеличить больше не буду.
Ага. Не будет или не может?
Ну, видимо, уже надо будильник завести. Ну, я видела, как заканчивался доклад, но с первого этажа я уже не успела добежать. Смотрю, люди справляются. Ну, как хорошо. Да.
Кстати, решили, вот это получилось.
well, there is a small announcement that after this session, because today we have welcome party, it will not be a full-scale coffee break, but maybe some water, juice, beverages, a small one. And also in the room of the organizing committee, it will be our secretary, Olga. Those who just didn't yet pay fee or have some other questions may approach her just at the end of the session, roughly an hour and a half. And so just now.
Good afternoon, dear colleagues. We start session devoted to electric dipole momenta. 3 talks. The first speaker, Professor Nikolaev. Nikolai Nikolaevich. The title is given here. EDM at storage ring from JEDI COSI to SPDM.
Нормально работает, да?
35 minutes plus 5 for discussion.
Well, I shall report about the past, present, and future of the JEDI collaboration at Jülich, and the new development, which is the formation of the CPADM collaboration with participation of CERN, which may become eventually a part of the CERN activity beyond LHC. First of all, why are we interested in EDM? The reason is very simple, because of fundamental symmetries and baryogenesis. And how shall we look for EDM? It's a spin rotation in electric fields. It's very similar to rotation of the magnetic field in magnetic fields. They're basically identical in physics. And for that, you cannot place a particle in an electric field, charged particle, because it will immediately fly away. Therefore, you need storage rings. And I shall give you selected record-setting results from a unique facility, which COSI is today. And life would have been fantastic without systematic effects. And the most important systematic effect is a false EDM-like signal from the rotation of the magnetic field in unwanted magnetic fields. COSI is an all-magnetic ring. Okay? And the new techniques which have been developed at COSI are spin-tune mapping as a tool to quantify and correct for the imperfection magnetic fields. And the new development by JEDI at COSI is radio frequency resonance tune mapping as a tool to quantify and correct for the same imperfection fields. And the results obtained at COSI really make pathways to the dedicated EDM storage rings. And the important CPADM initiative is looking forward to the first ever all-electric ring for the EDM studies. And JEDI publications are available on this, sorry. Doesn't work. Huh?
Нет, вот тут есть какая-то штука.
Вот это.
Вот это сбоку. Вот он.
Сначала включи ее. Левая. Там вот это вот. Ага. Теперь нажмите. Нет? Странно.
Может, батарейка села?
Да нет,
мы только что меняли. Может.
Странно.
Странно.
А листает хотя бы?
Что?
Листает.
Сейчас зеленый. Батарейки отменил. Еще раз. А вот сейчас он подал. Вот он все.
Okay, all the JEDI publications can be found on this public website. Why EDM is really important for understanding the baryogenesis in the universe? The point is that we know the baryon density in the universe, we know the density of relic photons of the microwave background, and the observed ratio is 10 to minus 10, basically 10 to minus 9. And the standard model contains all the ingredients you need to generate baryon asymmetry out of nothing, out of pure radiation at the very early stages. And CP violation is one of the three Sakharov's criterions for baryogenesis. And in the standard model, you are failing by 9 orders in magnitude. Therefore, there must be CP violation beyond the standard model. And CP forbidden electric dipole moments are the perhaps most promising observable to look for that CP violation beyond the standard model. And there are already very good neutron EDM results, upper bounds, and there are plans to increase the sensitivity by 1 to 2 orders in magnitude. With the proton specialized dedicated rings, one is aiming at 10 to minus 29 e-centimeters. And with the neutron EDM and PDM in precursor JEDI experiments, well, you can reach perhaps 10 to minus 20 e-centimeters. And sequel to JEDI will be CPDM prototype, 30 MeV pure electric ring, which can be located either at CERN or at COSY. It's a big international effort, and 2050 plus page third yellow report is to be published pretty soon. The fundamental symmetries, fundamental symmetries and the EDM versus CMDM, it has been clarified really in 64, 65 by Okuny. I was a student, I remember learning from him. And first of all, magnetic moments are allowed by all fundamental symmetries. And the scale for in the hadronic world is set by a nuclear magneton. If we trust CPT, then EDM is parity and CP and T forbidden. In order to generate electric dipole moment, you need to pay a price of 10 to minus 7 for the parity violation and extra 10 to minus 3 for the CP violation, just judging from KDKs. Therefore, a natural scale is 10 to minus 24 e-centimeters, and it is borne out by all major models except the standard model. The standard model is exceptional because in the standard model, CP violation happens in the flavor changing sector. Therefore, EDM is a flavor neutral matrix element. Therefore, you have to pay 10 to minus 7 extra to neutralize the flavor change. Therefore, the standard model expectation is 10 to minus 31 e-centimeters. This is a summary of what we know about the current limits, electrons, muons, and tau. It's in the units i.e. centimeters. The only really interesting upper bound is for neutrons. And the goal is to reach 10 to minus 28. Most ambitious authors are claiming that. And there are atomic experiments. Some of the atomic experiments can be reinterpreted within theoretical models because it's a nuclei in terms of the neutron EDM. And they claim that its upper bound is about the same as it is here, which must be taken with a grain of pepper and salt. And with the proton EDMs, again, reinterpretation of the same results, atomic experiments gives this upper bound with the same grain of pepper and salt. And technically, in the dedicated all electric rings, you can reach 10 to minus 29. And there are no real data for neutrons as yet. Neutrons are really record holders at the moment, and next generation experiments are in the pipeline everywhere where ultra-cold neutrons are available. Important point is that isotopic properties of CP violation beyond the standard model are entirely unknown. For that reason, proton EDM, much bigger than the neutron EDM, is not excluded at all. Even if you go to the entirely isoscalar CP violation, which is a QCD-seated term, even there the theory predicts unequal proton and neutron EDMs. And if you go to a neutron, then apart from the EDM of the proton and neutron, you may get new contributions from the T-violating nuclear force, which is, again, entirely unknown entity. And really not much is known about such a P-conserving but CP-violating so-called millistrong CP violation. It is entirely beyond the standard model beast. And at COSI, there are plans of a TVL experiment on double polarized PD scattering, and the idea is published in here. Okay. Now, the Schrödinger equation in the spin physics is the so-called Frenkel, Thomas, Bargmann, Michel, Telegny equation, which for the interesting case, for the case of interest for us, looks like that. It contains, it gives the rotation of the spin. It's battery is dying, I believe. Еле видно кнопку. You have two contributions to the spin rotation. One is coming from the interaction of the magnetic dipole moment, which interacts with the external magnetic field, and motional magnetic field from the electric one. And the EDM component, it interacts with the external electric field and motional electric field coming from the Lorentz transformation. There are two pieces, and those two pieces combine into something which is absolutely familiar. It's a Lorentz force, right? In order to eliminate the background from the gigantic magnetic moment, which is 10, 15 orders in magnitude larger than the EDM, thanks. You need to eliminate first the magnetic field, and this piece, which is also interaction of the magnetic field with the motional electric field. Therefore, you go to the so-called all-electric ring for ideal for protons, and you run it as a frozen spin condition at a momentum of 700 MeV over C. Then in that case, if you inject longitudinal polarized protons, they will stay longitudinally polarized all the time. In terms of Yuri Filatov's talk, it corresponds to the K equal to 0 resonance. Then, but if you have now this piece in here, you have an interaction radial electric field, and this radial electric field provides you the confinement of protons on their orbit, and this electric field gives you rotation of the spin. Therefore, it will be entirely EDM-driven rotation in this ideal world. And the signal will be rotation of the spin upwards from the plane to the upright position, and per turn you will get a rotation angle of pi eta. And this eta for the EDM of 10 to minus 29 EDM is 10 to minus 15. Just think of it, 10 to minus 15. Huh? No, compared to MDM effect. If MDM rotation angle is unity, then EDM rotation angle is 10 to minus 15. Okay, so what you can expect, again, in the ideal ring, it's a perfect alignment of all elements, it's stable, fields are really homogeneous, and no systematics. Okay. And you have high-density beams, polarized hadron beams, large electric fields, and long spin coherence time that you can observe for a long time, the spin rotation, to build up that teeny polarization rotation to something observable. And you have 1 part per million polarimetry, which has been demonstrated quasi-experimentally. And you end up with a sensitivity of 10 to minus 29 e-centimeters for a 1-year run of the accelerator. Okay, that's very encouraging. And but that was for this ideal all-electric ring. What we have today, we have all magnetic quasi as a testing ground. Therefore, you follow the yard sale tactics. Just take what you have. And this ring contains, first of all, wind filter to rotate the spin, polarimeter. This polarimeter has already been dismantled. 2 arcs, electron cooler, second electron cooler, and somewhere in here you have also Siberian snake. COSY is all magnetic storage ring. At the moment in the world, it is a unique facility for studying spin dynamics. If you do the same analysis for COSY, then you can reach, for deuterons, 10 to minus 24 e-centimeters. Deuterons are nice because in the COSY range, you have no spin resonances because of the small. That again. I'm sorry. But COSY is an old magnetic ring. If your magnetic field were ideally vertical, then you don't have any problems. But there are horizontal imperfection magnetic fields, and they are evil because they are causing MDM rotation, which would entirely screen your EDM effect. And therefore, you need to understand how one can suppress that false MDM rotation. And the general experimental result is that magnetic MDM background can be suppressed to 10 to minus 6 level. Therefore, I take the nuclear magneton, multiply by 10 minus 6, and then you cannot do anything at COSY better than 10 to minus 20 e-centimeters. But it will be still useful to see that you can reach that because you are really learning how to deal with ultra-high precision spin dynamics, which simply has not been done before. So first, really record-breaking finding at COSY was that you can measure spin tune, which means the spin precession angle per turn to better than 10 to minus 10. It has been really experimentally demonstrated, and the reason you can do that, such an experiment, is that you are having a spin lying in the horizontal plane. You have your magnetic field, and the spin is now having precession with a spin rotation per turn, which is a gamma factor times magnetic anomaly. And it is continuously changing its direction. But now, what you have at the moment, at the beginning, is that you are putting all vertical polarized particles simultaneously on the horizontal plane. Therefore, you have a spin arrow. And now you have a continuous polarimetry. You are hitting your beam stochastically, sending particles to a polarimeter. That you keep, you have a counting rate of about 1 event per 20 revolutions of the beam, and you keep measuring that, and for each event you have a time stamp, perfect time stamp. With that time stamp you can measure your spin tune continuously, and you end up, you discover that, first of all, this spin tune is drifting, and this drift is really from cycle dependent, which shows that perhaps the hysteresis in magnets is there. And there are some other unknown reasons. Power supplies are drifting because they were never meant to work to such a precision. Therefore, you have this drift, but the central position can be really determined to 10 to minus 10 in that 100-second cycle. At the beginning, no one believes that this can be reached, but it is experimental observation. Now, you need long spin coherence time because your single revolution rotation is so weak. You start with initially all spins are aligned, and eventually you'll get from this arrow a Hitchcock, so that the average polarization of the horizontal polarization will average to 0. In order to get long coherence time, first of all, you need to use a budged beam, and you need to decrease beam emittance via electron cooling, and then you have inevitably Betatron oscillations, and which lengthen the trajectory. And this lengthening of the trajectory is causing correction to the changing the spin tune for individual particles. Therefore, now particles are, each particle is rotating with its own spin precession frequency, and that is limiting the spin coherence time. But in 1988, Ivan Koop and Yuri Shatunov invented a technique to mitigate that by sextuple families, by fine-tuning sextuple families. And this is simply an example showing that you are having now routinely 1,000-second cycles, and the spin coherence, and the spin is just decreasing by a factor of 2 during those 1,000 seconds. Therefore, it is a really working procedure. Now, again, just imagine that you don't have any magnetic imperfections. Then you can look at this BMT equation, and in the cozy ring, you'll get a spin, stable spin axis, which is tilted because of the EDM by very small angle. And now you add in that ring the RF bin filter with a magnetic field which is perfectly upright. Then in that case, you are exciting RF spin resonance because you ask for the RF frequency equal to the spin precession frequency. And this spin resonance tune shall become to the EDM effect. Therefore, you can extract EDM either from the resonance tune or from the tilt of the spin, stable spin axis. However, we live not in the ideal world, and there are magnetic imperfections. And therefore, you get here some background from the magnetic dipole moment interacting with the radial magnetic fields, and also longitudinal magnetic fields do contribute. And this resonance tune becomes a vector product of the stable spin axis times the wind filter axis. Important point is that imperfection fields, they change the spin tune. And therefore, those imperfections can be probed by complementing a ring with artificial in-plane magnetic fields. Again, the same yard cell approach, you take advantage of electron cooler drift solenoids. You can use them as an imperfection fields. And therefore, you get a spin tune mapping, and you can convert a record precision, 10 to minus 10 precision of spin tune to a tool to determine imperfections. And it has been drilled experimentally. It's a published paper. And the major point is that a theory predicts that the spin tune, two-dimensional spin tune map as a function of spin kicks in two solenoids. This S1 here, again, but battery is dying again. I'm sorry. You predict this saddle point behavior, and the tip of this saddle point corresponds to imperfections in the ring. Therefore, you can choose the solenoids to compensate those imperfections. And what has been seen experimentally is that those magnetic imperfections correspond to a tilt of the stable spin axis of the order of 3 millirads. And the direction of the spin axis can be determined to about 3 microrads. This is at 10 to minus 6 accuracy. And from that, you can conclude that you cannot, your sensitivity is limited by systematics to 10 to minus 20 e centimeters for neutrons. Now, there are 2 rotations, and you really have to solve equations of motion for a spin. And it is a stochastic, stroboscopic motion because you have a 1 spin kick from the wind filter per revolution. Between those spin kicks, the spin is precessing idly, as before. And you apply the technique, which is, sorry, no way. I'm sorry. Never give a series to any gadget. What is happening is that spin is rotating around 2 axes, and one of them is determined by the vector product of the stable spin axis and wind filter axis, and the relative phase between the spin phase and the RF phase, which you can choose at your free will. What is happening is that initially, without wind filter, my spin was simply rotating in the horizontal plane. Now, you get an upright motion, but there are 2 components. One of them is in the rotating plane around this wind filter defined axis, and the component along that axis, as usual, is conserved. And the second component is now rotating in this plane defined by those 2 axes, vertical plane. It shows that, of course, now with the RF wind filter, there is no such quantity as an invariant spin axis. It doesn't exist anymore. But this spectator component, it keeps rotating with the idle precession frequency. Therefore, you can use it as a signal for correcting for the phase shifts, etc., and to synchronizing the spin precession and RF frequency. Of course, the other component is also meddling in the affair, therefore it is not quite clear that it is the ideal solution, but it is a solution. Why it is so important? Because all the EDM experiments, they relied on what you call comagnetometry. You would like to keep controlling your magnetic field all the time. And for that reason, for instance, in the neutron EDM experiments, and the comagnetometers are using usually mercury vapor in the same vessel where you keep your ultra-cold neutrons. In storage rings, as I showed before, you have a really comagnetometry is also imperative to maintain resonance condition during those 100 seconds. For instance, in the atomic EDM experiments, because the atomic magnetic moments are so large compared to the nuclear magnetic moments, usually you can run your experiment for milliseconds only. And here you're asking for 1,000-second measurement time. And in the case of JEDI, you control the spin tune by continuous timestamp of the idle precession. And, but that wouldn't work if your spin is rotated entirely out of the horizontal plane to the vertical one. A naive suggestion is to use the spectator component of the polarization at the price of diminishing the EDM signal. There are some other techniques which are under consideration and experimental tests are planning. For instance, Alex Nass, Frank Ratman, and Jamal Slim came up with a very interesting idea to have several bunches in a ring and to have a gating of the RF wind filter signal such that one of the bunches always passing through the wind filter at a zero field. Then its polarization can be used as a comagnetometer. Who? No. Okay, then I will just skip that. And no. Of course, you really need to check that the wind filter idea works because the wind filter must provide exert zero force on the beam. And that you can look at how this is fulfilled, changing the phase, relative phase, or changing the mismatch of the electric fields. And what is important is that effects are really different for different RF harmonics and depend on the beta function. And that means that you really need to have a very good control of the beam. That you don't need, you don't like to have coaxial beams in the wind filter, and therefore, at JEDI there is a program of changing from the old beam position monitors to the new Rogowski pickups, Rogowski coil pickups. And now I'm coming to the spin resonance tune mapping. You have an ideal ring, static solenoid, and RF wind filter as a spin rotator. And you are measuring your resonance tune. And for that resonance tune, as a function, and you start rotating wind filter along its longitudinal axis. And you also add a solenoid in a ring, and just make a map of this quantity as a function of two parameters. Just rotate. And those coefficients A and B are theoretically predicted to be equal to each other, and they can be expressed in terms of the fields in the wind filter. And I'll just show the numerical simulations, assuming that EDM is really large, 10 to minus 18 centimeters, just to enhance the effect, to shorten the simulation time using the laptop. And this quantity, the resonance tune, shall show ideally a tip, sharp tip in here. And what is important here is that you start with the ideal ring without any longitudinal imperfections. And the minimum here is really at zero in this direction, and at some is an offset. And this offset exactly corresponds in simulations to the input EDM. Therefore, first of all, the longitudinal imperfection is simply just a parasitic effect, and you can kill it at your free will. And here, the accuracy to which you can determine a position of this offset corresponds to the upper bound on EDM you can impose from your experimental data. And what is shown here are other experimental data showing how the build-up rate at the beginning can be controlled by the phase, by the wind filter orientation and the solenoid. So it's really, and the curves here are theoretical expectations. So it really, we have a good understanding of how that operates. And now I'm coming to the CPEDM. CPEDM In the collaboration, I'm afraid that some of the institutes are not yet in here in this list. And what's important is that CERN is joining this effort. And that will be 30 MeV ring in the pure electric, in the pure electric option. And also you can add to the same ring a magnetic field. Then you can go up to 45 MeV. And in that case, you can realize the frozen spin option. The compensation of the MDM effect coming from the magnetic field and the electric field. Electric field also induces this motional magnetic field. And the total magnetic field, effective field, is 0. Okay, and the ring will look something like that, but I'm really running entirely short of time. There will be 4 semi-arcs, 4 straight sections, and you can run in this all-electric field clockwise and anti-clockwise beams simultaneously. And then this is just how the electric field shall look in the vacuum chamber. And here how you can realize this E plus B option. And one possibility just now what is coming is really fancy. One possibility to look for EDM and to compensate for the systematic effects is to run simultaneously two beams, clockwise and counterclockwise, which will have a crossing point here and here, and the wind filter is sitting in here. They are both running across the same wind filter, but one beam is passing at the positive field, and second beam is passing at the negative field, because you are running your wind filter at the beam frequency. Okay? And if your bunches are short, then it is really, you are realizing for this bunch a static field situation. It is always seeing one and the same static electric field. And the same is true for the second beam. And simple algebra shows that in that case, the spin tunes for the clockwise and anti-clockwise shall differ, and the difference is proportional to the EDM. And this way, one can reach, in this all-electric option, a sensitivity to the EDM in the 1 year run of 10 to minus 24 centimeters, which is already becoming interesting from the point of view of theoretical models. Okay, really, commanditometry is really becoming one of the most important issues, and one of the important ideas is a co-ops spin wheel idea, but I believe that Yuri Senchev shall talk about that more. I'm really short of time now. This I simply skip. And conclusions. JEDI. We have a good understanding of the hitherto unexplored ultra-high precision spin dynamics. And JEDI at COSY precursor RF in-field experiment on the neutron EDM is scheduled for the next year. And the sensitivity in that experiment will be about 10 to minus 20 centimeters, which is, of course, a far cry from the theoretical estimates, but it is a good, will be good demonstration of our understanding of the spin dynamics. And if the CPDM shall come into life, it will give much more insight into possible systematic effects from both all-electric and hybrid E cross B options. And even non-magic all-electric ring will boost tremendously a sensitivity to the proton EDM, and much more theoretical scrutiny of the relevant spin dynamics is called upon. Okay, thank you very much.
for strong vegetation in spite of huge technical problems.
Yeah, you know.
Questions, please.
Of course, the correction for Earth rotation should be taken.
Of course, no. What in that 250 page document, there is a 5-page entry which is called gravity as a standard candle for EDM. Yeah. I simply didn't have time to speak about that, but what is happening is that you have a gravity, and the particles would like to fall on Earth. But in none of the rings constructed so far, it didn't happen. Why? Because there is a little tilt, absolutely invisible little tilt of the trajectory, such that the focusing fields are taking care of the effect. But in these all electric fields, where you only need the pure radial electric fields, this can only be done by the focusing fields which are vertical. And the vertical electric field shall generate radial magnetic motional field. And that radial magnetic motional field shall couple to MDM, and which will immediately become gigantic effect. And when you go to sensitivity of about 10 to minus 26 E centimeters, 27, minus 10 to minus 27 E centimeters, then the gravity effect starts taking over the expected EDM effect, but it can be eliminated by combining the effects for the clockwise and anti-clockwise.
But this is gravity, but also Earth rotation is also...
But Earth rotation is also in there, yeah. But yeah.
Thank you. Other questions? Yeah.
Do you have any idea why the up and down quarks would have different symmetry properties?
No, they don't. They have the same symmetry properties, but the point is that they have different charges. Therefore, the isospin properties of the EDM.
Yeah, but isospin is the same.
Yeah, but isospin is the same, but the projection of the isospin for the proton neutron is different, and the charges are different. For that reason, the EDMs of the proton and neutron are inevitably different. There is no way out of that. Therefore, you absolutely need to measure proton and neutron and EDM to be happy.
In other words, this question, why EDM for proton and neutron are different? Due to meson exchange currents?
No. Just simply, even you have an absolutely isoscalar interaction. Photon knows about the charge of a particle. And the charges of the proton and neutron are different. So that's it. It's very simple, like that.
No other questions. I would like to ask you, what will happen if you will measure proton EDM and obtain exactly 0 at the level 10 to minus 29? What is the impact for baryonic genetics?
Okay, I would say that in the supersymmetric models, you have so many parameters. You know, you are buying beauty at the expense of the very large number of parameters. And therefore, you can always fine-tune those parameters and get very strong suppression for protons. And perhaps you see something for neutrons, which would be somewhat unnatural. But I would like to remind one good story from our textbooks. You have in the standard model, there are delta I 1/2 and delta I 3/2 transitions, and they are both present in the bare Hamiltonian with about equal strengths. But k plus 2 pi plus pi 0 decay amplitude is by a factor of 20 smaller than k0 to pi plus pi minus amplitude. And that factor of 20 has never been properly explained up to now.
Thank you very much, Neil. Next speaker, Professor Senchev.
Не уносили.
Ага. Okay.
frequency domain method of neutron electric dipole moment.
Тут указка запасная.
Я понял, да. Где она запасная-то? Вот здесь?
Тут лежит, да.
Куда жать?
Вот это.
Все понял. Okay. If I would know that Kolya Nikolai will speak about so detail about physics, I would never prepare my additional slide which dedicated standard model, so on, because Nikolai said absolutely everything beautiful about that. And now, definitely, only I said to you that maybe remind you that EDM neutron at present has experimental result on the level -26, and proton on the level only -25, and so on, so on. And therefore, EDM opens the door for new physics. I'm a theoretical physicist, therefore I will speak about only spin orbital motion, which we investigate in order to study possibility to measure EDM in accelerator. In accelerator, in my long accelerator life, I first met such situation when accelerator play a role of detector. This experiment, in principle, don't require anything except accelerator itself. Detector only polarimeter and nothing else. By the way, it's very positive, for instance, for NICA, which later I will touch a little bit about possibility to make such experiment on NICA, where we don't need SPD anything, just only colorimeter, or only polarimeter. This is cooler synchrotron COSI. I don't know, Kolya Nikolai a little bit touch of that, but nevertheless, I will speak again. You see that this is 180 meter synchrotron, which has maximum energy on this region, circumference, something about that. Electron cooler installed here, it's very important for us, and stochastic cooler as well, because we use this one for measure decreasing emittance in order to increase increase life of polarization. So, in principle, there are at present two concepts of ring proton in deuterium. And frozen spin method, what Nikolai mentioned already, resonance methods, which detail discussed by Nikolai as well. Now, a little bit again, I prepare this slide. You see that the principal spin of quantum value, of course, but in classical physics, representation of spin means expectation value of quantum mechanical spin operator. And therefore, we use so-called Thomas Bergman-Michel-Deligne equation for EDM. We call TBMT equation. This is right in this form. And of course, EDM figure in this place. And in order to split out EDM effect, we have to somehow remove this term. And therefore, using pure electrostatic ring, we remove magnetic component fully, and then we have only rotation due to EDM only. But this effect, this is method we suggested by BNL, and we call frozen spin method. Frozen spin method very good for the for proton because it's an electrostatic ring and easy to remove magnetic component. At the same time, for deuteron ring looks differently. Since we have magnetic field in any case, because anomalous magnetic moment, this value equal already negative, therefore this term cannot be equal 0. Therefore, we require for the ring equipment equal component, full component equal 0 for both in magnetic electric field together. This is condition which couple magnetic electric field, and here Kolya speak about that. Therefore, a little bit escape. Now, most important problem in the ring EDM search. First of all, there are two conceptions of spin lattice. Lattice mean accelerator structure on our language. Frozen and quasi-frozen spin. Frozen, it's clear what is that. But additionally to that, we develop idea on quasi-frozen spin. I a little bit touch of that a little bit later. Then the next component, spin decoherence, and the most difficult problem, systematic error, as usually. Really, at present, there are frozen spin concept and quasi-frozen spin concept. What means frozen? Frozen, it means that when spin rotated the same frequency as momentum. So spin always direct along momentum. And this is condition described as mentioned before. But it's possible to use concept for deuteron when we use G factor, very small value in comparison with for proton, 10 times less. And then spin rotate very small value on the arc. And then we allow to rotate spin in the arc, not keep alone momentum, but then on the stray section we correct spin in positive side. This is concept we call quasi-frozen spin. It means that not fully, but quasi-frozen. For what reason we developed this idea? Because, for instance, if you take NICA ring collider, it has special arc, and it's not dedicated for EDM ring. It's a usual machine for usual purpose, so on so on. Nevertheless, if we use deuteron, and we could use this concept quasi-frozen and install spin rotator on stray section, which compensate rotation on the arc, and due to this fact, we get quasi-frozen concept. Spin, in principle, will rotate for with frequency equals 0 in average, but not instantaneously. This is frozen spin. We calculate this lattice, approximated just for your imagination how it looks pure dedicated ring. For EDM, it's around 145 meter. For the quasi-frozen concept, we use 165 meter. But quasi-frozen spin concept has two options. One of the options when on the stray section we install electrical deflector with a negative curvature of deflector, and due to this one we could compensate rotation spin on the band magnet. But then later we took a little bit different concept when instead such shape we create usual machine with straight section, where instead purely electrostatic machine, it's electrostatic together with magnetic field. Magnetic field, very small one, something about 80 millitesla, and it's possible to use permanent magnet. It's very simple without any oil, coil, electrical, so complication, and this is device very simple. The next problem is decoherence. No, decoherence is a simple phenomena which considered Koля already mentioned. It was met in Novosibirsk, and people consider this phenomena when they investigate effect of decoherence of spin. Really, it's clear that in the bunch we have many particles. A particle has different energy. This is energy provide spread of rotation spin in the time, and after some period total vector equals 0, which we call zero polarization, full degradation of polarization. And we call time during what we investigate call spin coherence time. This phenomena depend on spin orbit, and we investigate very deeply this effect, and could principle image how to install what kind of sextupole where in what place, so on how to compensate. In theoretically principle possible to compensate up to 0, but in real life it's not so easy. Then systematic error is the most important. Systematic error coming from many sources. One of them imperfection. Imperfection, the next one, describe picture. For instance, we have no misalignment, no anything, but then the ring where element, for instance, band magnet or deflector or quadruple or anything, has some not ideal installation in the space, 3D space. You immediately get projection for all the magnetic and electric field, which create rotation, spin in plane perpendicular of axis of polarization. Then sometimes, and this one create so-called fake EDM signal. This is fake EDM signal should be equal maximum minimized, otherwise we could not recognize where EDM, where other one. Koля already mentioned that for this one, BNL laboratory developing this idea additionally to the frozen spin concept. They suggest to remove this one using clockwise and counterclockwise beam when particle two beam rotated simultaneously in one direction, in another direction. And in that case, measuring spin oscillation in the time, and we could separate EDM signal from MDM plus EDM. At present, from my point of view, not taking account RF flipper, it's not touch of this method because Koля already said about advantage, disadvantage of this method. But speaking about method which we developed, there are three methods. It's BNL, it's original method, then Cope-Will method, and frequency domain method. In order to answer what the method better, what method has what kind of advantage, disadvantage, we investigate first of all what do this method measures. Then method of decoherence suppression mechanism and implementation of reverse field, clockwise, counterclockwise field. Really for deuteron machine, for proton machine, we're using pure electrostatic machine, and motion of clockwise and counterclockwise doesn't depend on polarity of deflector. For the deuteron, we have to change polarity of magnetic field, and how to change. If you say me that 1.1 number Tesla, then we change polarity, we could not recover the same field of in magnet. Nobody guarantee, and this is a rock could exceed significantly EDM. Therefore, this problem very important. Now let's speak about first of all BNL, because this is original method. In BNL measure amplitude. If we have spin, they measure a vertical component of spin. If spin orientated longitudinally, really it has a vertical polarization, because in principle spin should rotate around vertical axis, but frequency rotation equal frequency of momentum. Therefore, we consider like a longitudinal polarization. And simultaneously, they try to measure SY component of spin in the time for 1,000 seconds. So they measure amplitude. This amplitude consists of many components of spin precession, and Y and Z and radial component. And if we look at on this one, you will see that even if you suppose that we could measure this value 10⁻⁶ radian, it means that amplitude include all components, and we couldn't recognize where EDM, where BR, where Y, where Z. Only one possibility to split out in BNL method, when all these components except EDM should be equal almost zero. We calculate how accurately we have to install all elements of accelerator with what accuracy. And it's appeared on the level 10⁻⁹ meter. It's super unrealistic, because we could install a heavy magnet with 1 micron It's already fantastic accuracy, but nevertheless 10 minus 9 meter is an unrealistic value. Next problem, BNLs, geometrical phase. It's special term related to the next situation, when spin coming through some element which installed a little bit incorrectly, rotate in one plate, but then coming to the next element, rotated in another plate. And even if you can do all this, rotate totally equal 0, nevertheless, arise additions which quite big value. So this is a real fact. And geometrical phase not allowed to us measure EDM again, because even from point of view geometrical phase, we need to install this accuracy again with 10 minus 8, 10 minus 9 meter. It's the same figure. So, and last one, how to coming from clockwise to counterclockwise. BNL not suggest any idea of that. Now let's speak about a little bit about Kopp-Wilber method. It's a very interesting Kopp method. Ivan Kopp understood that clockwise, counterclockwise method a little bit discomfort given to us. We don't know how to recover magnetic field. We don't know how to anything. So many things. Ivan suggests to install transverse dipole, transverse magnetic field, and try to this magnetic field increase magnetic field up to the value when orbit one of the beam, two beam he used, one of the polarized, other one not polarized, and he split orbit of this two beam and getting splitting for delta and minus delta. No, I would say we simulate this method, and we got, to construct special ring design. And even with vertical plane, with 1,000 meter beta function, it's a huge value. When tune in vertical plane equal 0.2, 0.1, it's small value which sensitive to error and so on. Nevertheless, distance splitting equal 10 minus 9. It's a very small value, and in order to register this value, we need special device, so-called we call XVIII. XVIII, in principle, sensitive to that, but nevertheless, I would ask, what about how to prove that spin oscillate on the orbit delta and minus delta exactly equals minus delta. From our investigation on spin orbital motion is not true, because spin oscillate not proportional deviation, on proportional three-dimensional change. And there are linear term and non-linear quadratic term. Quadratic term give you the same sign, not minus plus, but plus plus. And from my point of view, it's doubly correct. Now let's speak about decagerians. In one of the argument which coming from Kopp-Wilber method, he said in the plane, vertical plane, we oscillated beam in vertical plane, we remove effect limitation due to decagerians. It's not true, because if we remove decagerians in one plane, you immediately get decagerians in another plane. In particular, in our case, in vertical plane, you get the same decagerians, the same effect, and we have to use again 6-2-pole. Now let's speak about frequency domain methods. What we measure? We measure not argument, not amplitude. We measure frequency. And frequency, but nevertheless, frequency include many of them. EDM, this one, this one, this one. And EDM, very small value. But how to split out EDM? Actually, this idea came after experimental measurement frequency, where it's published in Physics letter, we find out that accuracy of measurement of frequency doesn't depend on value of frequency, or a zero, or some value. Accuracy of frequency measurement, absolutely the same. Therefore, we decide, first of all, refuse from any geometrical change. We base only measurement of frequency. And now, in our concept, no, my God. Okay, oh, sorry. We can realize, if we cannot realize situation when EDM, when this frequency has to be as small as possible, which realizes BNL method. But we can realize situation when this value much smaller than sum of EDM plus rotation in vertical plane. But since accuracy of measurement doesn't depend on value of frequency, it means that we could realize frequency domain methods. It means that we not fixed spin. We forced to spin rotate in the vertical plane. We come out from zero resonance, because in zero resonance, any perturbation very sensitive, any rotation very sensitive to any perturbation. Therefore, it's in 2D frozen spin concept, we realize such condition when radial component of magnetic field, which created by error of installation of magnet, it helps in principle to us. We create very convenient for us condition when BR more than then, and then we get EDM accurately, which doesn't depend. What means that? In principle, before we have frozen spin, 3D frozen spin, and any smallest perturbation immediately affect on axis of rotation. But if we force the beam rotate around some axis with strong rotation, strong frequency, all other additions which coming from other frequency negligible in comparison with that. And due to this fact, we could create a situation when we can forget about contribution from any error, any misalignment installation of a magnet. We think about only the measurement frequency. For instance, if, for instance, in 3D frozen, we require that this frequency have to be equal 0. In our case, BR, we keep 100 radian per second, which much more EDM, but we measure sum of this value and this one. And accuracy of this one, the same as we would measure only EDM. Therefore, but due to this big value, contribution from omega z, omega y equal negligible in comparison with EDM. This is a trick we use for frequency domain method. If to compare BNL and frequency domain method, obviously frequency domain method gives significant advantage. A little bit about what we do in order to change polarity. Polarity of magnetic field is a very important problem. There are no any possibility how to recover up to the same value magnetic field with opposite polarity for counterclockwise beam. Actually, it's possible only one thing. We force the spin rotate for measurement EDM, we keep with radial polarization. But for calibration of magnetic field, we use vertical polarization. We change polarization direction and then measure gamma effective due to spin rotation around axis. Then we change magnetic field, recover the same frequency, and then measure already in radial frequency EDM. this is fundamental feature of frequency domain method. This is all what I said to you, the total spin, precession frequency, you could read. In principle, I said to you everything about that. Approximate ED measurement precision, we estimate the value of omega and which allow to us hope to get measure EDM on the level 10 minus 30 electron centimeter. Speaking about Nika collider, it's the last remark, 2 minutes, oh, too much. First of all, we consider possibility to install such element like that, when a small magnetic field and electric field, which rotates spin in a positive direction in comparison with arc direction. But the same idea could be applied for Nika collider. If you see Nika, now all straight section occupied by equipment. It's possible to even dream about any insertion inside. But in the same time, we need special line for the beam on the straight section. It's no problem if we install small magnet in deviate beam in some direction, then construct our install on this element on the straight section, and then again, so we could create a condition for quasi-frozen spin in Nika, and that we have zero rotation spin in average over ring. This one we can create good condition for EDM growth, but we don't touch anything inside of Nika, and we don't need SPD, and we don't need anything, only just what I said. So that is methodology of EDM. It's some conclusion, measuring some different frequency of spin, so on. We could measure for the one field 10 minus 7 accuracy. For 1 year, this value equal on the level 10 minus 9. This is independent absolute determined spin precession frequency, which we got experimentally. Unchangeable position of accelerator, it's clear, and not influence spin precession frequency on other plane of spin precession under some special condition. And for transition from CV to CCCV, we're using equilibrium Lorentz factor internal precision of spin in horizontal plane, which is then used in vertical plane. So shortly, this one. I finish. Thank you very much.
Okay, thank you. Questions, please.
You certainly know about the idea about Nika to use it as a 8-shaped accelerator to measure the EDM, similar to what is planned somewhere in the States, in Brookhaven or whatever. That idea was propagating by Kovalenko, Alexander Dmitrich, and maybe others. Could you comment on that? Because you just mentioned one ring, but if we try to use both rings and transfer particles from one to the other, that could make kind of 8-shape magnetic structure.
But what is your question?
Comment.
Comment. No, speaking about, I don't know what Alexander Mitch said about what kind of, but we discussed this one a long time already with Kovalenko about possibility introduce the scheme for Nika. Nika has good advantage. It's collider. We have 2 rings, one ring and the other ring. It means that if you think carefully about that, we could using this opportunity because in principle, 2 rings allow to you increase time of measurement, double. It's instead half 1 year, you could measure half year. Secondly, now I think about how to remove systematic error even more accurately in comparison with that. But actually, for the Nika, definitely we could use possibility to try to adjust this experiment for EDM investigation. Because it's pity if we construct machine And if we have some idea for polarized beam physics and not use for EDM, because at present CERN include EDM measurement in his program, but they will measure only proton, but not deuteron. But we have everything in Dubna and deuteron source and deuteron optics, everything. We could just to join together with, for instance, with CERN and measure the proton with deuteron and give us joint good result.
Other comments?
Surely, it's crucial to have good modeling of the process. You showed also in previous talk, we showed motion equations for spin dynamics in external fields. Let us suppose that we include every sensible corrections, including gravity effects, as I've made comment. Thing is that we suppose that we have good model based on the standard model for that process and with controllable precision. And if we see the experimental data differs from the predictions on the background, it will be effect, in this case, of the parameter of EDM, and you measure that parameter, right? And it depends on the proton or electron or deuteron. But I must say that not only motion equation direct solving, but the tools how to solve is crucial. Reformulation of that model in Hamiltonian way and Hamiltonian dynamics is important step to do. I have not seen in this your comparison of three different methods that Hamiltonian methods. It's crucial to reformulate model on the good mathematical scheme. Other thing is the optimal control theory methods. You know more or less what you want to measure. And with the long time dynamics, it is difficult to reach that point because of corrections and so on. So sophisticated methods of optimal control of this device is important. And I have not seen also the, maybe as previous talk, you have TIC, the book for this activity. But I suppose that you not used that good methods on the good level for dynamical systems. This is one of the simplest form of dynamical systems.
It seems for me the electrodynamics is used for measurements.
Any question?
As I understand.
You, I can,
no, I'm a little bit confused what, how to say, the matter of your question. But actually, you see, I never said about any mathematics. In principle, we check, of course, on the numerical simulation using very perfect code, code infinity, and other code which are based on other principle of mathematics. And we compare to result and see that the same. But this method demonstrates to you that we need only measure frequency. We experimentally prove that frequency could be measured with 10⁻⁷, nothing else. Then I tell you that we measure this one, this one, this one. We don't need any accuracy. Even we ask you to install your element, not high accuracy, because bigger misalignment help us. So this method quite simple.
Yes, but without ADM, everything works. Absolutely.
But with ADM, everything okay.
But you need to, on that background, you need to identify EDM effects. So you should know.
We measure frequency in one direction, we measure frequency in another direction, we compare this value, and difference between this one give you EDM.
Are you sure that is enough, just to measure frequency?
Okay.
Absolutely,
Okay,
because if you have some comments why it's not enough, you could give us.
Because it's not proved from the model.
This is not model.
Sorry.
This,
it is electrodynamics. We believe to electrodynamics as a method to measure EDM.
Yes.
That's all.
That's all. We believe that EDM is a track which spin, and we measure spin oscillation, getting what you see, nothing else.
Okay, thank you. No questions, no comments. Send the speaker again.
Okay.
And the next speaker, Dr. Sergey Dymov, again about EDM measurement at COSI. But the talk, the time of talk. Надо помочь тебе. Помог тебе его открыть. Ты, наверное, сам разберешься. Progress towards the first direct measurement of neutron EDM at COSI-Jülich storage ring. 20 minutes, 15 minutes.
Okay, I will also talk about JEDI experiment and the preparation for EDM measurement. And luckily, the two previous speakers have described, covered quite a bit of my talk, so I can be more brief, especially in the introduction part. So this is the what we understand under the electric dipole moment separation of the charge, and it requires the violation of time and P and T parity, and it's related to the question of matter-antimatter asymmetry and baryogenesis. So here I will not maybe repeat what was said. And the current limits for the EDM, the limits which are coming from the standard model, from electroweak interactions, are very low indeed, and the limits from the supersymmetric SUSY are higher, and it is measurement of the EDM can somehow bring us information beyond the standard model, about the physics beyond the standard model. And here also the motivation for the charge particles EDM. First motivation is that we need to measure EDM of different elementary particles, and there is no information about how they can be related to each other, so it's important to measure different values, and the most advanced now really the measurement for the neutrons, but the information for the charged particles are coming only from the neutral systems, from atomic measurements, and this information is model dependent, and of course any possibility of direct measurement is of great value in this question. And here we have, again I show the Thomas BMT equation, and which consists of the parts for the magnetic dipole moment and electric dipole moment. And if we want to measure the EDM, then we want to leave only the part related to the electric dipole moment, and this can be achieved in a pure electric field which cancels the first term, and using a magic momentum which cancels the second term, but this can be achieved only for the particles with G value anomalous magnetic moment larger than 0, for example protons. For neutrons this is not possible, unfortunately. And but for protons, really, the first idea is to fulfill this condition, and under frozen spin, in the frozen spin situation, when the spin rotates at the same frequency as the momentum, we can expect the vertical component of polarization to build up due to the EDM, to the EDM coupling to the electric field. But for a pure magnetic ring, this wouldn't be the case, of course, and the EDM would be the vertical polarization due to EDM could be achieved from the radial electrical field, which is Lorentz effect, which is a relativistic effect in this case. So here are three options which are now thoroughly considered in JEDI collaboration. Of course, the information which was presented by Yuri was also considered. It's also now under consideration as an advanced topic, and it will be very interesting in the future to see the discussion. And so what now we have a pure magnetic ring usual accelerator, and we start this study at COSI in Jülich, and this ring can be used now for systematical study, methodical study, and for estimation of EDM of deuteron. And this pure magnetic ring doesn't allow, for example, cancellation of the space parity effects due to use of reverse beam of the two beams. This is possible only in electric accelerator, so it has lower sensitivity due to this, and the spin is precession in the horizontal plane, and so there is no frozen spin condition possible. Nevertheless, as Kolya already also described, it's possible with the use of radio frequency Wien filter. It's possible to build up the EDM effect also in this condition. But for the future, the final goal would be the pure electric field at magic momentum for proton, really in ideal conditions with use of two counter-rotating beams. And and there is an extensive document describing these possibilities. So here is a list of main list of achievements which has been done in JEDI collaboration on this path, methodical achievements, partly also covered in the previous talks, the high precision spin tune measurement, the long polarization lifetime. Okay, it also doesn't work again. And the new achievement is update of the feedback system, which I want to show now, and also the measurement of the invariant spin axis, the beam-based alignment, and the beam position monitor with the use of Rogowski coils. And here is the basic idea of use of the RF Wien filter in the all magnetic ring. In all magnetic ring, if we can consider build-up of vertical polarization due to EDM, due to the spin rotation in the horizontal plane, this build-up will be cancelled. So we should have very tiny oscillations of this build-up. And the solution can be an RF pin filter, that is a device with perpendicular electric and magnetic field, which is transparent for the momentum, but acts on the spin. And this RF pin filter should act at the frequency or resonance frequency of the spin. And this can allow for the systematic buildup of the polarization, of the vertical polarization out of plane. Here we see that the EDM would be shown as a tilt of the axis of the spin rotation. So in the first picture you see the picture of the spin rotating on the horizontal plane without EDM effect. On the second picture, the axis tilted due to EDM, and on the third due to imperfections, for example, magnet misalignments. And this produced the same effect. And as Holly again described it in more detail, the tilt of the axis in presence of the wind filter produces buildup of the polarization, and this buildup depends on the phase between the spin and the speed of buildup depends on the phase between the spin and the wind filter, and also on the misalignments. And if we include the artificial misalignments like rotation of the wind filter or some kick from the solenoid somewhere in the ring, then we can study how our buildup depends on these misalignments. And this is a result of such study, which was done in November last year. And this is a parabolic shape in two parameters, kick of the solenoid and angle of rotation of wind filter. And in the minimum, we see the parameters which correspond to the inclination of the spin rotation axis. This inclination is caused by EDM and by imperfections, by misalignments, both. The misalignments can be estimated from the models and subtracted. This is ongoing effort now, and first rough estimation that observed limit can observed effect limits deuteron EDM down to 10 to minus 17, but better experiment is under preparation. We've improved improved on several points, like a new feedback system, new polarimeter, improvements in the beam positioning, in the wind filter, electric and magnetic field match in the wind filter, and so on. And the next measurement is planned for 2020. Out of there, we already planning to get more sensible results already on the deuteron EDM. So here I will just shortly show the idea of few methodics which are currently developing. Currently developed, this is beam-based misalignments, and this is needed to ensure that the beam goes through the center of the quadrupoles. And here you can measure the beam offsets and study the dependence of this measured beam offset on the strength of the quadrupole and on the position of the beam. And this dependence can be described as a also quadratic form of these two parameters, and the position of the BPMs relative to the quadrupole can be defined with very good accuracy, even if we don't know all the lattice parameters very precisely. Here is the development for the Rogowski coil, and This is used for the precise beam position determination, especially important for the beam passing the RF filter. And the big advantage of Rogowski coil is that it's very thin. It's 1 centimeter only thickness and can be easily installed in the ring and has a good resolution, especially for radio frequency signal. And the new feedback system, this I will just very shortly say, what is the advantage of it. The old feedback system analyzed the spin precession, in-plane spin precession, and determined the spin tune, and determined the phase of the spin. And it was used to correct the frequency of the wind filter, so that the phase between the spin rotation and the wind filter was kept constant. And as Kolya also showed in the pictures, there is a drift in the spin frequency, which we observe as a drift of the phase. And this can be corrected. But during the work with the system, we found that the system is not doing quite what we expect from it. And this is seen on the polarization build-up for several cases. On the upper picture, without feedback, this is simulation picture, and with feedback. And what the system keeps is the initial slope of the polarization build-up, but the amplitude and the frequency of the build-up, slow build-up oscillation are changed. And this is because the feedback system takes the beam which is affected by the RF, by the wind filter itself, which it corrects in turn. And so the new idea is to use multi-bunch structure, beam structure, so 4 bunches for the beam, and use one of the beam as a pilot beam, which should be gated in the RF filter, so it should not be affected by RF filter. And this beam, this bunch should be used for the feedback system for the other bunches. And this is also very interesting. Opens interesting possibility because you can set for different bunches for the other measurement bunches different phases and control the systematics also in this way. And this was the last slide. Thank you very much.
Questions? You say that estimation for EDM for neutron 10 to less than 10 to minus 17, yes?
Well, the analysis is ongoing, really. So the tilt which we observe now would correspond, if it purely assumed to be pure EDM signal, no imperfections, that it would correspond to 10 to minus 70 roughly. So it's an upper limit, but of course this is a signal mostly coming from imperfections. This we understand.
Did you use new polarimetry measurement, neutron carbon, or some old?
No, this is still old. This is VASA polarimetry, yes, and okay. I think it no analyzing powers were still used, so it's still working with asymmetries. Yes.
Any comments, questions? Let us wish you to finish this result and publish it. Thank you. We shifted by 10 minutes due to technical problem in the first talk, this measurement of EDM. And now we have to continue without coffee break, next session formally. I don't know. Oh, coffee break? It seems formally without coffee break.
сделали? Отлично.
Просто не могла найти, где это выключить, пришлось выдернуть.
А это правильно, это не надо выключать, это оно не отцепляется. Просто в каску вставляется.
Я просто сюда тыкал, чуть не лежит.
А как открыть? Да, сделать. Это вот это, да? Ага. Так. Нету номера. Ну, открыть просто. Вот сейчас я номер поставлю на весь экран. У вас PDF-файл, значит, это Ctrl-L. Смотрите, вот нажимали и Ctrl-L.
Ага, ясно, спасибо.
Так, 11:10. У нас пока нет 10-го. Ее все равно переименуем. Так, спин.
Это XVIII.
XVIII. Какая прелесть. Сейчас на ней все антивирусные программы будут ругаться. Так,
Волчанский. Можно на всякий случай запустить?
Ага, сейчас на весь экран такая.
Спасибо. Данке.
Ты ничего не дал.
Грацио. Чего?
Ничего не дал.
Как не дал?
70 дали, да?
Нет, нету 10-го и 13-го.
И хорошо.
Ну, в каком-то смысле, да. председатель обрадовался. Не тут-то было. Ну как? Длинные дискуссии можно делать.
Тут как-то народ ропщет, что не знает название. С этим тут мы произвели некую не знает название доказов. Что если вот Сережа составляет каждый день этот самый список с названиями, и вы выкладываете его на сайт, чтобы люди могли смотреть?
Нет, какие проблемы?
Да?
Файл даете?
Да? Все,
я могу выкладывать на сайт, но мне не труднее напечатать там 10, 15, 20 экземпляров и положить где-то здесь, и все. Кто хочет, пусть берет.
Мы можем и то, и другое сделать.
О, хорошо, давайте вот завтра.
Ну, файл просто делаете и посылаете мне.
Все?
Ну, хорошо. Нет, ну я и сам способен положить этот файл.
Да, конечно. Нет, ну мне сначала надо сделать раздел.
Нет, я понимаю,
положить,
я понимаю, что сделать раздел,
класть,
поэтому я понимаю.
Никаких проблем. У меня нет доклада Елисеева. Он ожидается?
А он не сегодня, по-моему.
Вот 13-й, Елисеев, 20 минут.
Елисеев сегодня. Ну, значит, он за разум зашел. Я его не видел.
Ну, я тоже. Ну, у вас пока одного докладчика нет. Номер 13 докладчика нет.
И даже мужик способ все равно легче, да?
Так,
ну, не придет человек, не придет. Я его вообще и на прошлой неделе не видел. Он же чуть ли не напротив меня сидит.
Ну да.
Please take your seats. Йод не нужен. We must keep strict to a schedule, because otherwise those who didn't attend the session shall eat everything over. So I invite the first speaker, Dr. Uzikov, and he'll announce his talk himself.
Yes.
Yes, and then spin amplitudes and PD scattering.
PD scattering. How does it work? Does not work. No reaction. Коля, how to manipulate? Nothing work.
Если, слушай, бери лучше.
А как?
Запасную.
А как тут? Я ни черта не вижу. Сейчас я очки возьму. Такие мелкие детали.
Ее, наверное, выключили. Какие-то
злые.
Конечно, да. Сейчас включилось. Нет, сейчас все работает.
И листать?
А почему-то листать нет. Что у тебя ничего больше и нет? Один слайд.
Нет, есть, увы.
Не знаю, что не листает.
Не листает.
Здесь листает.
О, это листает.
Смотри, в общем, как хочешь. Я на твоем месте листал здесь.
Да, и смотрел туда.
Указка здесь работает, но есть еще одна указка.
Это просто указка, она не листает. Да, листать вот этим.
Смотри, вот оно почему-то сейчас не листает. Я не знаю почему.
Ну, что ж. Не понял. Листать это
вот.
стрелка. Окей. And then spin amplitudes and proton-neutron scattering, elastic and inelastic, in collaboration with Colin Wilkin and Alexei Lugin. What's plan? No, motivations. Then I will say a few words about spin amplitudes in inelastic. And after that, how these amplitudes are incorporated into amplitudes of proton-neutron elastic scattering. Also about spin-dependent Glauber theory of PD elastic scattering. Some numerical results will be shown for elastic and quasi-elastic process when instead of neutron, in final state we have d-proton with 1 and 0 states. And how it is allows to test NN amplitudes. And DD elastic and inelastic only for plans for future. At the end, a few words about the search for T invariance violation in double polarized proton-neutron scattering, which is related to previous topic, previous section. Helicity amplitudes of NN scattering can be determined in different way. Helicity presentation is given here. We have 5 independent amplitudes, 2 of them with spin flip, 2 without spin flip, and 1 with single spin flip. We have 5 amplitudes for identical particles, proton-proton and neutron-neutron. In case of CPT invariance, Lorentz invariance, PET invariance. If you lost isospin symmetry for proton-neutron scattering, then we have 6 amplitudes instead of 5. Time reversal non-invariance provides 2 additional amplitudes. Instead, we have 8 amplitudes. And if P parity is broken, then we have 16 amplitudes. Having these amplitudes, we can explain any spin observables of NN scattering. What is the main idea, the main dream? To perform complete polarization measurement. It means to measure such observables which allows to determine amplitudes, absolute value of these amplitudes and relative phases. Indeed, for 5 amplitudes, we need 9 independent observables. Probably Vasily Mochilov will tell about this on the next day, how they are going to do it. Complete polarization experiment really was not performed even at low energy, but we have SAID base date, which usually we use to calculate any spin amplitudes for proton-proton and proton-neutron. For proton-proton up to 300 GeV over C, for proton-neutron up to 1.2 GeV over C. Arndt, Strakovsky, Workman developed this system and improving it permanently. Concerning this SPD Nika, I should note that above 3 GeV, only differential cross-section, and mainly single spin asymmetry A1 up to 500 GeV measured, and at 6 GeV, 12 GeV over C, a double spin asymmetry is also measured. But information about other double spin asymmetries are poor in forward direction. But nevertheless, there are some parameterizations for these amplitudes, like Redze parameterization by Ford Van Orden, Sibirtsev, A-canal approximation, Wakai-Zomi, and Savamoto. And maybe other also, I'm not sure that it's a full list. If you have, non-visible the first line. If you have a Redze parameterization like it given by Sibirtsev and co-authors, they use omega, rho, F2, A2, region exchange, and Pomeron in the region up to 3 to 500 GeV. Then it is possible to reconstruct, using these proton-proton amplitudes, it's possible to reconstruct also antiproton-proton, proton-neutron, and antiproton-neutron amplitudes as a linear combination of these proton-proton amplitudes. However, in this analysis was not included into this analysis was not included data for double spin polarizations measured at argon. What is the fit? What is the results of fit of Sibirtsov paper in Sibirtsov paper? It is vector analyzing power, single spin asymmetries. We're given in broad interval of energy from 3 GeV up to 45 in forward direction, but it enough at rather large t, where at J maybe does not work. But nevertheless, the fit seems to be reasonable. For double spin asymmetries, the results are obtained only at low beam momenta, up to between 3 and 4 GeV. And using these amplitudes, it's possible to calculate, as I mentioned, antiproton-proton total cross-section, proton-proton total cross-section, antiproton-neutron, proton-neutron. These bands are obtained from in Sibirtsov paper. It looks quite reasonable, but in detail, not so, because there is problem with antiproton-proton, which is larger than experimental points, and no cross to zero. And so, therefore, it is necessary to check these amplitudes. At higher energies in TV region, Alexei Lyugin has also parameterization using only Pomeroy exchange. Here are shown differential cross-sections, and in the next slide, single spin asymmetries at 100 GeV, 2 and 300 GeV. And he has planned to connect this parameterization with lower energies, introducing the region exchanges in addition to the Pomeroy exchange. PD, elastic scattering. In this case, we have 36 transition amplitudes, but only 18 independent if we have P invariants, which is formulated in this way. Oh, here, T, it is transition operator. E lambda prime, it is a neutron in polarization state, initial and final. And phi mi prime, it is a proton polarization state. If you have T invariants, then only 12 amplitudes are independent on this additional requirement. And in this independent amplitudes can be chosen in different way. Also, Platonova-Kukulin used this one, A1 and 2, A3, A12. If we introduce, if you omit T invariants, assume that it is broken, then we have additional 6 amplitudes. And having this formalism, we are able to calculate differential cross-section for polarizations, initial, finals, pulverized particles in this form, where coefficient C, A have to be measured, P, D, PG are determined by the experimental conditions. What is necessary to do in order to calculate this observables? To take traces from spin operators, sigma or tensor polarization, tensor operator, using this transition matrix element, then we can calculate everything. The question is, what is the M? It is determined by dynamics. We assume that dynamics is Glauber in forward direction, it works well. I will demonstrate it. We have only 2 mechanisms, single scattering, first line, without any integrals, and double scattering with integral over the transferred momentum. Only on-shell elastic PN amplitudes, scattering amplitudes, P even, like it given in this line, the structure, introduced in these calculations. We have here not 5 but 6 amplitude because it's in the laboratory frame written. Additional spin orbit term C prime appeared, addition to the C without prime. Spin independent are spin orbit and double spin terms other. Results of calculations are shown here for 135 MeV, differential cross-section, full line, it's the result of Glauber calculations with Coulomb included, without Coulomb this dashed line. For AD, neutron analyzing power is upper curve, also improvement obtained after inclusion the Coulomb interaction. And for AP, similarly. What is important to note that Fadeev calculations performed by Tiltuva, Fonseca, Sauer for this reaction, for this energy, also give almost the same agreement with the data. And not only for single spin asymmetry, but for spin correlation parameters. These Glauber calculations, our calculations. But they are also, like in previous case, similar to the Fadeev calculation. And it is important to mention why Glauber is so successful. Glauber model is in comparison with exact Fadeev calculation. In Glauber, we have no off-shell effects at all, only on shell. Maximal multiplicity in the scatterings is equal to number of nucleons inside target. For deuteron, only 2, not more. But in Fadeev calculation, we have off-shell PN amplitudes and infinite series of rescatterings. Therefore, why we have the same numerical results using these different theories, the answer is only one. We have compensations between included explicitly off-shell effects in Glauber and not included multiple rescatterings. For the first time, Harrington mentioned it in 40 years, maybe 50 years ago. But the numerical, it is not a theorem, it is on the indications. But these numerical results show that indeed there is, this compensation takes place in real life, in nature. Therefore, we can apply Glauber at high energy because Glauber is more validated at high energy than at lower energy. There is some example, AYT and AYY, and recent measurement at COSY, tensor polarization AXX, and many other examples. But there is a problem, of course, without an scattering amplitudes. And in the recent paper with Colin Wilkin, we discussed a ratio of AP to AD. No, indeed, AD to AP. In general, using these 12 amplitudes we have for AP analyzing power, this expression for AD another one. But in the limit of small transfer momentum, when Q comes to 0, only a single scattering mechanism dominates, is active. And the ratio AD to AP precisely at 0 transfer momentum is equal to thirds. If we make expansion, Taylor expansion over the some non-zero terms, then we obtain this relation for a real part A2, A10 divided by real part A2 and 1 is related to this R ratio, minus 2/3. But these spin amplitudes are shown here. They are related to spin-independent term A, spin orbit term, and transfer spin transfer term. Because A2 in numerator and in denominator, therefore not sensitive, as this ratio is not sensitive to spin orbit. Therefore, sensitivity of this R deviates from 2/3 only due to the spin transversal terms. It is the main idea of that paper. So our results. We can show in the simplest way why this ratio is equal to 2/3. In fact, it is comes from the following. For AP, a proton, we have 3 projection of deuteron, and for AD, we have 2 projection of proton. Indeed, on this ratio, it determines 2/3. But important is interesting is the deviation from 2/3. It is shown here using this spin-dependent Glauber model. What is the deviation from 2/3 of this R? For single scattering mechanism, it is about few percent, very small. And when we add double scattering mechanism, it changes, but very weak. Therefore, this ratio is sensitive mainly to single scattering mechanism, and within this, only to spin transversal terms. What is the reference to our paper? And these are some results of calculation of this ratio in comparison with the experimental data for several energies. And if spin terms is included, this ratio changes by several percents, and it is finally, what I want to say, it is important to measure this ratio with high accuracy in order to get information about spin terms of NN elastic scattering. Of course, it is a challenge for experiment because at Indiana University, this measurement was done about on the level of 1% at 135 MeV, at 2% at high energy. What for SPD energy, I cannot say. But it would be interesting to measure with high accuracy this ratio. In elastic neutron-proton scattering, when instead of deuteron, we have diproton in Figel street. Only if we are restricted by very small transferred momentum, only single scattering mechanism is sufficient to describe the differential cross-section for at different energies of deuteron from 1 GeV up to 227, the reference given here. And also spin observables, tensor polarizations, also for this interval, and spin correlations. Only at high energies, at 2 GeV, there is deviation between results of calculation using SAID database and Anki results. But these deviations, as was shown, comes from the pure knowledge about NN amplitudes incorporated into SAID. Therefore, measurement, anti-measurement of this reaction allows to improve the database for NN scattering amplitudes. It is a main idea for measurement for studying of proton-deuteron elastic or quasi-elastic scattering to get information about NN scattering amplitudes. In case of DD elastic, we have discussed a more complicated mechanism. Not all of them are shown here. Triple scatter is possible, is allowed. And an example of calculation using Glauber model was done many years ago in the paper Goggi, and Alberi at the end of this list of authors. The cross-section given here. In comparison, the full line, it is a Glauber with intermediate scattering, intermediate some Gribov corrections found to be important. At this square root 553 GeV. I mean, it has to be divided by 4 in order to be related to SPD. 4.
ISAR experiment.
ISAR, that. ISAR, that's right. Now, search for T invariance violation in double polarized PD scattering. Why search for T invariance violation but P parity conserving effects? T violating and P violating effects, TVPV, discussed today in EDM talks, arise in standard model through CP violation phase of Kaviba-Kobayashi-Moscow matrix, first. And second source for QCD theta term, just it is a source for EDM. But T violating, parity conserving, TVPC short, and flavor conserving effect, first considered by Okun before the standard model was formulated. They do not arise.
Weightman and T.D. Lee.
Sorry?
Weightman and T.D. Lee, 2 Nobel Prize winners.
Okay. But these forces do not arise in standard model as a fundamental interactions. But they can appear within standard model after taking into account weak corrections to TVPV terms. But in this case, we have Fermi constant in second power. Therefore, the coupling, effective coupling constant, extremely small. Gudkov was first who mentioned this. Nevertheless, without standard model, much larger constant can be, of course, realized in nature, who knows. And what is the main point, that experimental limits on TVPC effects are much weaker than for EDM. It is a main stimulus to study these effects. For example, in proton-neutron double polarized scattering. In this case, in forward direction, we have, if you have only T even terms, then we have only 4 structures in forward elastic scattering amplitudes. And if we add T odd P, but P even term, it introduces additional term with unknown amplitude G5. And using generalized optical theorem, we can calculate total cross-section related to G5. And this cross-section is a null test signal for time invariance violation. Null test signal means that it is zero only. It is non-zero only in case of these forces are presented in the nature, and is zero in opposite case. Zero only when they are absent. Oh, maybe with some exclusion. But non-zero only in that case when we have these forces. If you have T even, P even forces is given here, but T odd, P even are presented, I will not explain what is the structures, but with some terms H and G prime, like rho meson exchange, but not normal rho meson, but rho meson with TVPC forces. And the null test signal is formulated, okay, is formulated as an integral over a transferred momentum, double scattering, appears only double scattering mechanism, contains deuteron form factors, not necessary to explain how they derived, how they look like, but here we have this unknown constant TVPC, time invariance violation, G and H, this G and H, and multiplied by the well-known T even, P even, C prime terms, spin orbit terms. But we have to know these terms. We have to know them, to measure them before to say about the strength of these unknown constants. It is a reason for knowledge for the measurement of NN elastic scattering and PD elastic and inelastic scattering. C prime, in terms of helicity amplitude, C prime contains phi5 and phi1 and phi3. And then the total cross-section has trivial 4 terms, which are T even, P even, and the last additional term in front of the cross-section, coefficient in front of the product of vector polarized proton in the perpendicular direction and tensor polarized deuteron with alignment along the bisectors of angle, XZ angle. It is a null test. This is a null test signal, which it is important to measure. How it behaves is shown here in S approximation with dash curve. In the D wave is included to obtain this full line. We have about 0 points occasionally. It's not because the TVPC effects are absent, but because of some modulation factors, specific play of modulation factors. Therefore, measurement of this signal has to be done not at one point, but at several points. Okay, therefore, I come to conclusion. Measurements of spin observables in different types, in PD elastic scattering and PD inelastic, DD elastic and inelastic, it is PD is important because available radio parameterization of PP amplitudes can be tested. We can obtain clear test for these amplitudes. The ratio AYD to AYP at small q has to be being measured with high accuracy about 1%, give information about the spin transversal and N amplitudes without measurements of any other spin observers. Redze formalism for PP provides access to antiproton neutron elastic scattering, but indeed it was not tested in double spin observers. And these observers can be updated with PD-NICA to test PP amplitudes, to study oscillation effects. Lugin said about them many years, to test dispersion relations. Search of T invariance violation in double polarized proton-neutron scattering at energies of early universes seems to be very important. Thank you for your attention. Oh, one last transparency. NN forces are fundamental to nuclear physics on the whole. It is important to study a full set of their components, including small spin terms, because elastic scattering in N amplitudes, it's an NN potential, nuclear potential. Oh, now, thank you.
Thank you. one important, very important question, please.
You consider nucleons as point-like particles and include all of the structures. It reminds me that weak interaction theory before the people, Feynman and Gell-Mann were from that structure were extracted vector minus axial vector structure and then later reconstructed standard model. Have you any indication about the constituent structure of the nucleus?
No, indeed, form factors are introduced. I showed this amplitude. We have no point-like particle, but we have these form factors. Therefore,
quark counting rules.
No, quark counting.
Somewhere you should find in the larger angular scattering parts that one counting rules. Any indication of the constituent structure of the nucleus? Of course.
no, of course, it is well known that quark counting rules works for proton-proton elastic scattering in a region where we have T-even, P-even interaction. But our main goal is to search for time invariance violation. Is this case?
Is for large angle scattering, right?
Yes. For yes, thank you. Because counting rules, of course, at 19 degrees, we are restricted by forward direction. Therefore, it is not the case.
Okay. Thank you very much. We're really running short of time, so that we are moving to the next speaker.
Can I take the water? Thank you.
Next talk is by Alexander from Vietnam.
В нижний самый.
Вот этот, да?
Да. Okay, let's go to somewhat heavier objects. I will speak about lambda hyperon reconstruction at the BM10 experiment and prospects for polarization studies. Okay, here is the outline of my talk. I will remind you about Nika complex, then explain physics possibilities at the nucleotron, and present BM10 detector setup. Then I will present some details about technical run analysis with carbon beam, data analysis for GeV. So I will present reconstructed lambda, spectra DN-dy, DN-dpt, then present level of agreement of data Monte Carlo simulation. Then I will present the extracted cross-section and yields of lambda hyperon. Then I will show reconstructed PT spectra of lambda and extracted temperature. Then some results, preliminary results for 3.5 and 4.5 GeV. And then I will show the status of Monte Carlo study of lambda hyperon polarization. Then a summary and plans. So here is probably already a familiar picture of the Nika complex at the laboratory of high energy physics. So we will have in future collider. And I will speak about this spot, which contains so-called BM10 detector, which is a baryonic matter at nucleotron. And the experimental detector can be seen on this slide, on this picture. It's kind of overall picture, and then you will see it in more details here. Okay, just a minute. Okay, later. Okay, so here is the physics potential of this detector experiment. So you can see the collision energy square root of S. So here is the several experiments running in future. So we have, okay, not we, but our colleagues have NA61 star, then headers at GSI, and future Facilities will include BMT, which is stage 2, which will approximately same energies from 2.3 to 3.5 GeV, but higher luminosity, and it will be higher than HADAS existing now, but of course there will be a record-breaking experiment called CBM at CIS-100. But the coverage of square root of S shown here, and BMT will almost touch the MPD physics program in terms of the collision energy, and will cover energy region of maximum baryonic density. Physics potential can be also seen here. So these are nucleotron energies and in square root of S. And these are excitation curves of different particle production, starting from light pions down to heavy hyperons, anti-hyperons. So you can see that at this energy regime, there is a threshold and subthreshold production of like Xi minus hyperons and almost threshold production of lambda. So this energy regime is very interesting to understand some features of nuclear matter. Also, at this energy region, there is a high cross-section of hypernuclear production. So you can see predictions of statistical models for different hypernuclei, for hypertritium and double lambda hypernuclei. So you can see that BMT almost at maximum, but okay. So study of hypernuclei, this detector will be also interesting physics topic. Okay, here's the detector picture, which this is a so-called future final configuration. So this is typical fixed target experiment, which contains a dipole magnet and instrumented by central tracker. It will be a hybrid tracker consisting of GEM stations. They are shown here, and also silicon stations, small aperture at front next to the target, then large aperture silicon, which will be provided by our colleagues from CBM, from GSI, and also some small detectors to define beam and the trigger, and also some external detectors, which are time-of-flight detectors to identify hadrons, electromagnetic calorimeter to measure electrons and photons. These are time-of-flight. It will contain two stations at 4 meters from target. These are two shoulders, and one large time-of-flight at 7 meters. Also some external tracking detectors to match tracks from central tracker to TOF, and also there will be existing and also will be ZDC to measure centrality collision and event plane. So this is, as I said, the future configuration. Now we have measured some carbon interactions with smaller configuration. It is shown here. So size of this first detector is approximately 70 centimeters in X and 40 centimeters in Y. And these stations are twice as wide. And the feature of this second carbon run was that beam was passing through the center of detectors without beam hole. So heavy ions actually affected the work of these detectors, and it had some not very good consequences for analysis, because the readout of these detectors was double-sided strip detectors, so this area around beam was not only around beam, but also affected this vertical region. But anyway, it was managed eventually. So the carbon, as I said, carbon beam run program is shown here. So it was intended to test and calibrate time-of-flight detectors, trigger detectors, ZDC, parts of electromagnetic calorimeter, then trace beam through detectors, align detectors, measure beam momentum at different values of magnetic field from 0.3 to 0.8 Tesla. And of course, measure inelastic reactions of carbon beam with targets like carbon, aluminum, and copper for several sets of energies. Okay, so here is the results for lambda hyperon reconstruction, and the idea of this reconstruction is shown at this scheme. So we have protons and pions. In fact, in this run, there was no particle identification, so all positive tracks were taken as protons, all negative are taken as pions. So we took pair of tracks and then reconstruct vertex, which should be separate, so-called secondary vertex or the decay vertex, and it should be separated from the primary vertex by some distance, which consistent with decay length of lambda. So this topology defines the selection criteria. Here you can see listed here. So we had 7 stations, track stations, and required was we should have at least 4 hits on these 7 stations. Then the momentum range for positive tracks below 4 GeV to reject proton spectators. Then momentum range of negative tracks greater than 0.3 GeV to reject some junk at low momenta. Then distance of minimum approach here should be below 1 centimeter. It means relatively good quality of vertex reconstruction, and path should be greater than 2.5 centimeters to have good separation of primary and secondary vertex. And so we could reconstruct lambda invariant mass peaks for different targets here for carbon, aluminum, and copper targets, and you can see that it is well seen, and the width of peak approximately 2.53 MeV, and we have collected approximately 5 million triggers for different targets. This corresponds to 2.5 days of data taking. Okay, as I said, we needed to compare the experimental data with simulated, and the quality could be seen here. So there are some distributions, and the red lines present experimental data, and blue curves correspond to Monte Carlo for DCM QGSM generator for carbon-copper interactions. So here is the number of tracks per event, good agreement. Number of hits per track, on average 5.5 hits, also good agreement. Then number of hits per track for negative particles, and these are pions. Here is number of tracks for primary vertex, used for primary vertex reconstruction. So also rather good, except for this beam probably. This is the momentum of different particles, so divided by charge. So positive correspond to positive tracks, negative to negative tracks. For negative tracks, the agreement is quite good. For positive tracks, Monte Carlo predicts this secondary, let's say secondary peak corresponds to proton spectators, and this one should correspond to deuteron spectators. And you can see that unfortunately Monte Carlo does not reproduce the data here at this peak, and the explanation is that these proton spectators go through the beam area. As I said, this beam area was affected by the beam passing. So Okay, but it didn't affect the lambda reconstruction. Here is also momentum spectrum for negative tracks. Okay, but we needed not only to get reconstructed lambdas, we needed to correct for efficiency to extract some reasonable numbers which could be compared with Monte Carlo and other experiments. So this can be done by calculating yield of lambda hyperons, and this formula shows how it's done. So we need to calculate luminosity, trigger efficiency, reconstructant efficiency, and this is the formula which we are used to calculate reconstructant efficiency. So it can be decomposed into different factors. Okay, I will not go into details. And then we need to use total cross-section, which is listed here, and it can be extracted from model or calculated using this kind of another formula, which are quite consistent, so for different beams. So after applying this efficiency correction, we extracted yield of hyperons versus rapidity for different targets. So you can see that for heavy targets, this spectra becomes softer for rapidity, and also spectra for PT. So also, okay, they are shown like, and compared with two models in green, York MD, and in red, DCM QGSM. So results seem to lie between two predictions. Okay, here is another presentation. These are so-called invariant PT spectra, and they are used to extract so-called temperature by fitting some statistical expression from the statistical model, again for three targets. And these are comparisons with URMD and DCM QGSM. So in principle, the results are consistent within the error. Okay, here you can see some numbers. You can, these are lambda yields in some regions of PT, and these are extrapolated to the full kinematical region using predictions by models and cross-section of lambda production. And these can be compared with other experiments. So these are our point, this is our point. Here's the CC interaction measured at Propen chamber, and this is Hades data. So it looks like it goes up. And also we have 3.5 and 4.5 GV points, not yet calculated by already preliminary results on lambda reconstruction. So these are 4.5 GV for different targets: polyethylene, carbon, aluminum, copper, lead. So the results are quite good, better than for GV because of higher cross-section. For 3.5, of course, they're not so good because it goes down the cross-section. But still, we can see invariant mass peak. And we will try to extract cross-section and yields. Okay, so this is a summary of past and future of this experiment. So we had several runs at 2016, 2017, 2018. So these are already processed. Here, heavier beams, argon and krypton, they are in progress, and future is for 2020 and 2022 and later. Okay, so this is another study. As I said, if we have lambda, we can measure some polarization here. For instance, we can measure polarization with respect to production planes. So we will have beam and the direction of lambda, which they defined a plane, and the transverse polarization. If we have then in raster frame of lambda, we can measure proton direction with respect to this plane, And this angle should have some decay should not be uniform in theta, dependent on theta. So these are model predictions. They're made by DCM QGSM generator by adding some calculation based on this paper, and it was done by late Konstantin Kudima. So you can see the dependence on polarization versus on PT and X, which is a fraction of beam momentum of lambda. And this band at 0 is for secondary lambdas, which are not polarized, at least in the model. So, okay, so when we have reconstructed invariant mass peak, we also have on the peak some background, which can be extracted by using so-called sideband procedure. So we take here and here, extrapolate, and subtract from the peak, and we have some correct number of reconstructed lambda. And if we plot this versus cosine theta, so this shows the signal plus background. By using this procedure, we subtract this distribution, and eventually we have some correct distribution, which very well correspondent to the original distribution. So also you can see here that this distribution doesn't show the cosine linear dependence, because there is very huge effect of the detector acceptance. So in fact, how to extract this, it can be done very kind of simple procedure. If we have this with polarization distribution, then we simulate the detector without polarization, and we have this difference. By dividing one by the other, we can get this linear dependence. So here we can again see this original distribution, and after division we have this cosine linear dependent, which we should have. And this polarization extracted is shown here by this P1 parameter, and it is compared with what we should expect from Monte Carlo. So this peak corresponds to non-zero polarization of secondary lambdas, but mean value is pretty much consistent with what we extract. And also we checked the...
Can you determine also the asymmetry parameter alpha from your data?
No, this is not... Yes, this is asymmetry parameter. Yes, this is asymmetry parameter.
The question should be put in such a way: if you change alpha like it was told this morning, how simulation will change? Because now, according to modern data, alpha is like
75,
like 10% or 20%.
Okay, I mean, yes, I mean, it. Okay, so it depends on alpha, of course. So it's.
So you may include also this new alpha.
Sure. Yes. Yes. Okay. Okay. So also we have checked this with this simulation difference. I mean difference versus PT. So for low PT, as expected, this asymmetry parameter decreases. For high PT, it increases. So it has largest, and again consistent with what is inside Monte Carlo model. Also, the dependence on X parameter is also similar. So for low X, it is smaller. For large X, it is larger. Again, in agreement with this histogram. Okay, so this is a summary. So BM10 experiment technical runs have been performed with carbon beam for different energies, 3.5 to 4.5 GeV. Argon and krypton beams at somewhat lower energies, but not yet analyzed. First physics results have been obtained on lambda yields in C aluminum, C copper interactions. BM10 is on the way for heavy iron high intensity runs in 2020 and later, with the full configuration central tracker. The analysis method and procedure for lambda polarization study have been developed and tested on simulated central gold-gold events at 4.5 GeV. The obtained results demonstrate quite good sensitivity to polarization variables. It is planned to apply this analysis procedure to the experimental data. And possible extension of the method to some other polarization studies, polarization transfers to reaction plane should be evaluated in future. Okay, thank you.
Thank you very much. And I particularly would like to thank you for being really to saving time.
Okay.
And we have time for a couple of questions and comments.
You extracted the temperature already from the data.
Yes.
Using the feeds to statistical distribution.
Yes.
Was it done for lambda or also for
protons?
For other currents?
Okay, so there is a analysis for K mesons, but not finished yet. So only right now only talk for lambda.
So it can be possible to perform analysis for different particles and compare, right?
Yes.
And just so, how much time would you need to give the first results on experimental results on lambda polarization? Rough estimate, yeah.
Okay, I mean, as you know, our main player was on maternity leave twice, so now she's back to work, so hopefully, okay, in principle, everything in hands, so several months in principle, okay, to get something, but to correct for some experimental features, I don't know. I mean, I don't have an experience with this. So original results could be in a few months, but
I mean, for first results for polarization using the real data.
Yes, I mean, we could get some points, but how to interpret them, finally, I don't know. I mean, it needs some study.
Just a question. Your precision about vertex determination is about a couple of centimeters, I guess, because you put a cap on 2.5 centimeters. When you introduce in your experiment the silicon tracker, how much better that would be? And how many more lambda would you detect? Your efficiency now is about few percent. How much is it?
Yes, it's about, let's say, 3-5%. But it's not only the vertex, but also the detector configuration was not very optimal in terms of acceptance. Yes, okay, so in fact, the vertex resolution is about several millimeters. So 2.5 centimeters is not just not only dictated by the vertex resolution, but also by, I mean, let's see. Okay, yes, it's mainly dictated by, right, you're right. So, okay, I don't know. I mean, yes, it will improve, but I don't know how much. And also for heavier beams, it will be also better because of larger multiplicity.
Thank you.
Okay.
And what is your target mass dependence? It's much faster than 8 to 1, right?
Okay, it's hard to say. I'm not here.
No. I believe it was next one. No? No. Look, yeah. You see, it's from CC to...
No, this
it is slower than 8 to 1. Yeah.
Okay, there is a table here. Okay, so...
Here.
Yes. Okay, I don't know. I mean, here is the... Okay, this is, yes.
It increases, tenfold increase from carbon-carbon to carbon-copper.
Yes, but okay, I don't know. I mean, it should be scaled by number of participants or not. I mean, it depends on how it's presented.
And what DCM means?
Sorry?
DCM, it's Coq-Lowndes string model, but...
Dubna cascade model.
Dubna cascade model.
Yes, so it started from Dubna. Yes.
Okay. So, any more questions? If not, then thank you very much. we move to the next speaker, Kankova Anna. Background study for general process at SPD.
Листает? Ага. А, ну хорошо. Видите, как вы все подчиняете сразу.
So I will talk about the background study for Drellion process at SPD project. As it was already said before, initially this type of process was described in the paper of Matveev, Muradian, and Tahilidze 1 year before Drell and Yan. This type of the process is shown on this Femin diagram. In our study, it was calculated within PTI 6 Monte Carlo generator for the case of center mass energy of 27 GeV, and it gives us the cross section about 10 to the 3 picobarn. We did our calculation in assumption of the highest luminosity and the full year of beam operation, and in such a condition we expect up to the 10 to the 7 Drell-Yan events per year. Of course, before study the process itself, very important and big question arises about the backgrounds. First of all, first kind of the backgrounds are the background of the decay muons in the signal event itself. In this picture, we consider distribution of the number of decay muons per the same event. And we can see that about half of events do have more than 2 muons per event, and even it can be up to 8 muons per event. In our simulation, we allow particles to decay and produce muons in the cylinder of radius and size of in z direction like this. And in these conditions, the distributions of the parents of the muons look like this, when we can see that the most probable parents of the muons are charged kaons and pions. And the most probable grandparents of the background muons are the string from the Lund model, rho, k, and eta particles. For the case of the decay muons in signal events, they have distributions over their energy and PT spectrum shown on this picture in the Norman and logarithmic scale, while the signal events look like this in green color. We can apply easily, looking at this picture, the cuts on energy or momentum and the transverse momentum, like, for example, this first example and the second. After these cuts, the remaining part of signal events with additional muons are only about 4 and 0.3% correspondingly. But even in this case, when we have exactly 2 muons, we can have the situation when the first is the signal muon and the second one is the survived fake one. In one situation where the muons are of the same sign, we can easily to cut such an events. but there can exist some part of events where the muons have different signs. And after the cuts discussed above, we can say that the fraction of remaining signal events with muons of different signs are about 2% and 0.4% correspondingly for such cuts. But the main background consists of two parts, QCD, different QCD processes and so-called mini-bias events that are the events with the low PT, with the small transverse momentums. The main contribution from QCD processes give us these three sub-processes, and the signal to background ratio is 10 to the minus 6. While for the background events, the main contribution comes from low PT scattering, signal diffractive and double diffractive processes, and the signal to background ratio is 10 to the minus 7 in this case.
How do you get muons from your left column?
Sorry?
How do you get muons from your left column?
It comes from, first of all, from the interaction by strings and other with the rest. This is only the how say, part of the process. It means that quark, gluon, and the plus X. From fragmentation.
Yeah, but you should have mesons that decay to muons, nothing else. So.
Yes, muons, yes, of course. Mesons and energy and transverse momentum distribution for this processes together are shown in red color for the backgrounds, in green for signal. One can see that the most effective cuts on energy or momentum will be below 1.5 GeV, where there is the maximum gradient in the energy distribution, and somewhere also about 1.5 GeV for the transverse momentum distribution. We can play with these parameters and look what will happen. Another type of the invariant mass of the cut is the invariant mass cut on invariant mass of two muons. We can see that the biggest difference is in the region below 1 GeV, while in the rest, these two graphics will go in parallel. And so the most effective cut will be in this region where the cross-section for the signal event has the maximum. So further increase on invariant mass has no sense for minimum bias of background process, and it leads to significant loss of signal events without real improvement of signal to background ratio. While in this region we have some resonances which we have to study how to exclude them separately. This table shows us how signal to background ratio changes within the increase of the invariant mass. We see that at practical, this increase practical does not influence on signal to background ratio, while it influences very strongly on the for the number of the rest of the background. This picture shows us distributions of the distance of the decay vertices from interaction point in general in a transverse plane. in Z direction and in transverse plane two-dimensional. And this distribution, correlation distribution over transverse vertex and energy with the highest PT muon. From this plot, one can see the energy and transverse momentum correlation for the muons with maximum that called fast and minimum energy in the pair. And one can see how different type of cuts, for example, here we apply the cut on transverse momentum and energy about 1 GeV, how it influence of the number of events. We can see that the most effective cuts are here, and already we do not need to apply such a strong cut here. That is also visible very good on the correlation distributions over PT for fast and slow muons for signal and background. If we apply such a cut only on the muon with the for the fast muon, we have survived the bigger part of the signal, while for the background it cuts quite a lot. So we can propose initially this set of cuts. First of all, we choose the events with only 2 muons with transverse momentum and energy on momentum higher than 1 GeV, or with more soft cuts and cut over the PT of the fast muon. Then muons should be of the opposite sign, invariant mass greater than 0.9 on 1 GeV. The vertex of origin should lie within the distance from the interaction point, but of course this is a very difficult question which have been to study separately if we would be possible to find such muon production vertex in general in tracker. And isolation criterion. These two plots show us what does mean the isolation criteria. We do summarize energy of the final state charged particles in the cone of such a radius where at a pseudo rapidity in phi is azimuthal angle over the distribution over the direction of the muons. Here is shown for one positive muon, and we can see a very big difference, close to 0 for the signal and the background processes which can be used. And for example, isolation criteria is R equal 0.2 with the energy of particles greater than 0.5 allow us to separate a big part of the mini bias and QCD background. From this table, one can see the signal to background ratio after after all of these kind of cuts made separately and together, and to see how they influence on the signal to background ratio and on the rest on the background and rest of the and the rest of the signal. For invariant, the previous table was shown for the invariant mass 0.9, and the second is for the invariant mass 4.3. Here, the statistics of 10 to the 9 events is not enough, so only the numbers which we could obtain for the moment look like this. And we can see that the rest of the signal is much lower than in the previous table. Another kind of background where the muon pairs are produced directly are the process with the germanium production. Some processes which are available in PTA and was used for calculation are shown here. For this process, we have applied the same set of cuts, and we can see that cut over the vertex doesn't influence, because in this case muons are produced in the direction point, and cut on the invariant on the PT on the fast muon also doesn't work, but isolation criterion is supposed to work very good. The same is for the case of the lower PT cuts and the invariant mass. So, as I would say, the best criterion here is the isolation criterion, and we have to exclude the resonances. Here, gypsizer resonance doesn't have any width, but this width will be quite different in the real situation. Final table was done for separate efficiency for mini bias events for the case of the lowest cuts on PT energy, on invariant mass, and the PT of the fast muon. And final result for the separate cuts is shown here. But if we will apply all of them together, we can achieve the number like this. That's already not so bad. Of course, further we have to play with this all parameters and to try to find out which of the cuts are better. And as a conclusion, I would like to repeat that we propose cuts such choosing of events with only 2 leptons of the opposite signs with the cut on energy and transverse momentum, cut on the vertex of the muon production vertex, on invariant mass and the isolation criteria, and which allow us to suppress mini bias and QCD background up to the signal to background ratio greater than 80, with the loss of signal events about 70%, and further studied in SPD route is needed. Thank you for attention.
Thank you very much. Questions, please?
Anya, if you compare these 4 cuts which you list,
yes.
What is can you estimate the role of each? For example, number 2.
Yes, of course, it's shown in all of my.
Yes.
Yes, the role is shown here. If efficiency That means the ratio from the initial, from the final and the initial signal. So this is.
So this is the main one, or no?
No. This is work good. This is yes, much better. And the same is shown for signal. How much we cut off the signal events within such cuts.
But the distance, here, where is the cut? Less than 1. Exactly, this was my point. Here it's listed by number 5, but in your final it's number 2. So the role of this distance less than 1 millimeter when you identify muons going from one point is it's 5,000, right?
Sorry, this is altogether, but in the previous section here, it is free. But anyway, if you will look, the difference is, so it means from this free, this should be done together, and this can be done separately. And as you can see, the difference from here to here is about 3 orders of magnitude, so it's very important. But it's a big question if it will be possible to find out.
No. No? That ratio 80 between signal and background is kind of weak, and it needs to look into that.
Yes, of course, this is a big question about this possibility.
The next page, the next slide, and the last line.
Yes, but the next slide is all of this together after this cut. So if this cut will not be possible, it will not be so good, unfortunately.
No more questions? Then thank you very much.
Указка, а это запасная указка.
This is the title of my talk, and I would like to talk about this dominant radiative one-photon transition of germanium orbital excitations. And this is outline. My talk consists of 2 parts. The first part consists about this model which we use, and then the second part, this detail of theoretical calculation and numerical results. About motivation. Nowadays, the germanium stars are very intensively searched in different experiments, and particularly the recent measurements of the dominant radiative decays made by the LHC-B collaboration should be described by theoretical means. So one of this theoretical approach may be used is this so-called covariant confinement quark model, which is approved in different areas of particle physics, strong, weak interaction, and heaviness and boson physics. So we will use this conventional pattern. This means quark and quark pattern for mesons, CC bar, this germanium particles, and in particular there is 2 ground states. This is specific scalar and the vector mesons. This is eta C and gypsy. And germanium orbital excitation K scalar axial vector and tensor ones with spin 0, spin 1, and spin 2. So very quickly about this model. This model is Lagrangian-based formulation, so it possesses full Lorentz invariance. So direct inclusion of higher number of quark states is possible, for example, for 3 quarks, tetraquark, and so on, bond states. And wide application and convincing results have been obtained by calculation of the leptonic decay form factors, semi-leptonic, non-leptonic, heavy mesons, heavy baryons, and so on. So very basic assumptions of this model. So hadrons interact by quark exchange with hadron-quark coupling. These couplings, this is Lagrangian. And the matrix element between physical and Bayer states is determined by the renormalization constant, ZH, this is, and the very known compositeness condition, this renormalization constant should be equal to 0, eliminates the Bayer fields from the consideration. And this second basic idea is to use infrared confinement is introduced to guarantee the absence of all possible thresholds corresponding to the quark production. So it allows to use the same values for the constant quark mass. It means to use this quarkonium C bar and so on, B bar and so on. So let's consider meson-quark interaction. This is the Lagrangian, this is quark currents used. And here this vertex function is translationally invariant. And the most simple form is this Gaussian form here. And this is momenta, and this is so-called hadron size. Its inverse is lambda h is, in some sense, the mass scale of this hadron. And so this quark percutter can be written in Schrödinger representation. For example, this is, the most leading order diagrams for leptonic decay constants, electromagnetic decay rates, or meson this polarization mass function. And all of them, maybe this is, for example, the mass function can be written in this form, and then all the singularities is generated by this exponential. For example, for some configuration of mesons, this value is Z0, maybe tends to 0, for example. Then this exponential, this damping effect disappears, and then this integral over T converges, so everything is convergent, and we can make a calculation. So this means that instead of infinity, now we put here, and this lambda, small lambda is global value, and this is so-called confinement scale. So in this model, a meson is characterized by parameters. First, this renormalized coupling constant J, and this has parameter lambda h, and 2 constant quark mass we have. In fact, we have only one mass of a charmed quark, and the global infrared confinement parameter lambda. And so the model parameters are constant quark masses, hadron size parameters, universal infrared cutoff, this lambda, small lambda. So totally, in fact, only one parameter for per hadron. So, for example, we fixed the model parameters by fitting different physical processes. For example, by this is lambda is about 590 MeV, and this quark masses, constant quark masses in the yellow box. Here in this yellow box, And the fit values of this has parameters, for example, for this meson substance here. And this generally, the meson size shrinks as the mass grows. So let's consider this Chermenov additive effects. And recently, this LHC calibration report, they brought the first observation of these decays of lambda B boson into chi meson, these orbital excitations, and proton, for example, proton and count mesons. And they measured the ratio of branching fractions, and this interesting fact is that the branching ratio between this axial one and to tensor one is equals to, it's very, in fact, they are equivalents, but when you consider this B meson case, this is the branching rate of these mesons here, then Bell, Babar, LHC calibration report that this should be suppressed. But some theoretical estimation claimed that factorization approach, by using factorization approach, it should be suppressed. But Bell calibration recently, 3 years ago, says that if additional particles are present in the final sets, then this suppression should be lessened. So this is particle data group data. Here is this spin and mass and currents, and this is total decay width and this branching ratios also. So we consider this ratio of these mesons into tube psi plus photon, and this is triangle diagram and bubble diagrams, and then we calculated these form factors corresponding and calculated these widths. Now for the scalar excitations, this matrix elements gauge invariance condition requires that matrix elements looks like here with the coefficients T here, and then the decay width can be calculated by this formula. Here is form factor. Also the same for axial vector excitations. Now we have for matrix elements 5 Lorentz structures like this, but this is with here. But by using gauge inference first and the relation between these tensors, these are 5 tensors by using cyclic transformation, and they survive only 2 independent covariants. And for example, by using Helst amplitudes, we can calculate this decay widths in this form here. So for tensors, it's more complicated, but again, by taking into account gauge inference, we have this matrix element consisting from 2 independent form factors A and B. Then this we calculate this decay widths by using this formula. So for this coupling constant, we calculate coupling constant by using this equation for this compositeness condition here. And we see that, for example, for G psi, this is black curve, and the red curve stands for this scalar germanium, and then axial one, and this green one is for tensor one, and it's quite different. But all of them starting from lambda, this size parameter, starting from 3, 4, they tend to one stable plateau. This means that when you go to this point-like, this physical size is shrinks when this lambda increases. So when go to this point-like description, then the first two, one tends to very similar value, but they differs. So when you calculate independent decay widths of these mesons to one photon radiative decay widths for this one photon radiative decays, independence of the lambda size parameters, you obtain these curves. This is quite different. So we have fit this experimental data, and so we obtain this lambda size for GPSI, for scalar 1, for axial vector, and for tensor mesons in this. Then we obtain this our theoretical calculation for this decays. This is last column. So what we see, first agreement between our fit values and the particle data recently is quite satisfactory. And the constant quark mass and the values of lambda fall into the expected range, and the meson size, this is meson size, shrinks as the mass grows. So the summary and the talk, we obtained calculate the renormalized coupling constant for all these three particles, and then calculate dominant radiative transitions, and by fitting the experimental data, we fix this size, which can be used then when we consider light mesons, radial excitations, exotic mesons, and heavy baryon decays, and so on. So thank you.
Thank you very much. I'd like to comment that it's a remarkable feat that you are having predictions to widths which are within 1% agreeing with experiment.
Yes, but
what are typical accuracies of the potential models? Standard potential models?
Yes, I agree, yes. But our model is not potential. This is full, totally relativist. Yes, yes.
You are doing better than potential models?
In this case, yes.
Any more questions? Please.
You estimate coupling constant.
Yes, renormalized, yes.
It's also nice to calculate G square over 4 pi, analog of structure, because this is the perturbated expansion parameter.
Yes, I agree, yes.
So to your values about 6 corresponds the fine structure constant about 3. And this is the value for fine raw meson interaction coupling constant. So there's some correlation to vector meson.
Okay.
Any more questions? If not, then thank you very much again. And I put the next speaker, Sergey Yeltsin. He's not here. Okay, then we are moving to the last speaker of the session, Nikolai Volchansky.
Volchansky is coming, so just
coming.
Yes.
Okay.
Yeah. Что это такое?
Может, это не принес еще?
Не знаю. Так. Но тут есть...
А может, вот предпоследний?
Ну вот тут XVIII, меня это смущает. Это что? Ну да, попробуем. А нет, это он грузит XVIII. Коля, давай. Ваш XVIII загружен.
Okay. So the title of the talk is on the screen.
My talk will consist of 3 parts. Firstly, I will say a few words about thank you. What the composite vertices are and why it's worth considering the correlators of multiple composite operators. Then I will talk about how to calculate such objects. It will be a brief exposition of the results obtained in our recent paper in JHAP. And finally, I will talk about some simple and straightforward QCD applications of the results obtained here. In QCD, the composite vertices are usually appear usually as a result of QCD factorization of hard and soft scales. One of the simplest examples is the process to photons to neutral pion with large photon virtualities. Its matrix element can be parameterized in terms of transition pion form factor. And diagrammatically, it's shown here. What we see on the right-hand side of this equation is the result of the standard factorization valid up to height with corrections. It's a convolution of 2 objects. The hard one is called the coefficient function, and the second factor is the distribution amplitude defined here. It's given by a bilocal current on the light cone. The Fourier image of this current is called the composite operator. Expanding the Wilson line, we can derive the Feynman rules for the composite vertices. In the simplest case, when we have 2 patterns, 2 quarks, the vertex is simply is different from the standard vertex by the Dirac delta like this one. Now, if we look at the correlator of the composite operator and some local current, that could be axial vector, vector, or even tensor current, it's useful because such correlators give us distribution amplitudes of mesons in the framework of QCD sum rules. But we can also consider even more general object, a correlator of 2 composite operators. We will see that such things are useful because they can simplify some calculations. So I will skip this slide. How to calculate a correlator of 2 composite vertices in 2 loops? This is called a kite diagram. All propagators are massless. We consider arbitrary space-time dimension and indices of the edges of the lens. Both vertices are composite, which means that we have to deal with 2 Dirac deltas like these ones. Like The momentum integral is easy one. It can be performed in the alpha representation because the Fourier images of the Dirac deltas are given by the exponential functions. And to proceed further with this expression, we can use a following trick. We can apply the barrel transform to the both sides of this equation. A beautiful property of the barrel transform is that the barrel of the exponential function is the Dirac delta, which gives us the third Dirac delta function. And 3 of 5 integrations over the alpha parameters become trivial. The integral is then expressed in terms of leftover double integral, which is now a function of a single variable given by this ratio of the Bjorken variables. It's sometimes called a conformal ratio because objects like this are observed in considering the conformal properties of the evolution operators. This leftover integral is obviously an integral of the hypergeometric type. It can be expressed in terms of the so-called the compare de Fourier function. It's a function of 2 variables. It can be thought of as a product of 2 generalized hypergeometric series with such mixing gamma functions in coefficients. Particular special cases of the compare de Fourier function include all hypergeometric series in 1 variable and many hypergeometric series in 2 variables, like the Apple functions. This general result is important because it gives us analytic properties of such correlators and allows to construct epsilon expansions of such diagrams. There are some standard algorithms for this purpose. We can also derive a chain of reductions to simpler cases, to simpler functions, down to the genuine two-loop case with all indices equal to 1. One of the examples is the case when 2 indices of adjacent external lines are natural, M and N are natural numbers. Then the compare de Fourier function reduces to a hypergeometric series in 1 variable, more precisely a finite sum of the generalized hypergeometric functions. We can also derive the Merlin moments of such correlators. Such objects were considered in the literature for 40 years. There are 2 brilliant recent reviews. Byproduct of our consideration is that we can to derive all these special cases and reductions by a completely independent way, by a direct evaluation of the hypergeometric intervals in the Euler representations. Some conclusions, some summary of the results to this part of my talk. We can calculate all chi-type correlators in two loops, and all the results can be expressed in terms of KDF functions, with exception for some general Mellin moments that are expressed as Varicello functions. We can find a chain of reductions to Ciclo functions in particular cases. In particular, some results important for QCT applications that I will discuss now. The first application is the calculation of radiative corrections to QCD sum rules for low energy meson distribution amplitudes. If we consider next to leading order corrections to a correlator of two axial vector currents, this correlator gives us some rules for pion and longitudinal row meson. We have to calculate this set of diagrams. And to calculate this one, we need the integral like the one, the integral belonging to the class we discussed earlier. All calculations we have carried out are done in covariant Xi gauge, just to check that all Xi terms cancel, gauge invariant terms cancel as expected. Which means that all master integrals are correct in this sense. The logarithmic part of correlator was obtained long ago by Radyushkin and Mikhailov, and the final part is the new result. The distribution amplitude of pion and longitudinal row is given by the Borel transform of the correlator. A qualitative measure of importance of contributions to the distribution amplitudes is the inverse momenta to the sum is the inverse momenta of the distribution amplitude. We can see that next to leading order gives quite important contribution, 26% approximately. The similar result can be obtained for the transversal row meson. It was first obtained by Brown and Ball. We reproduce this result in our way. And an upper limit of a sort on next to leading order is 15%. It's obtained by setting the threshold to infinity, and for the Borel parameter and mu equal to 1 GeV. Now we can consider a part of next to order contributions, in particular the terms proportional to beta 0. The result is here, is written here. This is a comparison of next to leading order and next to leading order proportional to beta 0 terms, blue line. we can see that it's quite considerable correction in the immediate range of X. But at the endpoints, it's not so much significant. If you look at the inverse momenta, we can see that at mu equal to 1 GeV, the correction is approximately 3%. But for some other functionals where the immediate range of X is important, the correction can be much larger. For example, in the heavy quark physics. And the last application is the calculation of VVA correlator, vector-vector, axial-vector correlator. This correlator can be expressed in terms of 4 invariant form factors. The parent contributes into one of them, and there is a non-renormalization theorem that states that all radiative corrections to F1 should cancel each other. We can use this result and the factorization theorem to cross-check calculations of perturbative coefficient functions. In next to leading order, we can see that these two terms into the factorization, flowing into the factorization, indeed cancel each other. And it's a correction, it's a cross-check of sort of this calculation, because to calculate a two-point correlator is much simpler than to calculate a 4-point correlation function. But if we look at the next to leading order, more specifically the terms proportional to beta 0. Unexpectedly, we can see some disagreement. Our result is here, and the result obtained in this paper is written here. The parts in blue and red colors are different. They are different even in the degree of transcendentality. Here we have zeta 3, and here we have only zeta 2. And I'm almost done, my conclusions. So we find out a way to calculate two-point correlators of composite currents. We have calculated such currents for arbitrary space-time dimensions and line indices. The result can be expressed in terms of hypergeometric series of in two variables. We, starting from these results, we can calculate next to leading order NLO and NLO contributions to distribution amplitudes for pi and longitudinal and transversal row meson in the framework of QCD sum rules. And we have made an attempt to cross-check the coefficient functions for transition point form factor at this level with the help of the triangle VVA anomaly. Thank you.
Thank you very much. But I fail to understand, do you have some correction to the Butler-Ardeen theory?
No.
Fully confirmed?
Yes, of course. It was confirmed by this paper and in this one. What we have is a disagreement between these two calculations. One is the calculation of the coefficient function, and our calculation is the calculation of two-point correlator. And for some reason we don't understand yet, it doesn't work. These two terms in factorization theorem do not cancel each other.
So some terms coincide and some do not coincide, right?
Yes.
Can you identify the source of non-coinciding term, or this is?
Yes, of course.
The same.
Yes.
What is
Bottom lines.
Bottom line, yeah, but can you see where these terms are coming from?
Well, I cannot say where these terms come from, because it's not my calculation. But of course I can show you precisely what diagram in this blob gives you all these terms.
Because they look quite different, right?
Yes.
Very different. And did you compare them numerically? Are they very different numerically?
Numerically?
Yes.
No. To be honest, no.
It can be also interesting. Maybe you can derive some new relation.
But it looks like 10 new pages in Grasted region. You know, we still have to learn something. Any more questions? Please.
You mentioned modified Lorentz function. But Lorentz functions are four types, A, B, C, and D. Which one is modified? Or maybe your modification reduces to each of the four, and this reminds somehow M theory, which introduced two different consistent string terms.
Which reminds what?
You can say whichever. The indices are A, B, C, and D. B is most important.
You can see the definition here. In fact, it's the most general hypergeometric series in three variables. You have all three terms corresponding to hypergeometric series in every variable, and you have a general mixing term with completely arbitrary coefficients in the sum of indices R1, R2, and R3.
Well, you mentioned the corrections to transverse polarized rhombism, right? And it's known just for a long time that just if you take chiral or GPD, convert it with transverse polarized meson, at leading order it's zero, and even if you go to next two leaders, it's also zero. Is your correction satisfies this, or it may can be some really correction to this? So if you just this is very simple property. So if you take chiral or GPD with sigma, and if you take transverse polarized vector meson sigma, and if you take leading order contributions, due to simple algebra, it gives zero. But if you take corrections, if you do it accurately, it was discussion,
some time ago in the literature, it's also 0. Maybe just can you somehow prove? And there is some physical explanation that it is due to conservation of helicity by Marcus directly. So maybe you can start look using your integral. Is it satisfied? I don't know.
We haven't checked this.
Because I guess you didn't check this, right? Not yet.
Well, thanks. Once again, and thanks from speaker. And thanks to the speaker. And we can say who did show up. Miracle did happen. We finished earlier.
Yeah. And can start the welcome party.
оставляем здесь все или
Понятия не имею. Унесут за ночь.
не знаю.
Зал закрывается, нет?
Ну, мы можем закрыть.
Но если зал закрыть, то можно оставить.
А ты знаешь, что тут надо выключить? Открываешь, потом открываешь это, потом нажимаешь вот это.